Welcome. Over the next 5 hours, we are going to cover what happens after you deploy your system in production. How do you evolve a database schema on a table with billion rows? How do you deploy safely when millions of users are concurrently active? And how do you figure out what went wrong when there is an on-call incident and that is involving 15 different microservices? So that is the gap between having system design in the initial stages and then actually running one in production. So this is what exactly we're going to cover in the next 5 hours. So let's get started. So here is exactly what we'll cover. On the architecture side, we'll cover how production constraints shape your design choices, service boundaries, and API contracts. Then we'll cover synchronous versus asynchronous communication patterns. Then we'll also cover data schemas that can evolve for billions of users without downtime. And then we'll also cover caching and queue patterns that survive failures, and then the deployment strategies that make sure that your on-call stays peaceful. On the operations side, we'll cover failure handling with timeouts, retries, circuit breakers. So in a general system design content, things like, okay, let's cover a cache. However, we go a step further in this course and we cover things like cache invalidation, thundering herd problem, and TTL trade-offs. In a normal course, things will be said that, okay, let's use a message queue. But in this course, we try to go a bit step further and we try to cover more in-depth concepts like dead letter queues, idempotency, and poison message handling. In a normal course, we'll cover things like in the beginning, for example, let's do a deployment of production. But in this course, we will go a bit step further and we'll try to cover as many concepts as possible. For example, we'll be covering canary rollouts, feature flags, and rollback safe migrations. Here is a code insight. Interview designs they optimize for explaining and to be able to cover a system design question in 45 minutes. However, when you're designing systems of production, that takes much more longer to design, build, and operate and evolve over many years. In a system design interview, the process is pretty linear. You gather requirements, you sketch an architecture, you pick a database, you define your APIs, and the conversation pretty much has to wrap up between 1 hour for the duration of the interview. It's a snapshot of a design at a single point in time. However, in production, that process becomes a continuous cycle. You design, you deploy, you monitor, you learn, you evolve, and then you keep repeating the process for many years. The system is essentially never finished because the requirements change, traffic grows, dependencies fails, teams change, and the architecture has to absorb all of it. This cycle, which is deploying, monitoring, evolving, is where the engineers like us we spend most of our careers. And is the part that determines whether a system is pleasant to work on or painful to operate. Let me put some specifics on this gap. For example, on the time horizon, the interview is roughly 45 minutes. However, a production system has to evolve for many years. For schema changes, in an interview, you design a schema once. However, in production, you have to add and remove columns and tables with millions of rows while the application is actively being read and written to, and you have to do all these changes with ideally zero downtime. Now, failures. In an interview, you can say that, okay, we'll handle failures, but in production, you have to go in much more detail like, okay, how do you implement circuit breakers? What do you do for retry budgets? And how do you implement bulkhead isolation? For deployment, it's very rarely discussed in interview due to the time limit. However, in production, you are choosing between rolling updates, blue-green deployments, and canary rollouts. For debugging, in production, you would need structured logs, correlation IDs, and distribute tracing across microservices, which in interview generally we don't cover that deeply. For cost, in production scenarios, you are making decisions that can save or waste hundreds of thousands of dollars per year, so you have to keep cost in your mind at all times. And for on-call, let's say someone on your team is responsible for responding when something breaks at any hour. Generally, the on-call rotates for every team member. The quality of your architecture directly determines how often you'll be facing multiple incidents and how often can your DRI actually be much more peaceful. So this course that we are covering today is about the second column, which is focused heavily on production scenarios. Who can already pass a system design interview, but they haven't operated a system in production at real scale. It is also for engineers who have built and operate systems, but they would like to understand these patterns in a more structured way. And it's also for anyone preparing for senior or staff level interviews, where interviewers expect you to reason about deployment, failure handling, and cost, not just architecture diagrams. So, for prerequisite, you should have a working understanding of basic system design fundamentals. The course has 5 parts, and each one of the part builds on the previous one. So, the part 1 is foundations. This is the introduction and architecture boundaries. Part 2 is building blocks, where we cover the data and production, caching, queues, and async workflows. Part 3 is operations, which covers reliability, observability, and deployment. In Part 4, we'll cover scale and cost, in which we'll be covering security, cost optimization, and multi-region architecture. And for Part 5, which we'll be covering and combining everything that we have covered so far, which is incident management, 3 case studies, and summary. The sequence of this course is intentional, so you need architecture boundaries before you can make good data decisions. You need data patterns before you can make caching decisions that make sense. And you need all of that before you can reason about deployment and incidents. Here is a section by section breakdown. We start with the introduction and architecture boundaries. Then we cover the data and production, covering schema evolution and migrations. Then we cover caching, queues, and async workflows, including the patterns that prevent the thundering herd problem and poison messages. After that, we cover reliability patterns like circuit breakers and graceful degradation. Then we cover observability concepts like logs, metrics, and distributed tracing. And then we move to deployment strategies, including canary rollouts and feature flags. In the end, we also cover security concepts, cost optimization, and multi-region architecture. And then we finish with incident management. Before we get into the technical material, let's cover about the mindset that makes the foundation of this course. Early in your career, the primary question is, okay, how do I build this feature? That is the right starting point, but as you grow more older in your career, that thinking has to evolve. As you gain experience, the question expands itself. So it becomes like, okay, how do I build this feature so that it's observable, so that I can tell whether it's working in production or not? It's recoverable so that if it fails, I can fix it quickly when something goes wrong. And it's evolvable so that I can keep building on top of this feature and it can change without breaking and causing regressions. So a younger engineer can, maybe they will ask questions like, okay, does it work? But a more experienced engineer will ask questions like, okay, does it work? Can I prove it works? And can I fix it at, let's say, when I'm sleeping and there's an on-call incident at 3 in the morning and I have to get on a bridge call with many other engineers. So you have to really think about operating things in production for a longer period of times. So that's what we're going to cover in this course today. Now let's talk about the constraints that shape every production system. There are 5 constraints that come up in virtually every design decision. Number 1 is uptime SLA. So 99.9% availability means 8.7 hours of total downtime per year. 99.99%, which is the 4 nines, means 52.6 minutes per year. So every deployment, every migration, every infrastructure change has to fit within that budget if that's the goal for your team and your system. Second, latency budget. A common target is P99 under 500 milliseconds. That is 500 milliseconds has to be divided across every component in the request path, which is network, load balancer, auth, application logic, database, cache, and even external APIs. If any single component exceeds its allocation, the overall request will miss its target. The third is cost. That covers compute, storage, bandwidth, database instances. All of these components cost real money. A single architecture decision can swing your monthly bills by tens of thousands of dollars. Fourth is team size. 5 engineers cannot realistically operate 50 microservices. Your architecture has to be something your team can actually build, deploy, and also debug. And fifth is compliance. This covers frameworks like GDPR, SOC 2, HIPAA. These are legal requirements that restrict architecture choices in non-negotiable ways. The key insight is that in an interview, you optimize for ideally elegant solutions that you can fit in 1 hour. In production, you have to optimize under constraints, and those are often very different targets. Let's move to the next section. We'll be covering 4 topics that form the foundation for everything else. The first is production requirements. We'll work through uptime SLAs with the computing math that catches team off guard sometimes in production, latency budgets with component level allocation, cost constraints with real dollar amounts, team ownership and Conway's law, and compliance requirements that restrict the data flow. The second is service boundaries, when to keep a monolith and when to split, which is super important. We will also learn how to identify good boundaries versus bad ones, API contracts with schemas and SLAs, versioning strategies, and the backward compatibility rules that will protect your consumers. The third is synchronous versus asynchronous communication. For example, when to use each, hybrid patterns like synchronous response with asynchronous processing, and then we'll also cover the trade offs between latency, consistency, and debugging complexity. And the fourth is stateful versus stateless services. So, why stateless is preferred for horizontal service scaling when state is generally unavoidable like WebSockets, and how to manage sessions using JWT tokens will be some very important concepts that we'll be covering as well. And these topics connect directly. Production requirements determine your service boundaries determine your communication patterns, communication patterns will determine your state management approach. Let us now start with requirements. Let us start with availability because the math here is more nuanced than it appears. The availability targets look deceptively similar. 99% availability called 2 nines means 3.65 days of data downtime per year and 7.3 hours per month. 99.9%, which is 3 nines, means 8.76 hours per year and 43 minutes per month. 99.99 4 nines means 52 minutes per year and only 4 minutes per month. And 5 nines, which is 99.999%, means 5 minutes per year and 26 seconds per month. Each additional 9 represents a roughly 10x reduction in allowed downtime. Going from 3 nines to 4 nines does not sound significant on paper, but is the difference between 8.76 hours and 52 minutes of annual downtime. The additional 9 requires substantial more engineering effort, infrastructure redundancy, and operational discipline to achieve. Now here's where the math gets super important. Your system depends on multiple components and each of which has its own availability. Suppose your database has a 99.99% SLA. Your cache, let's say it has a 99.99%, and your message queue has a 99.9%, and an external API has a 99.9%. So then your combined availability of this product will be 0.999 times 0.999 times availability of the payment gateway and the fourth component, which will equal to approximately 99.78%. That translates to roughly 2 hours of downtime per month. Even though each component is individually quite reliable, the combined system is meaningfully less reliable than any single component. Your system's availability is bounded by your least reliable dependency. That single fact should drive your fallback and redundancy design for every critical path. So how does this availability math changes your architecture? An interview level answer might be something like, okay, we'll use a database and a cache. That is a reasonable starting point, but it does not address what happens when either one of them is unavailable. A production level answer accounts for failure paths. For example, a database and a cache combined gave us the 99.98% availability. To reach our 99.99% target, we need a fallback from cache to database so that the cache failures do not become user-facing errors. We need read replicas for database failover so that a primary failure does not take down reads. We need circuit breakers so that a slow dependency does not consume all of our connection pools and cascade into a broader outage. And we need a graceful degradation so that the system returns partial results rather than failing entirely when a non-critical dependency is slow or unavailable. The architecture should handle this cleanly. When the cache is available, the request is served from the cache. When the cache is unavailable, the request falls back to the database. In both cases, the user gets a response. They might see slightly higher latency on the fallback path, but they do not see an error. Every dependency in your system should have a defined fallback path. If it does not, that dependency's downtime becomes your system's downtime, and your availability target becomes impossible to meet. Now let us look at latency budgets because this is where production thinking gets very concrete and very practical. Suppose your SLA targets P99 response time under 500 milliseconds. That 500 milliseconds is the total budget for everything in the request path, and you need to allocate it deliberately across every component. Network from the client to the load balancer gets about 50 milliseconds, accounting for geographic distance. The load balancer itself should take about 5 milliseconds, or then rate limiting should take about 20 milliseconds for token validation. Application logic gets about 100 milliseconds for business rules and data transformation. The database query gets about 150 milliseconds for complex queries with joins. Cache lookup should take about 10 milliseconds. An external API call gets about 150 milliseconds for a third-party dependency. And you can keep about, let's say, 15 milliseconds as buffer for unexpected delays. That totals roughly 500 milliseconds, so there is no slack in this budget. Every component has an allocation, and if any single component exceeds it, the overall request misses the SLA. If your database query takes around, let's say, 200 milliseconds instead of 150 milliseconds, you have exceeded the budget by 50 milliseconds and your users experience degraded performance. Latency budget forces you to understand exactly where time is being spent in your request path. They make you identify and address slow components proactively before they even become a problem rather than reactively after users start complaining. Now let us talk about why we track P99 rather than average latency, because the distinction has real consequences for how you operate. P50, which is the median, tells you the experience of a typical request. P95 tells you the experience at the slower end. P99 tells you the experience of the slowest 1% of the request. And P99.9% or 9 tells you the experience of the slowest 0.1%. So why does the P99 matter so much? Consider a system handling 1 million requests per day. A P99 of 500 milliseconds means 10,000 requests per day exceed that threshold. That is 10,000 users getting noticeably slow experience every single day. In many systems, the users who hit the P99 tail are disproportionately your most active users. They make more requests, so they are more likely to hit complex code paths, and they are often your most valuable customers. Your average latency can look perfectly healthy, while a meaningful number of important users are having a poor experience. The average hides the problem, P99 actually reveals it. The production practice is to measure P50, P95, P99 for every service. You set your alerts on P99, not on your average. When we get to the observability section later in the course, we'll cover exactly how to implement this and histograms, how to set up the SLIs and SLOs around these percentiles, and how to build dashboards that surface latency problems before your users report them. Now let us talk about the constraint that very rarely gets covered in system design interviews, but that can single-handedly determine whether your architecture will survive in production or not. And that constraint is cost. Most courses will tell you that you should be adding a cache or add a CDN or spin up more instances, but it's very rarely being told that what actually cost when you're running at this much scale. So let us break this down with real numbers, because when you're sitting in a design review with your engineering director and you say that it should scale, that's not enough. You need to back it up with what this new field is called as FinOps. So you need to be able to say exactly what it will cost and why to run your infrastructure. For example, a single compute instance, a virtual machine in the cloud, should cost you somewhere between $100 and $500 per month, depending on the size. That sounds perfectly reasonable, but in production, you are not running one instance. You are running hundreds of instances for redundancy, for handling traffic across availability zones, for absorbing traffic spikes. So now your compute bill can alone be just by roughly around $50,000 per month. Whereas your database instances, which is something like RDS, should cost between $500 and $200 per month, depending on your use case and traffic. So if you need 10 of those for read replicas, failover instances, and databases for different services, that is another roughly around $15,000 per month. Now for cache, which is something like Redis, that should run about $30 to $50 per gigabyte per month. So let's say at 500 gigabytes, which is realistic for a large scale application caching user sessions, computed feeds, and hot data, that is roughly $20,000 per month. Now here is where it gets interesting. Storage, something like AWS S3, is actually quite cheap, about $23 per terabyte per month. Even at 100 terabytes, that is roughly only $2,300. Storage is one of the few things in the cloud that is genuinely inexpensive. However, for bandwidth, that specifically Egress, which is data leaving your cloud provider, should cost about roughly $90 per terabyte. And CDN bandwidth is very similar, which is around $85 per terabyte. At 500 terabytes of CDN traffic, you are looking at roughly around $42,000 per month just for content delivery. And this brings us to the hidden cost that catches almost every team off guard, which is egress. Data leaving your cloud provider is often the single largest surprise on your bill. To put this in perspective, let's say at Instagram scale, CDN egress alone cost would be around $50 million per month. It's not a typo, $50 million per month to serve images and videos to its users. But we have to keep in mind that Instagram operates at internet scale, which is even more than 2 billion users. So the next time someone says that, okay, we can just put something behind a CDN, you need to understand that at scale, the CDN is also one of the most expensive components in your entire architecture. So now that you understand what things cost, let us look at how cost should actually shape your architecture decisions. Because this is where strong engineers separate themselves from everyone else. They do not just design for correctness and performance, they design for cost efficiency, and they can justify every trade-off with real numbers. Let us look at a concrete example here. Imagine you're building an image service and you need to serve images in multiple sizes, thumbnails, let's say medium and full size. You have a decision to make. Do you compute all the sizes when the user uploads the image, or do you compute them on the fly when someone requests a specific size? The first approach is eager computation, computing on upload. You pay a higher compute cost once at upload time, and you pay a higher storage cost because you're storing every size for every image. But your latency is low because images are pre-computed and ready to serve the instant someone requests them. The second approach is lazy computation, which is computing on the request. Your storage cost is low because you only store the original image, but your compute cost is high because now you're recomputing the same resize over and over again every time someone requests the size. And for the first user to request a specific size gets hit with high latency while the computation happens. This is a bad user experience for use cases, let's say profile pictures that get viewed thousands of times. The third approach is hybrid. You should be computing early on upload and cache the results on a CDN. This gives you medium compute cost, medium storage cost, and consistently low latency on every request. So which approach should you pick for production? I would say you should consider picking hybrid approach, leaning towards the eager computation. And here's the reasoning behind it. Because storage is cheap, which is at $23 per terabyte, compute and latency are, however, very expensive. So it makes sense to generate 3 standard sizes at upload time, cache them on your CDN, and accept the slightly higher storage cost in exchange for consistently low latency for every user. And that is a key takeaway from this slide. Every single architecture decision you make has a cost implication. It is not enough to just say that, let's say, this design is correct or this design scales. Strong engineers should be able to estimate cost and justify their trade-offs. Let's say when you walk into a design review and you can say, let's say that this approach costs $50,000 more per month, but it saves us 200 milliseconds on P99 latency for highest value users. That is when people know that you think like someone who has actually operated systems in production. Now let's talk about a constraint that is not technical at all, but it shapes your architecture more than almost anything else. And that is your team structure. There is a famous observation in software engineering called Conway's law, and it says that organizations design systems that mirror their actual communication structure. So what does that mean in practice? It means that your architecture will reflect your team structure whether you plan it or not. This is not a suggestion or a best practice, it is just an observation about how organizations work. Your team boundaries will become your service boundaries, your communication overhead will become your network overhead, and your reporting structure will become your dependency graph. Let me give you some concrete examples. If you have one team with 5 engineers and you're going to end up with a monolith or maybe 2 to 3 microservices, and that is the right architecture for that size. There's nothing wrong with a monolith when you have a small team. If you have 3 teams with 15 engineers in total, you should probably have around 5 to 10 microservices with clear ownership boundaries where each team fully owns and operates those services. And let's say if you have 10 teams with 50 engineers, that is when a microservices architecture with a dedicated platform team starts to make sense because you have enough people to absorb those operational overload. Now, there is an anti-pattern that I have seen which causes real pain in production. So let's say, for example, 5 engineers trying to maintain 20 microservices. In this scenario, the operational overhead will absolutely crush the 5-member team. Every single service will need its own monitoring, alerting, deployment pipelines, on-call coverage, documentation, dependency management, and security patching. Multiply that by 20, and your 5 engineers are essentially spending all their time keeping the lights on and zero time building features. A good production rule is that one team should own no more than 2 to 3 services. If you have more services than engineers, then you have a problem that no amount of automation can fully solve. So, what does ownership actually means in production? When you say a team owns a service, that means 5 specific things, and all 5 are non-negotiable. The first is code. That team writes and reviews all the code for that service. No other team commits to that repository without going through this team's review process. The second is on call. That this means that the team responds to pages when something breaks at 3 a.m. They are the ones who get woken up, and they are the ones who are responsible for restoring the service. The third is the SLA. That team is accountable for uptime and latency of the service. If the service misses the availability target, that team owns the exploration and the remediation plan. The fourth is roadmap. So that means that the team decides what features get built, what technical debt gets paid down the road, and what are the priorities are. And the fifth is dependencies. So that means that so that the team responsible will be managing the upgrades and deprecations of everything with the service that it depends on, from library versions to downstream API changes. Now here's the anti-pattern that causes the most damage in real organizations: shared ownership. When you say everyone owns it, that means no one owns it. When an incident happens at 3 a.m., who gets paged? If the answer is unclear, if people have to check a wiki or ask in a Slack channel, you do not have clear data on the ownership. It needs to have more clear visibility into it. And ownership must be explicit, document, and unambiguous. Now let's talk about compliance. This is another constraint that rarely comes up in system design interviews, but in the real world, compliance requirements are fundamentally how they change how you architect a system. And ignoring them is not an option because the consequences are legal, financial, and reputational. Let me walk you through the most common compliance frameworks and what they require. GDPR, the European Data Privacy Regulation law, has two major requirements that affects your architecture. The first is right to deletion, meaning you must be able to find and delete all of specific users' data across every system on request. The second is data residency, meaning EU user data must physically remain inside the EU. SOC 2 requires audit logging, meaning every access to sensitive data must be logged with who accessed it, when, and why. HIPAA requires that all healthcare data is encrypted at rest, not just in transit. And PCI-DSS requires network segmentation, meaning payment systems must be on isolated network segments that are not accessible from a general application infrastructure. Let me make the data residency requirement concrete. If you have a user in Germany, their request must be routed to your EU region, and their data must be stored in your EU database. You cannot route EU user data through US servers, even temporarily, even in the cache, even in a log file. This has a massive impact on how you design your routing layer, your database architecture, your replication strategy, and even your logging infrastructure. So let us compare how an interview answer and production's answer will differ when it comes to compliance. In an interview, you might just say user data is stored in our database with replication. That is technically correct, but completely insufficient for production. A production answer sounds more like this: that user data is stored in regionally partitioned databases. EU users are routed to EU West 1. US users are routed to US East 1. Cross-region replication excludes PII fields. We maintain the deletion capability with soft delete plus a 30-day hard delete job. All access is logged to immutable audit storage for SOC 2 compliance. The difference in these two answers is night and day. And this is the level of thinking that distinguishes strong engineers who have operated systems in production from those who have only limited system design experience. Before you finalize any architecture, you should be asking yourself 5 questions. The first is, where is data stored geographically? This matters for data residency laws. The second is, can we delete all user data on request? This matters for right to deletion requirements. The third is all access logged. This matters for audit requirements. And the fourth is data encrypted at rest and in transit. This matters for security standards. And the fifth is, are payment systems isolated? This matters for PCI-DSS. So if you cannot answer all 5 clearly and specifically, your architecture is not production ready. Now let us talk about something that most courses completely ignore, which is the fact that your system will look completely different on day 1 versus day 100 versus day 1000. On day 1, you might have 100 users, 1 gigabyte of data, 3 engineers, and a single monolith. Your SLA is best effort because honestly, if it goes down for an hour, nobody really notices because you have a small user base. By day 100, you have 10,000 users, 100 gigabytes of data, 10 engineers, and you probably split into between about 5 microservices. Your SLA is now 99.9% because customers are paying you money and they expect things to work. And you have started the on-call rotation because someone needs to respond to things when things break outside of your business hours. By day 1000, you have almost, let's say, 1 million users and 10 terabytes of data and 50 engineers and 30 services. Your SLA is now 4 nines, which is 99.99%, and you have a 24/7 on-call coverage across multiple time zones. The architecture that works on day 1 will not work on day 1000, but here's the important nuance. You should design for the next 10x, not for the next 100x. If you have 1000 users today, you should be designing your system to handle 10,000. Do not design a system to handle 10 million. Over engineering for scale you do not have yet wastes engineering time, increases complexity, and makes it harder to iterate on the product. You can always re-architect when you hit the next order of magnitude in terms of traffic. So how do you know when it's time to re-architect? The answer is you follow the pain signals. You do not re-architect because you predict future problems. You re-architect because you're experiencing real problems today. There are 5 key signals to watch, which is the first is the deploy frequency. If your deploys are getting blocked by other teams and you're waiting for more than 2 days, that is a signal that your service boundaries are wrong and the teams are stepping on each other. The second is incident rate. If the same service is causing more than 2 outages per month, something structural needs to change because the band-aids are not working. The third is latency. If your B99 is approaching 80% of your SLA budget, you are running out of room and a single regression could push you past your SLA. The fourth is cost. If a single component is consuming more than 40% of your total infrastructure spend, that component needs attention because it is likely not optimized or is doing too much. And the fifth is team friction. If you have recurring arguments about code ownership, that is an organizational signal that your service boundaries do not align with your team boundaries. The key production practices here. Do not re-architect based on predictions. You should be re-architecting based on your observed pain. Premature optimization of architecture is just as wasteful as premature optimization of code. You should be waiting until the pain is real, measurable, and affecting your ability to deliver new features to users. The most important decisions you will make in production, which is to when to split a monolith into microservices. My recommendation, and this is based on seeing it play out many times in production, is to start with the monolith. A monolith gives you 5 important advantages. The first is simple deployment. You have one artifact to deploy, one CI/CD pipeline to maintain, one version to track. The second is simple debugging. There is one log stream and one process. When something goes wrong, you are not chasing traces across 15 microservices. The third is simple transactions. Database asset works naturally. You do not need sagas or compensating transactions. The fourth is fast development. There are no network calls between the components. A function call takes nanoseconds, not milliseconds. And the fifth is that it is small team friendly. One code base, one on-call rotation, one set of dashboards. So when should you split? There are essentially 4 clear signals. The first is different scaling needs. If your feed service needs 100x more instances than your upload service, deploying them together means you're wasting compute on the upload service just to scale the feed service. The second is different deployment cadence. If your auth changes weekly but the payment changes monthly, coupling them means auth waits for the payments to be ready, or payments takes on unnecessary risk by deploying with auth changes. The third is different team ownership. If there is a clear organizational boundary between 2 teams, a service boundary often makes sense there too. And the fourth is fault isolation. If a payment failure should not crash your feed, then they need to be separate processes so one cannot take the other service down. So how do you actually identify where to draw the boundary? There is 4-step process. First, identify your domains, then draw data boundaries around those domains, then verify that your boundaries align with team structure, and finally, extract the service. For each potential boundary, you should ask yourself four questions. The first is, does this domain have its own data? If the user service owns the user's table and nothing else reads or writes that table directly, that is a good split. But if a service shares tables with other services, meaning multiple services are doing direct SQL queries against the same tables, that is a bad boundary. You will have coordination nightmares and possible outages with this. The second question is, does this have a clear API? If you can define clean, stable endpoints like post users, get users by ID, that is a clean boundary. But if the communication between these components is a bunch of internal function calls with complex parameter passing, extracting a service will be painful. The third question is, can a different team own this? If the auth team can fully own the auth service, including code, on-call, and SLA, that works. But if a single engineer would end up owning 5 services, you have not actually separate concerns. You have just added more network hops. And the fourth question is, does this scale differently? If search needs, let's say search service needs significantly more compute than the rest of the system because of the computational cost, indexing, and ranking, separating it lets you scale search service independently. And here is the anti-pattern I would want you to warn about, which is to splitting too early. Premature microservices add network latency, operational overhead, and debugging complexity without giving you any of the benefits. You should be splitting when you feel the pain, not when you are predicting the pain for future. Now let us talk about what happens once you do split into microservices. The moment you have two services talking to each other, you need a contract. An API contract should define 6 things. The first is endpoint, meaning the URL path and the HTTP method. Something like get v1 users followed by the user ID. The second is a request schema, defining which fields are required and which are optional. The third is response schema, covering both the success format and the error format. You need to define both because your consumers need to handle both. The fourth is the SLA, specifying the latency and availability guarantees. For example, P99 under 100 millisecond and 4.9's uptime, which is 99.99% uptime. The fifth is rate limits, which specifies how many requests per second each client is allowed. Without rate limits, one misbehaving client can take down your whole service for every other user. And the sixth is versioning, defining how breaking changes will be handled over time. Let me walk you through a complete contract, how it looks like. The user service owned by the, let's say, identity team exposes a get endpoint at v1 users followed by the user ID. The SLA is P99 under the 50 milliseconds with 99.99% availability. The rate limit is 10,000 requests per second. The request requires a path parameter for user ID and an authorization header with the bearer token. A successful 200 response returns the user object with the user ID, username, email, and created at timestamp. A 404 response returns a structured error object with an error code like user not found and a human readable message like user with user ID 12345 does not exist. The level of specificity is what separates a production contract from a handshake agreement that falls apart the first time someone makes a change. So why do contracts matter this much? Let me paint you in 2 pictures. Without the contracts, a provider changes a field name and nobody will know until production breaks. A consumer assumes a field exists that was never guaranteed. Breaking changes show up at 3 a.m. on-call incidents, and the postmortem dissolved into, let's say, who did what, and where nobody can point to a documented agreement. So with contracts, a contract test fails before the deploy even reaches production. Every field is documented and versioned. Breaking changes are caught in the CI, not in production, and ownership and expectations are clear from the start, so when something does go wrong, the conversation is productive instead of adversarial. In this model, the provider service has a set of provider tests and the consumer service has a set of consumer tests, and both are verified against the same contract definition. If either side changes in a way that violates the contract, the tests fail and the deploy is blocked. The production practice here is straightforward. Every service boundary needs a documented contract. Any change to the contract requires a version bump and a migration period, no exceptions. This discipline is what allows large engineering organizations with dozens of teams to ship independently without breaking each other. Okay, so now that we have contracts, the natural question is what happens when you need to make a breaking change? And that brings us to API versioning. There are three common versioning strategies. The first is URL versioning, where you put the version right in the path. For example, /v1 users /v1 /users v2 /users. The second is header versioning, where the URL stays clean and the version is specified in a request header except version v1. And the third is query parameter versioning, where you pass something like, let's say, /users version equal to 1. My personal recommendation is using URL versioning, and here is why. It is explicit and visible. When someone does read your code, they can immediately see which version of the API is being called. It is easy to understand, there is no hidden configuration, and most importantly, it is easy to route at the load balancer level. You can point /v1 traffic to one set of servers and /v2 traffic to another set of servers, which gives you the ability to run both versions simultaneously during migration. Header versioning is cleaner in terms of URLs, but it's hidden and it's easy to miss. When debugging, you would have to inspect the headers to know which version was called. Query parameter versioning is flexible but easy to forget, and most CDNs and caching layers do not handle query parameters consistently. Let's talk about the lifecycle of a version, because creating a new version is just the beginning. You need a clear process for how versions age and eventually get removed. A version should go through 4 phases. The first phase is current. This is the active version with full support and active development. This is what new clients should integrate with. The second phase is deprecated. This should last 3 to 6 months. No new features are added, only security fixes. You're actively encouraging clients to migrate to the new version during this period. The third phase is sunset. This should last 1 to 3 months. Warning logs are emitted with every request to the old version, and migration reminders are sent to client teams. This is the final warning period. And the fourth phase is removed. At this point, the endpoint returns a HTTP 410 gone response, and clients must have migrated. Any client still calling this endpoint will get an error. In production, you should communicate deprecation through response headers. The deprecation header should be set to true. The sunset header should specify the exact date when the version will be removed, like Saturday, July 1st, 2025. You should also add a link header to point to the successor version URL so clients know exactly where to migrate. You should also be logging which clients are still using the deprecated version so you can reach out to them directly and help them migrate before the sunset date. Now let us talk about what you can and cannot change without bumping a version. Understanding backward compatibility rules is critical because you get this right, you can evolve the API continuously without forcing every consumer to update their code simultaneously. There are 4 types of changes that should be safe and backward compatible. The first is adding an optional field to a request, like adding a nickname field. For example, old clients can simply do not send it to it, and this is fine because the field is optional. The second is adding a field to a response, like adding an updated at field. Old clients will ignore fields they do not recognize, which is the default behavior of most JSON parsers. The third is adding a new endpoint entirely, like adding, for example, get /v1 /users followed by the user ID /post. This does not affect an existing endpoint. And the fourth is widening the accepted values, like accepting either email or phone for login when you previously only accepted email. Or old clients sending email still work exactly as before. Now here are 5 changes that break backward compatibility and will require a version bump. The first is removing a field from response. Old clients expecting that field will get a null or crash. The second is renaming a field, like changing user underscore name to just username. Old clients looking for the wrong field name will actually now fail. The third is changing a field type, like changing age from a string to an integer. Any client parsing age as a string now will break. The fourth is now adding a required field to a request. Old clients will do not send it, so the request will start failing validation. And the fifth is changing the URL structure, like going from, let's say, /users followed by the ID to accounts followed by the ID. Old clients will call the wrong URL. So what do you do when you need to rename a field but you cannot break existing clients? You use the expand contract pattern. Let us say you need to rename user underscore name to username. In phase 1, the expand phase, you add the new column and return both fields in the response. Both user underscore name and username contain the same value. Old clients will read the user underscore name, new clients will read username. Everyone is happy, both fields are there, and nobody breaks. In phase 2, the migrate phase, you update all clients to read from the new username field. This happens over a few weeks as different teams update their code at their own pace. You monitor the logs to see which clients are still reading the old field. In phase 3, the contract phase, you remove the old user underscore name field from the response. By this point, all clients have been updated, so removing the field is safe. The typical timeline is expand in week 1, migrate over weeks 2 through 4, and contract in week 5. This pattern takes longer than a direct rename, but it guarantees zero breakage for any consumer. And in production, zero breakage is always worth the extra time. The operational cost of a breaking change, the incidents, the emergency patches, the cross-team coordination far exceeds the cost of spending a few extra weeks on a phase migration. Okay, now let us shift gears and talk about one of the most fundamental architectural decisions you will make: synchronous versus asynchronous communication between services. In synchronous communication, the client sends a request and waits for a response. It is blocking, meaning the client cannot do anything else until the response arrives. It is immediate, meaning the response comes within milliseconds. It is simple, meaning it follows a straightforward request-response pattern. But the client and server must both be available at the same time. If the server is down, the request fails. In asynchronous communication, the client sends a message to a queue and continues immediately without waiting for a response. The response, if there is one, comes later. It is non-blocking, meaning the client can continue doing other work. It is decoupled, meaning the client and server can be unavailable at different times, but it is more complex because it requires a queue, callbacks for polling, and careful error handling. So how do you decide which to use? Here is a decision framework. You should be using synchronous when the user is waiting for a response and needs it now. The operation completes fast under 500 milliseconds. Failure should be visible immediately so the user can take action. You need a simple request response pattern, or you need strong consistency where the user sees the result of the action right away. You should be using asynchronous when the user does not need an immediate result and can check back later, but the operation takes longer than 1 second. Failure can be retried automatically without the user knowing, and you have a complex multi-step workflow or eventual consistency is acceptable. Let me give you 3 concrete examples. Getting the user profile should be synchronous because the user is waiting on screen and looking up, the lookup should be fast. Login should be a synchronous operation as well because the user must know immediately whether their credentials are valid. Uploading a photo should be asynchronous because processing an image, generating thumbnails, and running content moderation takes 5 to 10 seconds. Sending a notification should be also asynchronous because the user who triggered the action does not wait for the notification to be delivered. Now, generating a report should also be asynchronous because it takes minutes to run complex aggregation queries. And charging a payment should be synchronous because the user needs immediate confirmation that their purchase has been successful or not. The key takeaway is that decisions should always be driven by the user experience requirement and the operational duration, not by a technical preference. Now let us go deeper into synchronous patterns and the rules that makes them work reliably in production. In a typically synchronous flow, the client sends a request to the API gateway, the gateway forwards it to the user service, the service queries the database returns the result, and the response flows all the way back to the client through the gateway. Every hop adds latency and every hop is a potential point of failure. This is why timeout configuration is critical. Each hop should have its own timeout, and here is the most important rule. Inner timeouts must be shorter than outer timeouts. The client to gateway timeout should be around, let's say, 30 seconds to allow for slow mobile networks. The gateway to service timeout should be about 5 seconds because the service should be fast. The service to database timeout should be about 2 seconds because queries should be optimized. And the service to any external API should be about 3 seconds to account for the external dependencies latency. Now here is why the ordering matters. If your database timeout is 5 seconds, but your service timeout to the database is only 3 seconds, the service will give up on the database call before the database finishes processing. The database is still doing work, consuming resources, but the service has already returned an error to the caller. Worse, the error message will say the service has been timed out, not that the database timed out, making debugging incredibly confusing. Always ensure that the timeouts get shorter as you go deeper into the call chain. Now let me walk you through two synchronous anti-patterns that cause serious problems in production. The first is chain of synchronous calls. Let's say API calls service A, which calls service B, which calls service C, which calls service D. Every call is synchronous. The problem here is threefold. Your total latency is the sum of all four services, so if each takes 100 milliseconds, the user will be waiting 400 milliseconds. If any single service in that chain fails, the entire request will fail, meaning your availability is a product of four services' availability. And debugging becomes painful as well because at a timeout at the API level could be caused by any service in the chain, and you have to trace through all of them to find the culprit. The second anti-pattern is synchronous fan-out. Your API calls service 1, service 2, and service 3 simultaneously in a synchronous fashion, waiting for all three to respond before returning to the client. The problem is that you must wait for the slowest service. If service 1 and 2 responds in 50 milliseconds, but service 3 takes 2 seconds because it is having a slow moment, your entire response takes 2 seconds. One slow dependency dictates your latency. The solution to both is the same. Parallelize independent calls where possible and move non-critical calls to async. If the user does not need data from service 3 to see the page, do not block the response on it. You should be firing it asynchronously and then let the result arrive later. Now let us look at asynchronous patterns in production. The most common is queue-based pattern. A producer enqueues a message, the queue holds it reliably, and a consumer dequeues it and processes it at its own pace. This pattern works well in 5 specific scenarios. The first is slow processing like image resizing or video encoding, where the operation takes seconds or minutes. The second is unreliable consumers, like an external API that may be down temporarily. The queue absorbs the messages and the consumer processes them when it comes back up. The third is spiky traffic, where you need to absorb bursts of requests and process them at a steady rate. The queue acts as a buffer between the traffic spike and your processing capacity. The fourth is a fan out, where one event needs to be processed by many different consumers. And the fifth is retry logic, where failed messages should be retried automatically without the producer needing to know about the failure. Now, which queue technology should you be using? For example, you could use AWS SQS, which is a general purpose and handles about 10,000 messages per second. It is fully managed, so you do not have to operate the queue infrastructure yourself. You can also consider using RabbitMQ, which is great for complex routing scenarios at about 220,000 messages per second. Apache Kafka is built for high throughput streaming at over 1 million messages per second and can retain messages so consumers can replay them. And Redis Streams is a good option for simple queuing at about 100,000 messages per second if you already have Redis in your stack. The other major asynchronous pattern is event-driven architecture using publisher-subscribe. In this pattern, the user service publishes a user-created event to an event bus. Then the email service, analytics service, and billing service each independently subscribe to that event. The user service does not know who is subscribed. It does not know how many subscribers there are. It just publishes the event and moves on. This gives you 4 significant benefits. The first is loose coupling. The publisher does not know or care who is subscribed. You can add or remove subscribers without touching the publisher. The second is easy extension. Want to send a welcome email when a user signs up? Just add a new subscriber. No changes needed in the user service. The third is the independent scaling. The email service and analytics service can scale completely independent based on their own processing needs. And the fourth is failure isolation. If the email service goes down, analytics and billing continues to process the events without any interruption. When you design events, your event schema should include an event type like user.created for routing, a unique event ID like ABC123 for deduplication and tracing, a timestamp for ordering and debugging, and the actual data payload containing the relevant information like user ID and email. This structure enables reliable, traceable event processing across your entire system. In practice, many production systems use a hybrid of sync and asynchronous communication. Let me show you the most common hybrid pattern, which is synchronous response with asynchronous processing. Here is how it works. The client sends an upload request to the API, receives the request, validates it, stores the work item in a queue, and immediately returns an HTTP 2 to accept a response. That response contains the job ID, a status of processing, and a status URL that client can poll for updates. The client gets an instant response in under 100 milliseconds. Meanwhile, in the background, a worker picks up the job from the queue, processes it, which might take seconds or minutes, and when it's done, it's either sends a push notification to the client or updates the job status so that the client's next poll gets the result. The pattern is perfect for three common scenarios. The first is photo uploads, when you return immediately but process thumbnails, run content moderation, and generate metadata asynchronously. The second is report generation, when you return a job ID and the user can poll for completion or navigate away and come back later. The third is batch operations, where you acknowledge receipt of a large request and process everything in the background. Now let us look at another hybrid pattern that is very common in production, which is asynchronous with synchronous fallback. This comes up a lot in feed generation. When a user requests their feed, you first check the cache for a pre-computed feed. If there is a cache hit, you return it immediately. That is the synchronous fast path around 50 milliseconds. If there is a cache miss, you have three options. Option A is to compute the feed on demand synchronously. This gives you perfectly fresh data, but at the high latency around 500 milliseconds, because computing a personalized feed requires querying multiple data sources and running ranking algorithms. Option B is to return the stale cache feed if one exists and trigger an asynchronous refresh in the background. The user gets a fast response at around 50 milliseconds and the feed will be fresh on the next request. Option C is to return an empty or minimal feed immediately and push the fully computed feed to the client when it's ready using WebSockets or server-side events. This is the fastest initial response but the most complex to implement. In most production systems, option B, stale plus refresh, hits the right balance. Users get a fast response, the feed refreshes in the background, and most users they never notice the brief period of staleness because feeds they change continuously anyways. Now let us zoom out and talk about the fundamental trade-offs between synchronous and asynchronous, because understanding these trade-offs deeply is what helps you make the right choice in every situation. The core trade-off is latency versus consistency versus complexity. Synchronous gives you high latency because the user waits for the full operation to complete, but strong consistency because the operation is done when the response arrives, and lower complexity because request response is a simple, understood pattern. Asynchronous gives you low latency because the user gets an immediate acknowledgement, but only eventual consistency because the actual processing happens later, and significantly higher complexity because you need queues, workers, retry logic, and correlation IDs. So what does the consistency difference means in practice? With synchronous writes, the user creates a post, it writes to the database, and the post is visible immediately. What you wrote is what you read. There is no gap. With asynchronous writes, the user creates a post, the post goes into a queue, a worker eventually picks it up and writes it to the database, and the posts become visible sometime later. What you wrote will eventually be readable, but there is a window where the user might not see their own post. So the key question to ask yourself is, can the user tolerate seeing stale data for a few seconds? For a bank balance, that's absolutely not the case, so that must be synchronous. For a social feed, every few seconds of delay is fine, so async synchronous works in this case. For an inventory count, tolerance is low because overselling is costly, so you probably want synchronous with cache invalidation. And for analytics dashboard, minutes of delay are perfectly acceptable, so the asynchronous is ideal. Now let's talk about the other major trade-off that does not get enough attention, which is debugging complexity. With synchronous systems, debugging is relatively straightforward. A request comes in, you follow the call stack, you find the error in the logs, you fix it, and then you deploy. Single trace, single log stream, single process. The entire flow is visible in one place. With asynchronous systems, debugging is fundamentally harder. A request comes in, a message goes to a queue, a worker picks it up, maybe minutes later, or on a completely different machine with completely different logs. The worker processes the message, an error occurs, and now you need to correlate across multiple systems, multiple machines, and multiple time windows to understand what happened. The request that triggered the error might have happened 10 minutes ago on a different server, and there is no call stack connecting them. This is why asynchronous systems absolutely require 4 additional pieces of infrastructure. The first is the correlation ID, a unique identifier that travels with the message through every system so you can trace the full journey. The second is dead letter queues, a separate queue that captures failed messages instead of losing them so you can inspect and reprocess them later. The third is message replay, the ability to reprocess failed or lost messages, which is essential for recovery. And the fourth is distributed tracing, tooling that lets you visualize the flow of a message through your entire system across services and queues. These are not nice to have. These are actually, without them, debugging an asynchronous system in production will become a very hard problem, which can turn a 3-minute investigation, like a 10-minute investigation, into like many hours of investigation work. Okay, now let us move into stateful versus stateless services and why stateless is strongly preferred in production. A stateless service does not store any client session data between requests. Every request that arrives contains all the information the server needs to process it. A stateful service, on the other hand, stores client session data that persists between requests. The server remembers something about the client from a previous request. With stateless services, you get 4 major benefits. The first is horizontal scaling. You can add new servers to your fleet without migrating any data or worrying about which server has which user's state. The second is simple load balancing. Any server that can handle any requests, so your load balancer can use simple round-robin distribution. It does not need to be smart about routing. And the third here is failure resilience. If a server crashes, no client data is lost because the server was not storing any. The client simply retries the request and a different server handles it. And the fourth is simple deployment. You can replace any server without draining sessions or worrying about losing active user state. In a stateless architecture, state does not disappear. It gets externalized to dedicated state stores that are designed to manage state reliably. Session data goes into Redis or Memcached. User data goes into your database. File uploads go into object storage like S3, and cache data goes into a Redis cluster. The request itself should contain all the context the server needs to process it. The most common approach is to use the JWT token in the authorization header. The JWT contains the user ID, the user's role, and an expiration timestamp. The server receives the request, decodes the JWT, validates the signature and expiration, and processes the request. No server-side session lookup is needed, no trip to a session store, no dependency on remembering which server this user was talking to previously. This is what makes stateless services so powerful for scaling. Any server in your fleet can handle any request because the request carries its own context. You can add servers, remove servers, restart servers, and deploy new versions without any coordination around user state. Now, despite the strong preference for stateless services, there are cases where state generally cannot be externalized. Let us go through the 3 most common ones. The first is WebSocket connections. A WebSocket connection is inherently stateful because the TCP connection itself lives on a specific server. The client and server maintain a persistent bidirectional channel. If you need to send a message to that client, you have to find the specific server holding their WebSocket connection. You cannot move a WebSocket to another server mid-conversation. The second is in-memory caches for extreme low latency. Redis might give you 1 to 5 millisecond cache lookups, but for some use cases like a trading system or a real-time recommendation engine, even 1 millisecond is too slow. Local memory access happens in nanoseconds, which is 1,000 times faster. If you need sub-millisecond cache for access, local memory is the only option. The third is long-running computations. If a server is 20 minutes into a 30-minute video encoding job, you cannot easily move that computation to another server. The intermediate state, the partially encoded video, the position in the encoding pipeline, all of that lives in server's memory and on the local disk. So when state is unavoidable, you have 3 strategies to manage it. The first is sticky sessions. The load balancer routes the same client to the same server every time using a cookie or a hash of the client's IP. This is the simplest approach, but it has a significant problem. If that server fails, all sessions on it are lost. Every user on that server has to re-establish their session. The second is state replication. All servers maintain a copy of all state by replicating to each other. If server A goes down, server B already has a copy of all of server A's sessions. This provides redundancy, but the replication overhead can be significant, and maintaining consistency across replicas adds complexity. The third is graceful handoff. Before a server shuts down for maintenance or deployment, it transfers its active sessions to another server. This preserves all the sessions, but it's complex to implement, and the transfer process itself takes time, during which the user might experience a brief interruption. Each strategy trades simplicity for resilience in different ways, and the right choice depends on your specific requirements for how much session loss is acceptable and how much complexity you can take on. Now let us talk about how to handle user sessions specifically, because this is where the stateful versus stateless decision plays out most directly in your code base. Option 1 is server-side sessions, which are stateful. The client sends a session ID in a cookie. The server looks up that session ID in a session store and retrieves the user's data, their user ID, their shopping cart, and their preferences. The problems are clear. The session lives on one server, or at best in a shared session store that every server queries. You need either sticky sessions or a shared store like Redis, and server memory or Redis memory grows linearly with the number of active users. Option 2 is JWT tokens, which are stateless. The client sends a JWT in the authorization header. The server decodes the token and extracts the user ID, expiration time, and roles. No lookup is needed here. No round trip to Redis as well, and no dependency on the session state. Any server in your fleet can validate the token by checking the cryptographic signature. But JWTs have their own problems. The most significant is that you cannot revoke them immediately. Once a JWT is issued, it is valid until its expiration time. If you need to log a user out right now, you cannot invalidate their JWT. You would have to wait for it to expire, and the token size grows as you add more claims, which increases the size of every HTTP request. The production pattern that solves the JWT revocation problem is JWT with refresh tokens. When the user logs in, you return two tokens, an access token with a short lifetime of 15 minutes stored in the client's memory, and a refresh token with a longer lifetime of 7 days stored in a secure HTTP only cookie. The access token is used for all API calls. Because it expires in 15 minutes, the fact that it cannot be individually revoked is acceptable. The worst case is that the revoked user retains access for up to 15 minutes, which is an acceptable security trade-off for most applications. The refresh token is used to get a new access token when the current one expires. The client sends the refresh token to a dedicated token endpoint and receives a fresh access token. For revocation, here how it works. Access tokens cannot be revoked individually, but they expire in 15 minutes anyways, so the window of risk is small. Refresh tokens can be revoked because they are stored in the database with the revoked flag. When a user logs out or when an admin revokes a user's access, you set the revoked flag on the refresh token. The current access token continues working for at most 15 minutes, but when they try to refresh, the server checks the database, sees the revoked flag, and refuses to issue a new access token. The pattern gives you near immediate logout capability combined with the horizontal scalability of stateless JWT authentication. It is standard approach used by most production systems today. Now let us go deeper on sticky sessions, because despite the preference for stateless services, there are situations where you generally need them. Sticky sessions work by having the load balancer set a cookie on the client, something like server ID equal to server A. All subsequent requests from that client include this cookie, and the load balancer reads it and routes that request to server A. There are 4 legitimate use cases. The first is WebSocket connections, because the connection is inherently tied to one server and cannot be moved. The second is in-memory server caches, where you would want to avoid the latency of a distributed cache lookup on every request. The third is long polling, where the client is waiting for a response from a specific server that is processing their request. And the fourth is gradual rollouts, where you would want to keep a user on the same application version for the duration of their session so they get a consistent experience. But sticky sessions, they come with three serious problems that you need to plan for. The first is uneven load distribution. Some users are more active than others. A power user might make 100 requests per minute while an average user makes 5. Then sticky sessions pin users to servers. You can end up with server A handling 1000 active sessions, including 50 power users, while server B has 100 sessions and server C has 50. Your load balancer can no longer distribute load evenly because it cannot move users between servers. The second is server loss on server, session loss on the server failure. So let's say if server A crashes, all 1000 users on it lose their sessions immediately. Every one of those users would now have to re-authenticate, reload their state, and start their workflow over. For a shopping site, that means 1000 abandoned carts. The third is deployment complexity. When you need to deploy a new version to server A, you have to either drain all this 1000 sessions first, which means waiting for those users to leave naturally and could take hours, or you accept losing 1000 active sessions, which means 1000 users get interrupted. The mitigations are periodic sessions rebalancing to address uneven load, session replication to a standby server to address server failure, and graceful draining with session handoff for deployments. But each of these adds significant complexity. This is why sticky sessions should be your last resort, not a default choice. You should first exhaust all your stateless options first. Let us take a moment to consolidate everything we have covered in this section. For production requirements, your uptime SLAs compound across dependencies, so your actual availability is a product of all your dependencies SLAs. Latency budgets force you to make optimization decisions early by identifying which components can afford to be slow and which cannot. Cost constraints shape architecture choices at every level, and senior engineers should be able to estimate costs and justify trade-offs with real numbers. Team structures determine service boundaries through Conway's law, and compliance requirements restrict how data flows through your system in ways that can fundamentally alter your architecture. For service boundaries, start with the monolith and split when you feel that real measurable pain. Every service needs a single clear owner who is responsible for code, on-call, SLA, roadmap, and dependencies. API contracts are the law between services, and changing them requires a version bump and migration period. You should also add backward compatibility features and make sure that it protects your consumer from breaking changes. For synchronous versus asynchronous, you should be using synchronous when the user is waiting and the operation is fast. You should use asynchronous when the operation is slow or when failure is tolerable. Hybrid patterns like synchronous response with asynchronous processing combine the best of both. And always remember that asynchronous significantly increases debugging complexity, so invest in correlation IDs, dead letter queues, and distributed tracing. For stateful versus stateless, prefer stateless for horizontal scaling. Externalize state to databases and caches. Use JWT Refresh Tokens for session management, and treat sticky sessions as a last resort with known trade-offs around load distribution, failure resilience, and deployment complexity. Now let me give you a practical decision framework you can use when making these choices in your real-world production projects. For monolith versus microservices, if your team is smaller than 10 engineers and your system is less than 2 years old, you should definitely start and stick with monolith. If you observe different scaling needs across components or different deployment cadences that are blocking each other, then you should consider splitting into microservices. Otherwise, stay with the monolith. Do not split on speculation and possible future needs that might never materialize. For synchronous versus asynchronous, if the user is waiting for the result and the operation completes in under 500 milliseconds, use synchronous. If the operation takes more than 1 second, or if it can fail silently and can be retried without the user knowing, use asynchronous. For everything in between, use a hybrid pattern where you give the user a synchronous acknowledgement but do the heavy processing asynchronously. For stateful versus stateless, if you can externalize all state to a database, cache, or object store, use a stateless service. This should be your default. If the connection is inherently stateful like a WebSocket, use sticky sessions with state replication for resilience. Otherwise, evaluate the specific trade-offs case by case. These are not absolute rules. There will always be edge cases and context-specific considerations, but this decision framework gives you a solid starting point that will be correct from vast majority of production systems that you will encounter. So let us now take stock of what we have covered so far before we start the next section. In section 1, the introduction, we talked about the gap between interview design and production reality, what production constraints actually look like with real numbers, the production mindset that separates senior engineers from junior engineers, and the structure of this course. In section 2, production requirements and architecture boundaries, we went deep on 5 categories of constraints: uptime, latency, cost, team ownership, and compliance. We covered Conway's laws and how team structure determines architecture. We explored service boundaries, including when to split, how to define API contracts, how to version APIs, and how to maintain backward compatibility. We went through synchronous versus asynchronous patterns, covering when to use each, the hybrid approaches, and the critical debugging complexity trade-offs. And we also covered stateful versus stateless services, including JWT session management, sticky sessions, and strategies for unavoidable state. Now in the next upcoming section 3, which is data in production, this is where things get really challenging because data problems are one of the hardest problems in production systems. We are going to cover schema evolution and safe migration patterns, database replication, and consistency models, and how to build backup and disaster recovery strategies that actually work when you need them. Production, and why this is arguably one of the most important sections in this course. There's a fundamental difference between code and data, and that changes everything how you operate a system in production. Code is stateless and replaceable, and if you mess up a code deployment, you can deploy the previous version and you're back to normal within minutes. The rollback is clean and predictable. However, data is stateful and irreplaceable. If you mess up a data migration, you cannot simply unmigrate. If you corrupt data, the corruption may be permanent. And testing data changes in staging is never fully representative because your production data has unique patterns, edge cases, and scale characteristics that no test environment can replicate. Let me make this concrete with a comparison on this slide. Code rollback means deploying the previous version. Data rollback means you cannot easily undo a migration that has already transformed millions of rows. Code mistakes are fixed with a redeploy in minutes. Data mistakes may require manual fixes across millions of rows, each of which needs to be carefully verified. Code scales by adding more servers. Moving data, whether it's resharding, migrating between the databases, or replicating across regions, is expensive, risky, and time-consuming. The key insight is this. Most production incidents involve data problems, not code bugs, not infrastructure failures, that is, data problems. Schema changes that lock tables, migrations that corrupt the rows, replication lag that causes stale reads. This section is about preventing these data problems before they happen. So let us start with the most common data problem in production, which is schema changes. Imagine your day 1 schema has a users table with ID, a name, and an email. Simple and clean, right? Then on day 100, let's say the product team comes to you and says, we need to split the name column into first name and last name. This sounds trivially simple, but think about what actually means in production. Now you probably have, let's say, 10 million rows in that table. Application servers are reading and writing to that table continuously, maybe thousands of queries per second. You cannot take downtime because users are actively using the system. And here is a real problem. During deployment, some application servers are running the old code that expects a name column, while other servers are already running the new code that expects the first name and last name. Both versions of your application are now running simultaneously. If this is asked in an interview, the interview answer might just be that, okay, just add new columns and migrate the data. However, the production answer is, this requires a 4-phase migration over 2 weeks with careful coordination between database changes and code deployments. That gap between the two answers is exactly what this section will teach you how to navigate. What can go wrong with the schema changes because each of these mistakes cause a different kind of production failure. Adding a not null column without a default causes every insert to fail immediately for all existing rows. Your application cannot create new users because the database enforces the constraint that existing rows violate. Dropping a column that code still references causes the application to crash because queries reference a column that no longer exists. Renaming a column without coordinating with the application code will cause queries to fail with column not found errors. And running a long migration that logs the table will cause all writes to be blocked, which cascades into request timeouts for every user. And if the migration fails halfway through, you end up with an inconsistent data state where some rows have been migrated and others have not. That is extremely difficult to recover from. The data on this is clear. Database schema changes cause roughly around 30% of production incidents at organizations operating at scale. The average resolution time for these incidents is around 2 hours, and many require manual data fixes that are painful, error-prone, and stressful. The takeaway is that schema changes are the most dangerous deployments you will make. They will require more planning, more caution, more review, and more testing than any code change, because unlike code, you cannot easily roll back a schema change once it has been applied to millions of rows. So let us talk about how to add columns safely, because this is the most common schema change you will make. The safe way to add a column is to add it as nullable. When you add a nullable column, existing rows automatically gets null as a value. Old code that does not know about the new column ignores it entirely. New code can start writing to it immediately, and most databases, including PostgreSQL and modern MySQL, adding a nullable column is a metadata only operation that does not log the table. It is virtually instant regardless of table size. The unsafe way is to add a not null column without the default value. This will fail immediately because the database cannot satisfy the not null constraint for existing rows that would have no value in the new column. The safe alternative is a three-step process. First, add the column as a nullable, which is instant and safe. Second, backfill the data in batches, updating maybe 10,000 rows at a time with appropriate sleep between batches so you do not overwhelm the database. And third, only after every single row has a value, add the not null constraint. By that point, the constraint is satisfied by all rows and the operation succeeds. There is an important nuance around adding columns with default values that depends on a database version. In PostgreSQL 11 and later, adding a column with a default value is safe. PostgreSQL stores the default in catalog metadata and does not actually rewrite the table. Existing rows are not touched. The default is applied lazily when rows are read. It is virtually instant regardless of the table size. This is a significant improvement that makes a lot of schema changes much simpler. But in the older PostgreSQL versions or in MySQL, adding a column with a default value rewrites the entire table. The database has to visit every single row and write the default value. On a table with 10 million rows, that means several minutes of table logging during which all writes are blocked. User will experience timeouts and errors. For older databases, the safe pattern is a four-step approach. First, add the column as nullable, which is instant. Second, update your application code to write the desired default value for all new rows going forward. Third, backfill existing rows in batches, setting the default value in chunks of maybe 10,000 rows at a time with sleep between batches. And fourth, only after all rows are backfilled, add the default constraint for future rows. This approach is more steps, but it guarantees zero downtime regardless of a database version. Now let us talk about removing columns, which is actually more dangerous than adding them. This might sound counterintuitive, but let's think about it. When you add a column, old code simply ignores it. When you remove a column, any code that references it crashes immediately. If you drop a column and any application code, any view, any stored procedure, or any scheduled job still references that column, your select queries will fail, your insert queries will fail as well, and your application will crash. This can happen even with the code that was not part of your most recent deployment, like a bad job that runs weekly and references a column you forgot about. This is why column removal should never be a single step operation. The safe removal pattern is a four-phase process. Phase 1. You should stop writing to the column in your application code and deploy that change. Phase 2. Stop reading from the column in your application code and deploy that change. Phase 3. Monitor for at least 1 week to verify that absolutely no queries and no bad jobs, no reports, and no ad hoc scripts reference to the column. Do you actually drop the column from the database? Execute the drop column, you should verify exhaustively that nothing is still using it. Check if the column is referenced in any database views by querying the information schema. Search your application logs and query logs for any queries mentioning the column name. Check for stored procedures and functions that reference it. And here is a production trick that adds an extra layer of safety. Instead of going straight to dropping the column, first rename it with a underscore deprecated prefix. So the middle name becomes, let's say, deprecated middle name. Then wait 1 to 2 weeks and monitor for errors. If any code was still referencing middle name, it will throw errors after the rename, which will tell you the code that still depends on that column, and you need to update it first. If nothing breaks after 2 weeks, then you can drop the renamed column. Column removal should take weeks, not minutes. That extra time prevents this kind of pretty big failure where your application crashes in production because a bad job that runs on, let's say, 15th of every month references a column that you dropped on the 3rd of the month. Now let us talk about renaming columns and why a direct rename is one of the most dangerous things you can do to a production database. Let us say you need to rename a user underscore name to username. The wrong approach is to use a direct alter table rename column. The moment the statement executes, every single line of code referencing a user underscore name breaks instantly. Every query, every ORM mapping, every report, every export job, all of them will fail. The correct approach is an expand contract pattern which has 3 carefully sequenced phases. In phase 1, the expand phase, you add the new username column alongside the old user underscore name column. You backfill the new column with data from the old column, and you create a database trigger that keeps both columns in sync so that any write to user underscore name automatically updates the username and vice versa. At this point, both columns exist and both contain the same data. In phase 2, the migrate code phase, you gradually update all application code. This happens in stages over several weeks. Initially, your code reads from the user underscore name and writes to user underscore name. During the migration, you deploy code that reads from the new username column and writes to both username and user underscore name. The trigger handles keeps keeping them in sync, but the dual write provides an extra layer of safety. After all services have been updated and you have confirmed through monitoring that no service is reading from the old column, you deploy code that writes only to the new username column. In phase 3, the contract phase, you remove the sync trigger since it's no longer needed and drop the old user underscore name column. By this point, no code references the old column, so the drop is safe. The typical timeline is week 1, add the column and sync trigger. Weeks 2 and 3, deploy code reading from the new column across all services. Weeks 4 and 5, deploy code writing only to the new column. Week 6, remove the trigger and drop the old column. Yes, this takes 6 weeks to rename a single column, and in production, that is exactly the right pace. Rushing a column rename is how you end up with a 3 AM incident that affects every user on your platform. Now let us talk about one of the most dangerous schema changes you can make, which is the changing a column's data type. Here's a real scenario. Your user underscore ID column is, let's say, is an int, which has a maximum value of 2.1 billion. Your table has 1.5 billion rows. You are approaching the limit, and if you hit it, the new user creation fails entirely. You need to change it to BIGINT, which supports values up to 9.2 quintillion. You have time, but not unlimited time. The wrong approach is to do a direct alter table to change the column type. On most databases, this rewrites the entire table, visiting every single row to convert the data type. On a table with 1.5 billion rows, this will take hours. During that time, the table will be locked for writes. Your application cannot create new users, update existing users, or even delete users. Every user-facing operation that touches that table will fail. There are three production approaches, each with different trade-offs. The first is using an online DTL tool like PT, Online Schema Change, or Ghost. This provides minimal downtime and medium complexity. The second is dual write to a new table, which provides zero downtime but high complexity. The third is a blue-green database approach, which requires minutes of downtime but it's very high complexity. Each approach is valid, and the right choice depends on your downtime tolerance and your team's experience with these tools. Let me walk you through the dual write migration pattern in detail because it is the safest approach for true zero downtime column type changes. The process has 6 steps. Step 1. Create a new table, in this case users underscore v2 with the BIGINT column for the ID. The schema is identical to the original table except for the column type you are changing. Step 2 is to update your application code to dual write. Every insert, update and delete that hits the old users table will now also hit the new users underscore v2 table. In the code example, the create underscore user function inserts into both tables within the same code path. This ensures that from this point forward, the new table stays perfectly in sync with the old table. Step 3. Backfill historical data. All the rows that existed before you started dual writing need to be copied to the new table. They should be done in batches with sleep between the batches, exactly like the batch update pattern we discussed earlier. Step 4. Switch reads to the new table. Your application now reads from users underscore v2 instead of users table. The old table is still receiving writes from the dual, but reads are now coming from the new table. Step 5 is stop writing to the old table. Now that the reads and writes are both going to the new table, the old table is no longer needed for writes. Step 6. Drop the old table after a safety period of monitoring to confirm everything is working correctly. Now let us zoom out and establish the golden rules that should govern every production migration. These are the principles that prevent the 30% of incidents caused by schema changes. Rule 1. Separate schema changes from code deployments. Deploy the schema change first, wait for it to propagate to all replicas, then deploy the code that uses the new schema. Never deploy both at the same time. If you deploy them together and either one fails, your rollback becomes incredibly complex because the code and schema are out of sync. Rule 2. All changes must be backward compatible. Adding a nullable column is backward compatible because old code ignores the new column. Dropping a column is not backward compatible and requires removing all code references first. Renaming this column is not backward compatible and requires the expand contract pattern. Changing a type is not backward compatible and requires dual write. Rule 3. All changes must be forward compatible. This means that if you need to roll back your old code deployment, the old code must still work correctly with the new schema. If you add a column, the old code should ignore it. If you change the default value, the old code should not break because of it. Forward compatibility is about protecting your rollback path. Rule 4. Migrations must be idempotent. Running the same migration twice should produce the same result without errors. Instead of create table, use create table if not exists. Instead of alter table, add column directly. First check whether the column already exists using information schema. This matters because migrations can fail partway through, and when you retry them, you do not want the retry to fail on steps that have already completed. Rule 5. Migrations must be reversible. For every forward migration, there must be a corresponding rollback migration. If your forward migration adds a column, the rollback drops that column. If your forward migration creates a table, the rollback drops the table. Every migration should be a two-way door. Before you run any migration in production, you should have already written and tested the rollback because if something goes wrong, you do not want to be writing rollback SQL under pressure at 3 a.m. These 5 rules are not guidelines or suggestions. These are the minimum safety standards for production database changes. Following them consistently is the difference between a team that deploys confidently and a team that is having challenges with every database migration. Let's talk about what happens when you need to update a large amount of existing data, which is commonly called a backfill. Let us say you need to set the status column to active for all rows where status is null and you have 50 million rows that match. The naive approach is a single update statement. The problem with this approach is severe. It logs the table for potentially 30 minutes while it's processing all 50 million rows. The transaction log explodes in size because the database has to record the change for every single row within a single transaction. And replication lag spikes because all of your replicas need to process this massive write, which can cause tail reads for the users during the entire duration. The solution is batched updates. Instead of one massive update, you process rows in chunks of 10,000 at a time. After each batch, you commit the transaction so the logs are released, and then you sleep for 100 milliseconds to give the replicas time to catch up. You track progress by recording the last process ID, so if the job fails or needs to be paused, you can resume from exactly where you left off without reprocessing any rows. In the code example, the backfill function runs a loop. Each iteration updates up to 10,000 rows where the status is null and the ID is within the current batch range. If no rows are affected, the backfill is complete and the loop exits. Otherwise, it advances the ID cursor, sleeps for 100 milliseconds, and logs progress. Now let me give you the best practices for batch configuration, because getting these parameters right make the difference between a smooth backfill and one that causes problems. For batch size, 1000 to 10,000 rows should be the sweet spot. Too small and the migration takes forever because of the overhead of starting and committing a transaction for each batch. Too large and you hold logs for too long, which can cause the queries to wait. For sleep between batches, 50 to 100 milliseconds should be a good range. This gives your replicas time to catch up with each batch before the next one starts. For progress tracking, log every batch completion with the last process ID. This serves two purposes. You can monitor the progress of a long-running migration, and you have a checkpoint to resume from if anything goes wrong. For resumability, always track the last process ID in a way that survives the process restart. If your backfill of 50 million rows fails at row 30 million, you should be able to restart from row 30 million, not from the beginning. During the migration, you should also be monitoring replication lag and log the waits on the database. If the replication lag exceeds 30 seconds, you should pause the migration and alert the on-call. Your backfill should never degrade the user experience. Users come first, backfill second. Let's talk about the specialized tools that exist for performing schema changes on very large tables without downtime. The core problem is that alter table on large tables can be extremely slow and log the table for duration. On MySQL 5.6, adding a column to a table with 100 million rows logs the table for writes potentially for hours. MySQL 8.0 improved this with the online DDL, but it can still be slow for large tables. PostgreSQL handles the add column much better because it is a metadata only change that completes instantly. But even PostgreSQL struggles with operations that require rewriting the table, like changing a column type. For MySQL, the two most important tools are PD Online Schema Change from Percona and Ghost from GitHub. PD Online System Schema Change works by creating a shadow table with the new schema, copying data over using triggers to capture ongoing changes, then swapping the tables atomically. Ghost by GitHub does something similar but uses binary log parsing instead of triggers, which avoids the overhead and complexity of the triggers. For PostgreSQL, pg_repack can repack and reorganize tables without holding logs. Now let me walk you through how Ghost works in detail because it is one of the most elegant solutions in database operations space. The process has 5 steps. Step 1, Ghost creates a Ghost table that has new schema you want. That is pretty instant. Step 2, it copies the existing rows from the original table to the Ghost table in chunks. This takes hours depending on the table size, but crucially, it does not log the original table. Your application continues reading and writing normally. Step 3, it streams ongoing changes from the MySQL binary log to the Ghost table. Every insert, update, and delete that happens on the original table also gets applied to the Ghost table. This happens continuously so the Ghost table stays current with the original. Step 4, it waits for the Ghost table to fully catch up with the original table. This typically takes just seconds because the streaming has kept it nearly current the whole time. Step 5, it renames the tables atomically. The Ghost table becomes the production table and the old table gets renamed. The swap is pretty instant. The advantages of Ghost are pretty significant. It does not use triggers, which makes it safer and avoids the performance overhead triggers create. It is possible and resumable, so if something goes wrong, you can stop it and restart later. You can test it in dry run mode before executing for real. And it has controllable throttling, so you can limit its impact on the production traffic. The production practice is to run these tools during low traffic periods, monitor replication lag continuously while the tool runs, and always have a tested rollback plan ready before you start. Let's move into database replication, which is super important how production databases achieve both high availability and read scalability. The most common replication pattern is leader-follower replication. All writes go to a single leader node. The leader writes each change to a replication log, which is in PostgreSQL is called the write ahead log or WAL. And in MySQL, it's called the binary log or bin log. Follower nodes continuously read the replication log and apply the changes to their own local storage. Then when your application distributes reads queries across the followers to spread the load. This process has 6 steps. Step 1, the application sends the write to the leader. Step 2, the leader writes the data to its local storage. Step 3, the leader records the change in the replication log. Step 4, followers read new entries from the replication log. Step 5, followers apply those changes to the local storage, bringing the data up to date. And step 6, followers either acknowledge back to the leader that they have applied the change or they do not, depending on whether the replication is configured as synchronous or asynchronous. That choice has major implications, which we'll be discussing next. The choice between synchronous and asynchronous replication is one of the most important infrastructure decisions you will make because it directly affects your data durability guarantees and your write latency. With synchronous replication, the leader waits for at least one follower to acknowledge that it has received and apply the change before confirming the write to the client. The advantage is zero data loss. If the leader crashes immediately after confirming the write, the follower already has the data. The disadvantage is higher write latency because every write has to wait for the network round trip to follow to the follower. With asynchronous replication, the leader confirms the write to the client immediately after writing to its own storage without waiting for any follower. The advantage is lower write latency because there is no waiting. The disadvantage is potential data loss. If the leader crashes before the follower receives the change, that change is lost. Semi-synchronous replication is a middle ground where the leader waits for 1 out of n followers to acknowledge. This gives you durability against single node failure without requiring all followers to acknowledge, which balances latency and safety. This creates what we call replication lag, the time between when a change is written to the leader and when it appears on the follower. Typical values are 1 to 10 milliseconds within the same data center, 50 to 200 milliseconds cross region, 1 to 60 seconds under heavy load, and potentially minutes to hours during maintenance operations. So why does lag matter so much in practice? Imagine a user creates a post which writes to the leader. The user immediately refreshes the page, which reads from a follower. The follower is 500 milliseconds behind. The user does not see its own page. They think that the system is broken. They try again, creating a duplicate. This is exactly the kind of user-facing bug that replication lag causes. Post problem. The answer is a pattern called read your writes consistency. The idea is that after a user writes something, you temporarily route their read to the leader instead of a follower, guaranteeing that they see their own writes. Here's how to implement it. When a user creates a post, you write to the leader as normal. Then you also set a short-lived flag in your cache, something like recent underscore write colon, followed by the user ID with a TTL of 5 seconds. This flag is just a marker that says this user just wrote something. Then when that user reads their post, you check the cache first. If the recent underscore write flag exists for this user, you read from the leader. If the flag does not exist, meaning the user has not written anything in the last 5 seconds, you read from a follower for better performance and lower load on the leader. This approach is elegant because the vast majority of the time, reads go to the followers, keeping a leader's load manageable. Only for the brief 5-second window after a write do you route that specific user's reads to the leader. The window is invisible to the user but completely prevents the frustrating experience of not seeing the own content. And there is a key insight from this slide. You do not need a global strong consistency for most applications. You need strong consistency for the specific user who just wrote something. Everyone else can safely read from followers with eventual consistency. And this selective consistency approach gives you the user experience of strong consistency with the scalability of eventual consistency. It's the best of both worlds. So we just looked at solution 1, which was reading your own writes directly from the leader. That works, but it puts all the read pressure back on the leader, which defeats part of the purpose of having replicas in the first place. So let us look at two smarter approaches here. Solution 2 should be a timestamp based approach. The idea here is pretty elegant. When a user creates a post, the write goes to the leader as usual, but the response back to the client should include the timestamp of when that write happened. Then, when that same user makes a subsequent read request, the client sends along that timestamp as a minimum timestamp parameter. The read path looks at that timestamp and says, okay, I need to make sure my replica has caught up to at least this point in time before I return the results. So then the system calls a wait for replication function with that timestamp and a timeout, let us say 2 seconds. If the replica catches up within that window, it serves a read. If it does not catch up in time, the system can fall back to the reading from the leader. So why should this be a preferred approach in most cases? Because it gives you strong consistency for the user who just wrote the data while still distributing read traffic across your replicas. The user who posted this comment sees it immediately. Other users who are reading from replicas that might still be slightly behind, they will see it within few seconds anyways, and for them that delay should be completely fine. Now, solution 3 should be sticky sessions. And this one takes a different angle entirely. Instead of tracking timestamps, you just make sure that a given user always reads from the same replica. So user, let's say user number 123 always goes to follower 2. Since follower 2 is receiving the replication stream in order, that user gets a consistent view of their own data, at least eventually. They will never see their data go backwards, which should be the main thing we are trying to prevent. So what is the downside for this? The load distribution here becomes uneven. If you have a power user generating tons of reads, that one replica is handling a disproportionate amount of traffic. And technically you are still getting eventual consistency, not strong consistency. The user might still not see their write immediately if the replica has not caught up yet, but to avoid the confusing experience of seeing your post, then refreshing and seeing it disappears, then refreshing again and it comes back. So now let us compare all three solutions together. The first is reading from the leader. This gives you strong consistency but poor load distribution because the leader gets overloaded. Complexity should be low since it's straightforward to implement. The second is the timestamp based approach. That also gives you strong consistency but with good load distribution because reads still go to the replicas. Complexity should be medium since you need to track and propagate timestamps. And the third is sticky sessions. That gives you eventual consistency with uneven load distribution, but complexity should be low since most load balancers support session affinity out of the box. The key takeaway here is that there should not be a single right answer for your writes consistency. The timestamp based approach should be the strongest option for most production systems because it gives you the strong consistency guarantee without sacrificing the scalability benefits of your replicas. But sticky sessions can be perfectly reasonable choice if your consistency requirement is a bit more relaxed and you would want to have the simplest possible implementation. Now let us talk about what happens when the leader dies. This is one of those topics that separate systems that work in demo scenarios from systems that work in production. Because in production, your leader node will go down at some point. Hardware fails, network partition happens, processes crash. These things are bound to happen in production. The question should never be if it happens, but when it does happen, how does the system handle it? The failover process should follow 4 steps in sequence. First, you need to detect when the leader has actually failed. Then you need to elect a new leader from your existing followers. Then you need to reconfigure the remaining followers to replicate from the new leader instead of the old one. And finally, you need to update the application layer so it knows where to send its writes. Now that's the first step. Failure detection should be the trickiest part because you need to distinguish between a leader that is generally dead and a leader that is just slow or temporarily unreachable. There are three main methods for detecting failure. The first is heartbeat timeout. The leader sends periodic heartbeats, and if the followers stop receiving them for somewhere between 10 to 30 seconds, they assume that the leader is down. Detection time should be moderate, but the risk of false positives should also be moderate. A leader that is just experiencing a brief network blip might get declared dead when it's actually fine. The second is consensus based detection using protocols like Raft or Praxis. They should be much faster, typically 1 to 5 seconds for detection, and false positives should be low because multiple nodes need to agree that the leader is unreachable. The third is manual intervention. When a human operator makes a call, detection time could be minutes to hours, but false positives should be essentially zero because a human is verifying. In practice, most production systems use consensus based detection because that 1 to 5 second window hits the sweet spot between speed and accuracy. Once the system has confirmed the leader is dead, it needs to elect a new leader. The criteria for choosing which follower gets promoted should be straightforward. First, you want the follower with the most up to date data, meaning the smallest replication lag. Second, that follower needs to be healthy and responsive because promoting a struggling node that gives you another failure is not good. And third, in a network split scenario, the new leader should be in the majority partition, meaning the side that can still communicate with more than half the nodes. That last point should be critical because if you elect a leader on the minority side of a partition, you can end up with two leaders accepting writes simultaneously, and that leads to data divergence, which should be extremely difficult to recover from. The takeaway here is that failover should never be an afterthought. It needs to be a first class part of your database architecture, tested regularly, and understood by your entire engineering team. So, we have just covered how failover detection and leader elections work. But there's a harder question we need to address. What happens to the data that the old leader had but had not yet replicated to the followers before it crashed? Let me walk you through a concrete scenario. Say the leader has processed transactions A, B, and C, but because replication is asynchronous, this follower has only received the transactions A and B. There is a lag and transaction C has not been replicated yet. Now the leader crashes. Follower gets promoted to the new leader. Transaction C is essentially gone. It was acknowledged to the client. It was committed on the old leader, but it was never made to another node. So that data essentially from transaction C is lost. This should be one of the most important trade-offs in distributed systems, and there are three mitigation strategies you can choose from. The first is synchronous replication. With synchronous replication, the leader does not acknowledge a write until at least one of the follower has confirmed it received the data. Data loss should be zero in this case, but you pay for it with higher latency on every write and lower availability because if the synchronous follower is down, your writes stall. The second is semi-synchronous replication. Here, one follower is synchronous and the rest are asynchronous. Data loss should be minimal because at least one follower always has the latest data, and the availability impact should be moderate. The third is fully asynchronous replication. This gives you the best availability and lowest latency, but data loss should be possible during failover. Most production databases default to asynchronous replication because the performance and availability benefits outweigh the small risk of data loss during a rare failover event. Now, here's where it actually gets really interesting from application perspective. When a failover happens, your application needs to handle it gracefully. A typical pattern should be catch the connection error, wait briefly, and refresh the database connection to discover the new leader and retry the write. But notice the subtle problem here. If the original write actually succeeded on the old leader before it crashed, but the acknowledgement never made it back to the client, now you are actually trying with that same write on the new leader. You could end up with duplicate data. This is why every write operation in a distributed system should be idempotent. Idempotent means that executing the same operation multiple times produces the same result as executing as once. If your insert operation uses a client-generated unique ID, retrying it will either succeed because the data was truly lost, or fail gracefully with a duplicate key error because the data actually did make it through replication before the crash. So the key insight here is that failover should be messy by nature. You cannot make it clean, but you can make your application resilient to the messiness by designing for idempotency and building retry logic that handles duplicates gracefully. Now let us shift gears from replication mechanics to something more fundamental. Let us talk about consistency models, specifically the difference between strong consistency and eventual consistency. This should be one of the most important concepts in distributed systems design because the consistency model you choose affects everything, from your user experience to your system architecture to your operational costs. Strong consistency means that after a write completes, every subsequent read from any node in the system should return the write, no exceptions. If you write the value of x as let's say 5 and that write is acknowledged, then any read of the variable or a value x from that moment forward should return 5. It does not matter which replica you read them from, it does not matter how many milliseconds later you read. The system guarantees that once a write is committed, it is visible everywhere immediately. This should feel intuitive because it is how a single database on a single machine behaves. The challenge in maintaining this guarantee when your data is spread across multiple nodes. Now, eventual consistency means something totally different. After a write completes, reads might still return the old value for a small amount of time. If you write the value of let's say x as 5 and then immediately read x, you might get an older value, let's say 3. Or you might even get 5. It depends totally on whether the replica you are reading from has received the update yet. But the guarantee is that eventually, given enough time with no new rewrites, all replicas will converge and every read will return the value 5. Now that word, which is eventually, should be doing a lot of heavy lifting in that definition. In practice, the word eventually essentially typically means that somewhere between a few milliseconds and a few seconds. It does not mean minutes or hours. Most modern distributed databases with asynchronous replication converge within 10 to 100 milliseconds under normal conditions, but during network partitions or high load, that window can stretch. The key insight here is that strong and eventual consistency should not be thought of as good versus bad. They should be thought of as different tools for different problems. Strong consistency gives you simplicity at the application layer because you never have to worry about stale data, but you pay for it with higher latency and lower availability. Eventual consistency gives you speed and resilience but pushes complexity into your application code to handle the possibility of stale reads. Choosing between them should always be driven by what your users and your business actually need, not by which one you feel more technically correct. So when should you use strong consistency and when should you use eventual consistency? Let us go through concrete examples because this decision should always be driven by the business domain, not by a technical preference. Strong consistency should be used when incorrect data can cost you money or customer trust. The first example is bank account balances. If a user has $500 in their account and they make a $400 withdrawal, every subsequent read of that balance needs to reflect that withdrawal immediately. If a stale read shows $500 and allow another $400 withdrawal, you have just given away $300 that you do not have. The second is inventory counts during purchasing. If you have one item left and two people are trying to buy it, you cannot let both succeed because of a stale count. The third is user authentication. If an admin revokes someone's access, that revocation needs to take effect immediately, not eventually. And the fourth is payment processing. As you can see, there are more examples like, let's say, booking reservation systems where double booking is unacceptable as well. So eventual consistency should be used when slight staleness has no meaningful business impact. The first example is social media feeds. If your feed is 2 seconds behind, nobody notices. The second is like counts. So like count, whether let's say a post shows 10,442 likes or 10,044 likes, makes no practical difference. The third is view counts, and the fourth is recommendation systems. These are things like, the fifth is the analytic dashboard where data is typically aggregated over time windows anyways. So now this maps directly to the cap theorem trade-off. When a network partition happens and in any distributed system it will happen eventually. So you would have to choose. You either choose consistency, which means you refuse writes until the partition heals, So the system becomes more temporarily unavailable, but never returns the wrong data. Or you choose availability, which means you continue accepting writes on both sides of the partition and reconcile the differences later so that the system stays up but might temporarily return stale data. Most production systems choose availability with eventual consistency because for most workloads, a few seconds of staleness is far more acceptable than minutes of downtime. And this is the production reality of that trade off. Strong consistency gives you higher latency because the system has to coordinate across nodes before acknowledging a write, and it gives you lower availability because if enough nodes are unreachable, the system stops accepting writes. Eventual consistency gives you lower latency and higher availability, but you have to design your application to handle the possibility of stale reads. The right choice should always be based on what the business requires, not on which approach you feel that is more technically elegant to you. Because both approaches are correct in their own ways and it totally depends on your business requirement. Okay, so we have established that most production systems use eventual consistency. But that raises a pretty important practical question. If your reads can be stale, how do you manage the staleness so that it does not cause problems for users? The answer is that you should design for acceptable staleness explicitly rather than just hoping for the best. Let us look at the two strategies here on the slide. Strategy 1 should be time bounded staleness. The idea here is simple but pretty powerful. You define an explicit staleness window and you only serve cache data if it falls within the window. In this example, the getUser function checks the cache first. If there is a cache entry and its timestamp is less than 5 seconds old, it returns the cache data. If the cache entry is older than 5 seconds, or if there is no cache entry at all, it goes to the database, fetches fresh data, stores it in the cache with the current timestamp, and returns it. Why should this be a strong approach? Now let's think about that part. Because you're making a deliberate engineering decision about how much staleness is acceptable. You are not leaving it to chance. For a user profile, 5 seconds of staleness should be completely fine. For a stock price, you might set that window to 1 second or even lower. For a production catalog might be let's say 60 seconds. The key is that the staleness window should be a conscious choice based on what the data is and how your users interact with it. Now, strategy 2 should be version based reads. This one takes a different angle. Instead of tracking time, the client tracks a version number. When the client writes data, it gets back the new version number. On subsequent reads, the client passes in that version as the minimum acceptable version. If the replica returns data with a version lower than what the client expects, the system falls back to reading from the leader to get the latest version. This should be particularly useful in scenarios where a specific user just made a change and needs to see their own update, but you still want other users to be able to read from replicas. It is essentially another way to achieve read your writes consistency, but framed through the lens of versioning rather than the timestamps. Now let's look at two more strategies for managing stale reads. Strategy 3 should be casual consistency. This is the most sophisticated approach. The idea is that you track dependencies between operations. When you perform a write, the database returns a token that represents that write in the replication stream. Then when you perform a subsequent read, you pass that token along and the database waits until the replica has processed at least up to that point before returning results. Why should this be powerful? Because it gives you consistency guarantees exactly where you need them between casually related operations without requiring global strong consistency. If user A updates their name and then immediately reads their profile, the system ensures that they see the updated name. But user B reading from user A profile at the same time can still hit any replica, even one that has not received the update yet. You get strong consistency for the operations that have a casual relationship and eventual consistency everywhere else. Strategy 4 should be read repair. This is the most pragmatic approach. When a read detects that the data is stale, it does not block the response. Instead, it returns the stale data immediately and triggers an asynchronous refresh in the background. The next time someone reads that same data, the cache will have been updated. This should be excellent for scenarios where returning something fast is more important than returning something perfectly fresh. The user gets the response in 1 millisecond instead of waiting 50 milliseconds for a database query. and by that time they make their next request, the data will likely refresh. The key insight across all four of these strategies is that most users tolerate 1 to 5 seconds of staleness without even noticing. You should design for that explicitly, choosing the right stillness window and the right strategy for each type of data rather than trying to fight for strong consistency everywhere. Fighting for strong consistency everywhere is expensive, fragile, and usually not required for every business scenario. Okay, now let us talk about what happens when things go wrong in distributed systems. Specifically, let us talk about the problem of distributed transactions. In a monolithic system with a single database, transactions are straightforward. You start a transaction, do your work, and either commit or roll back. The database handles that atomicity for you. But in microservices architecture, a single business operation might span multiple services, and each microservice will have its own database. For example, placing an order might involve the order service, the inventory service, the payment service, and the shipping service. Now, here's the problem. What happens if the payment succeeds but the inventory reservation fails? You have already charged the customer's credit card, but you do not have the item in the stock. You cannot just roll back because there is no single database transaction wrapping all of these operations. Each service committed its own transaction independently. The solution should be what is called a saga pattern. A saga is a sequence of local transactions where each step has a corresponding compensating action that undoes it. So the flow should be something like this. First, you create the order, then reserve the inventory, then charge the payment, then schedule the shipping. If everything succeeds, the order is complete. However, if any of the step fails, you execute the compensating actions for all the steps that has already been succeeded, but in reverse order. If the shipping step fails, you refund the payment and release the inventory reservation. If the payment step fails, you just release the inventory reservation. Each compensating action should undo the effect of its corresponding step. This is a fundamentally different model from database transactions. Instead of preventing inconsistency by locking everything, you accept that temporary inconsistency will happen and you have a well-defined process to correct it. The system might be in an inconsistent state for a few seconds while compensating actions execute, but it will converge to a correct state. Now let us look at how a saga should be implemented in code. The order saga class has an execute method that takes an order and runs through the steps sequentially. Step 1 is reserving the inventory. Step 2 is charging the payment. Step 3 is scheduling the shipping. If all three succeed, the saga returns a success result. Now the interesting part is the error handling. If a payment error is raised during step 2, the saga needs to be compensating step 1 by releasing the inventory reservation. If a shipping error is raised during step 3, the saga needs to compensate both step 2 and step 1, so it refunds the payment and releases the inventory reservation. Notice the order matters. You compensate in reverse, undoing the most recent successful step first. There are 4 key properties that every saga should have. The first is that every step should be idempotent. Running the same step twice should produce the same result because in failure scenario, you might end up retrying. The second is that every step should be compensatable, which means every step action can be undone. If you cannot undo a step, it should not be in a saga. The third is that the steps should be executed in order because later steps might depend on earlier ones. And the fourth is that every failure should trigger the appropriate compensation chain. The takeaway here is that the saga pattern should be your go-to approach for maintaining data consistency across service boundaries. It is not as clean as a database transaction, but it is the practical solution for distributed systems. And once you internalize the pattern, it becomes a natural way to think about multi-service business operations. Move into a topic that catches a lot of teams by surprise in production, which is hot partitions. The setup is pretty straightforward. You have sharded your database, let us say by user ID modulo by 1000. Under normal conditions, this should distribute traffic evenly. Each shard has roughly 2 million users and handles, let's say, about 1000 requests per second. Everything looks balanced and healthy. But then a celebrity with 100 million followers posts something, and that celebrity happens to be on the shard 3 number, let's say 345. Now, every one of those 100 million followers want to view that celebrity's feed, and all of those read requests hit that shard 345. Suddenly, shard 345 is getting 500, let's say 500,000 requests per second, while every other shard is still sitting at 1000 requests per second. Shard 345 is now completely overwhelmed, and the users assigned to that shard experience massive latency spikes or outright failures, even if they had nothing to do with the celebrity. This is what it's called the hot partition problem. Your hashing function distributes the data evenly but cannot distribute the traffic evenly because the traffic is not uniform. It follows power law distributions where a tiny percentage of keys attract a disproportionate amount of activity. What are the common causes of hot partitions? The first is celebrity users, like a major public figure posting content that millions of people view simultaneously. The second is viral content, where a single post gets shared millions of times. The third is time-based keys, where all the writes go to the partition for today's date. The fourth is sequential IDs, where auto-increment keys create hot tail because all new writes go to the highest number partition. And the fifth is event-driven spikes, like let's say Black Friday sales or live sport events. The symptom should be recognizable. You will see one database shard at 100% CPU, while others will sit at 10%. You will see latency spikes for a subset of users, specifically the ones whose data happens to live on the overloaded shard. You will see connection pool exhaustion on that one shard, and you will see replication lag on that shard only, because the leader is so busy handling reads that it falls behind on replicating it to its followers. The key insight here is that uniform hashing does not prevent hot partitions. Your hash function can perfectly distribute 2 billion user IDs across 1000 shards, but if one of those user IDs attract 50% of all traffic, you still have a massive imbalance. The problem is not the data distribution, the problem is the traffic distribution, and those are two fundamentally different things. So how do you handle hot partitions in production? Let us look at two solutions on this slide. Solution 1 should be caching hot data. The idea is to identify which users or keys are hot and serve their data from a dedicated cache rather than hitting the database directly. In this code example, the getCelebrityPost function checks whether the user is a celebrity. If they are, it looks in a dedicated celebrity cache with a higher TTL. If the data is in the cache, it returns immediately without touching the database at all. If the data is not in the cache, it queries the database, stores the result in the celebrity cache with a 60-second TTL, and returns. Why should this be effective? Because a single celebrity might generate 500,000 reads per second, but the underlying data only changes a few times per minute. By caching the data for 60 seconds, you absorb 99.99% of the traffic at the caching layer, and the database shard barely feels the load. Solution 2 should be adding read replicas specifically for hot shards. Instead of giving every shard the same number of replicas, you give the hot shard more replicas. Shard 345 might have 5 read replicas, while other shards have 1 or 2. Read traffic gets distributed across these replicas, reducing the load on any single node. This should be a good complementary strategy to caching. The cache handles the extreme burst, and the extra replicas handle the baseline elevated traffic that hot shards experience even outside of the viral moments. Now let us look at two more solutions. Solution 3 should be key salting. The idea is that to take a hot key and distribute it across multiple cache entries by appending a random salt. Instead of a single cache key like a user colon 12345, you create 10 keys, user colon 12345 colon 0 through user colon 12345 colon 9. When reading, you pick a random salt value between 0 and 9 and read from that key. This distributes the read load across 10 different caches, cache nodes, instead of concentrating it on one. The trade-off here is that it should be on the right side. When the underlying data changes, you need to update all 10 salted keys. There is a fan out of 10 writes for every data change, but for data that is read millions of times and written a few times per minute, that trade-off should be extremely favorable. Solution 4 should be separating hot and cold data entirely. You route requests through a check that determines whether the user is a hot user. If they are, the request goes to a dedicated hot data store, which could be a completely separate infrastructure stack optimized for high read throughput. If they are not, the request goes to the regular data store. This should be the most operationally expensive solution because you are maintaining two separate infrastructure paths, but gives you complete isolation. A celebrity going viral will never impact the experience of your regular users because they are on entirely separate infrastructure. Some of the largest social media platforms in the world use exactly this approach for their highest traffic accounts like celebrities. Now let us talk about a specific type of hot partition that is incredibly common and often overlooked, which is time-based partitioning. Imagine you have an events table and you partition it by event date. This seems pretty logical, right? But all events from then for event, let's say from 15 January will go to one partition. All events from January 16 will go to another partition. The problem should be obvious once you think about it. All writes go to today's partition. Yesterday's partition gets 0 writes. Tomorrow's partition gets 0 writes. Today's partition will get, let's say, 1000 writes per second, and you have created a hot partition by design. This is not a hypothetical scenario. I've seen teams deploy this exact schema and then scramble when their write throughput hits a wall because a single partition is handling all the load. The better pattern should be actually to add a random prefix to the partition key. Instead of partitioning purely by date, you partition by a combination of random number between 0 and 99 and the date. When inserting an event, you generate a random partition key value and the event gets distributed across 100 different partitions for each date. So instead of one partition handling across 100,000 writes per second, you have 100 partitions, each handling 1000 writes per second. That is a dramatically more even distribution. Now the trade-off with this random prefix approach should be on the read side. If you want to query all events for a specific date, you cannot just read from a single partition anymore. You need to query all 100 partitions and merge the results. This is called a scatter gather query. The implementation should use parallel execution. You submit a query for each of the 100 partitions simultaneously using a thread pool or async execution. Each query returns a subset of results and you merge them together. The total latency should be roughly equal to the slowest individual partition query, not the sum of all 100, because they execute in parallel. Let us compare the trade-offs across three approaches. The first is partitioning by date only. Write distribution should be hard because everything goes to today. Read complexity should be simple because it's a single partition lookup. This should be fine for low write volume workloads. The second is date plus random prefix. Write distribution should be even across 100 partitions. Read complexity should be higher because of scatter gather. This should be a choice for high write volume workloads. The third is date plus hour. Write distribution should be moderate, spreading across writes across 24 partitions per day. Read complexity should be simple since you will target specific hours. This should be good middle ground for medium write volume. The key insight here is that write heavy time series data needs synthetic partitioning. You should accept the additional read complexity in exchange for write scalability. Trying to optimize for simple reads while ignoring write distribution will eventually become a bottleneck that is painful to fix retroactively. This is one of those topics that every engineer knows is important, but that does not get nearly enough attention in system design discussions. And yet, in production, your backup strategy can be the difference between a 5-minute recovery or a company-ending data loss. There are 4 main types of backups. The first is full backup, which copies the entire database. Recovery speed should be fast because you have everything in one file, but storage cost should be high because you're duplicating the entire dataset every time. The second is incremental backup, which only copies the changes since the last backup. Recovery speed should be medium because you need to restore the full backup and then apply all the incremental backups on top. Storage cost should be low because each incremental backup is much smaller. The third is continuous backup using write-ahead log shipping, often called WAL. This streams every transaction log entry to a backup location in near real time. Recovery speed should be very fast and you can recover to almost at any point in time. Storage cost should be medium. And the fourth is the file system snapshots, which capture the entire state of disk at one point in time. Recovery speed should be very fast and storage cost varies depending on the snapshot technology. A typical backup strategy should combine multiple types. full backups weekly, say let's say on Sunday at 2 a.m., incremental backups daily, and WAL archiving continuously, and a 30-day retention window. Now there are two critical metrics you need to define for your backup strategy. The first is recovery point objective or RPO. This answers the question, how much data can you afford to lose? If your RPO is 1 hour, you need backups for at least 1 hour. If your RPO is 0, it means you cannot lose any data at all. You need synchronous replication plus continuous WAL archiving. The second critical metric is recovery time objective or RTO. This answers a different question. How long can you afford to be down? If your RTO is 4 hours, restoring from backup is perfectly acceptable because even a full restore of a large database can usually complete within that window. But if your RTO is 1 minute, you cannot afford to restore from a backup at all. You need a hot standby with automatic failover that can take over almost instantly. RPO and RTO should be business decisions, not technical ones. Your engineering team does not get to decide how much data loss or downtime is acceptable. The business does. So your job as an engineer is to build the infrastructure that meets those requirements. Now let us talk about where you store your backups. There are 4 key requirements. The first is durability. Your backup should be stored in a different region than your primary database. If your primary is in the US East and your backups are also in US East, a region outage could take out both. The second is cost. Older backups should be moved to cold storage like AWS S3 Glacier, which is significantly cheaper than standard storage. The third is security. Backup should be encrypted at rest. An unencrypted backup is a data breach waiting to happen. And the fourth is compliance. Some industries require you to retain backups for specific periods, sometimes even years. A good rule of thumb is the 3-2-1 rule. You should have 3 copies of your data, that is your primary plus 2 backups. Those copies should be on 2 different storage types like local disk plus cloud object storage, and at least 1 copy should be in an offsite location, meaning a different geographic region. This gives you resilience against hardware failure, software corruption, and region disasters simultaneously. Now here's something that a lot of teams get wrong in production. They set up automated backups, they verify that the backup jobs complete successfully, and then they move on. They never actually test whether they can restore from those backups. So now when you're doing backups, what you should be testing? There are 5 levels of backup testing. The first is backup completion, which you should verify daily through automation. This just confirms that the backup job ran successfully and produced an output file. The second is backup integrity, which should verify weekly. This confirms that the backup file is not corrupted and can be read. The third is partial restore, which you should test monthly. This confirms that you can restore a signal table from the backup. The fourth is full restore, which you should really be doing quarterly. This confirms that you can restore the entire database. And the fifth is point-in-time recovery, which you should also test quarterly. This confirms that you can restore to a specific moment in time, not just the latest backup. Now let me walk you through a full restore drill, how it should look like. This is a quarterly exercise that every production team should be running. Step 1 is to spin up a new empty database instance. Step 2 is to restore the latest full backup to that instance. Step 3 is to apply the WAL logs to bring the database up to the current point in time. Step 4 is to verify data integrity by checking checksums and row counts against the production database. Step 5 is to run your application's test suite against the restored database to make sure queries return the expected results. Step 6 is to measure the total time the restore took and compare it against your RTO. If the restore took 6 hours but your RTO is 4 hours, you have a gap you need to address. And step 7 is to document the results, any issues that you would have encountered during testing. You should also automate as much of this possible, so the verify backup function in this code example actually restores the latest backup to a test environment, then it runs the integrity checks including checksum verification and row count validation, and then it runs the sample queries to confirm the data is queryable, cleans up the test environment, and sends a success alert. The key insight here is that a backup that has not been tested is not a backup actually. It is just a hope, and then you're hoping that it will work somehow in the future. And the thing is, hope is not a strategy. Until you have successfully restored from a backup and verified the data, you do not actually know if your backup system works. One of the most valuable backup capabilities you can actually have, which is point-in-time recovery. Here's a scenario that happens in production more often than anyone you would like to admit. At 2 a.m., your full backup completes successfully. At 9 a.m., normal operations are running. At 9:15 a.m., let's say a developer runs a delete statement without a where clause. At 9:16 a.m., let's say 10 million rows are gone, and by 9:20 a.m., the team will start to notice it. The goal is to restore the database to 9:14 a.m., 1 minute before the destructive query. Without the point-in-time recovery, you would have to restore from the 2 a.m. backup and lose 7 hours of data, everything from 2 a.m. to 9:14 a.m. With point-in-time recovery, you take the 2 a.m. full backup and then replay the write-ahead logs forward in time, applying every transaction that has happened between 2 a.m. and 9:14 a.m. You stop replaying at exactly 9:14 a.m. right before the destructive query. The result is a database that reflects the exact state at 9:14 a.m. with zero data loss. In PostgreSQL, this is done by restoring the base backup using pg-restore and then configuring the recovery target time to extract timestamp you would want to recover to. The database will replay WAL logs up to that point and stop. This should be one of the strongest arguments for WAL archiving. The full backup gives you a starting point, and the WAL logs gives you the ability to move forward to any specific moment in time. Without WAL archiving, you are just stuck aware with whatever your last backup has captured. There are 4 requirements for point-in-time recovery to work. The first is that WAL archiving should be enabled on a database, which is PostgreSQL, meaning setting archive mode to on. The second is continuous WAL shipping, meaning those WAL files should be archived to durable storage like S3 or GCS every minute. The third is regular based backups because you need a full backup as your starting point. And the fourth is that WAL files should be encrypted and retained securely. The trade-off should be straightforward. On the advantage side, you can recover to any point in time, you minimize data loss, and you can undo specific mistakes like accidental delete. On the disadvantage side, you have higher storage costs because WAL files accumulate continuously, longer recovery times because you'll have to replay potentially hours of WAL logs, and additional complexity in configuring the configurations and the monitoring part. The production practice should be to enable WAL archiving on all production databases with no exceptions. Ship WAL files to durable storage every 1 minute, and you should be retaining WAL files for at least 7 days. You should also be testing point-in-time recovery quarterly to make sure it actually works when you need it. Now let us zoom out from individual backup strategies to the bigger picture, disaster recovery planning. This is about planning for the worst case scenarios and having a clear tested process from recovering from them. Let us walk through the spectrum of disaster scenarios. The first is a single server failure. One replica goes down, the impact should be limited and recovery should be automatic failover to another replica. The second is a rack failure. Multiple servers in the same physical rack go down simultaneously. Recovery should be failover to servers on a different rack. The third is a data center failure. An entire region goes down due to, let's say, a power outage, network issue, or a natural disaster. Recovery should be failover to a different geographic region. The fourth is data corruption. Your data becomes unreadable, possibly due to software bug or storage failure. Recovery should be restoring from a known good backup. And the fifth is ransomware. Let's say a bad actor or an attacker encrypts your data and demands payment. Recovery should be restoring from an offline backup that the attacker would not have reached. Notice that each scenario actually requires a different recovery approach. Automatic failover handles hardware failures, cross-regional replication handles regional outages, and offline air-gapped backups handle ransomware. A complete disaster recovery strategy should cover all of these. For multi-region disaster recovery, a typical setup should have your primary database in one region, say US East, with asynchronous replication to the disaster recovery replica in a different region, let's say US West. Your backup should also be stored in both regions with cross-region copy, ensuring that a backup exists in the secondary region even if the primary region is completely lost. Now let me walk through what a disaster recovery runbook should look like for a data center failure. There should be a documented practice procedure that your team can execute under pressure. Phase 1 is detection, which should take, let's say, 0 to 5 minutes. Your monitoring system alerts on region failure. The on-call engineer then will acknowledge the alert. Phase 2 is assessment, which should take roughly 5 to 15 minutes. You confirm the scope of the failure, you estimate when the primary region might come back, and then you make the critical decision. Do you wait for the primary to recover or do you fail over to the secondary region? And this decision should be based on your RTO. If your RTO is 30 minutes and the primary region is estimated to be down for 2 hours, then you fail over to the secondary region. Phase 3 is failover, which should take roughly 15 to 30 minutes. You promote the disaster recovery replica to primary, you update the DNS and load balancer configurations to point to the new primary, and you verify that the application can connect to the new database. Phase 4 is verification, which should take roughly 30 to 45 minutes. You run smoke tests against the failover environment, you monitor error rates to make sure they return to normal, and you confirm data consistency. Phase 5 is communication, which should be ongoing throughout. You update the status page, you notify customers, and you send internal updates to stakeholders. Now, having the runbook is not enough. You should test it. There are 3 levels of testing. The first is tabletop exercises, which you should be doing monthly. This is where the team walks through the runbook verbally without actually executing it. The second is partial failover, which you should be doing quarterly. This is where you fail over non-critical services to validate the process. And third is full failover, which you should be doing annually. This is where you execute a complete region failover. Full failover tests are stressful and disruptive, but they are the only way to know for certain that a disaster recovery plan actually works. Makes with the data in production. These are the patterns I have seen that have caused outages and incidents, and all of them are pretty avoidable if you follow the right measures. Anti-pattern 1 should be coupling schema changes with application deployments. The bad approach is to deploy new code that expects a new column and then run the migration to add that column. During the 30 seconds or so between the code deployment and the migration completing, your application is trying to read or write a column that does not exist. You get errors, failed requests, and unhappy users. The good approach should be to run the migration first, add the column, wait for that change to replicate to all followers, and then deploy the code that uses the new column. By the time the code starts running, the column already exists everywhere, 0 errors. Anti-pattern 2 should be large transactions. Wrapping a million row update in a single transaction is pretty dangerous. The bad approach runs a begin, updates all 1 million rows, and then commits. That transaction holds logs for the entire duration, blocks other writes, consumes enormous amount of memory for the transaction log, and if it fails partway through, the rollback can take even longer than the original update. The good approach should be to break it into smaller batches. Update rows 1 through 10,000, commit. Update rows 10,001 through the 20,000, commit, and so on. Each batch is small enough that it completes quickly, holds log briefly, and if one batch fails, you only need to retry that batch, not the entire million row update. Anti-pattern 3 should be ignoring the replication lag. The bad approach writes data and then immediately reads it back from the replica, assuming their data will be there. But if the replica has even 100 milliseconds of lag, the data might not even have arrived yet, and the read returns nothing or stale data. The good approach should be to read from the leader after a write if you need to see the data you have just written. We covered this earlier with the read your writes consistency, but it's worth repeating here because the mistake is very common in practice. Anti-pattern 4 should be not testing backups. The state that says we have backups is not the same as we can restore from backups. As we discussed, a lot of the companies that test their backups find failures. If you have not tested your restore process, you do not actually have a working backup system. Anti-pattern 5 should be unbounded queries. The bad approach runs a select star from events with no where clause and no limit. If that table has a billion rows, you have just tried to load a billion rows into the memory. Your database server will either run out of memory and crash, or it will consume so much resources that every other query slows to a crawl. The good approach should be always to include a where clause to filter results and always include a limit to cap the result set. A query like select star from events where created at the greater is now -1 day limit 1000 is bounded and predictable. It will never return more than 1000 rows regardless of how large the table grows. Let us take a moment to consolidate the key takeaways from everything we have covered about data in production. For schema evolution, the core principle should be separate schema changes from code deployment, so you never have a window where the code expects something the database does not have yet. Use the expand contract pattern for renames, where you add the new column, migrate the data, update the code, and then remove the old column. Always add new columns as an nullable and backfill data afterward. And only remove the columns after you have confirmed that the code no longer references them. For migrations, the principle should be batch large updates into chunks of 1000 to 10,000 rows per transaction. Use online schema change tools for large tables so you do not lock the entire table during the migration. Monitor the replication lag during the migrations because the large migration on the leader can cause followers to fall behind. And always have a rollback plan before you start. For replication, the principle should be understand the trade-offs between the synchronous and asynchronous replication and choose based on your durability requirements. Implement the read your writes consistency where users need to see their own changes immediately. Plan for failover because it will happen, and test failover regularly, not just when something goes wrong. For consistency, the principle should be you should be using strong consistency for financial and transactional data where incorrect results have real consequences. You should be using eventual consistency for high skill read workloads where brief staleness is allowed. Implement the compensating transactions using the Saga pattern for operations that span multiple microservices, and design for acceptable staleness explicitly rather than trying to achieve zero staleness everywhere. For hot partitions, the principle should be monitor for uneven shard distribution so you catch hot partitions before they cause outages. Cache the hot data aggressively because it is the fastest way to reduce load on an overloaded shard. Use key salting for write-heavy keys to distribute the load across multiple partitions. And add read replicas specifically for hot shards rather than giving every shard the same number of replicas. For backups, the principle should be follow the 3-2-1 rule, which is 3 copies, 2 storage types, 1 offsite location. Test recovery regularly with a quarterly full restore drill. Enable point-in-time recovery on all production databases, and document and practice your disaster recovery runbooks so your team can execute them under pressure. And with that, we have covered all of the major topics in the data and production section. Coming up next, we are going to dive into section 4, which covers topics like caching, queues, and async workflows. These should be the building blocks that take a system from handling thousands of requests per second to handling millions of requests per second. Section 4. This section covers the building blocks of scalable systems, which is caching, CDNs, message queues, background workers, dead letter queues, and eventual consistency patterns. The flow of this section should be logical. We start with caching, which is the most immediate way to reduce latency and database load. Then you move to CDNs, which extend caching to the edge for static content. Then you move to message queues, which let you decouple the producers from consumers. Then we will cover the background workers, which process slow operations asynchronously so your user-facing requests stay fast. And finally, we'll cover dead letter queues, which gives you a safety net for handling failures in async workflows. Let me explain why this section matters by walking through what each component solves. Caching should reduce the latency and reduce the database load. CDNs should be able to serve static content from edge locations near your users so that it's much more faster. Message queues should decouple producers and consumers so they can scale independently. Background workers should process slow operations asynchronously. And dead letter queues should handle failures gracefully so failed messages do not get silently dropped. Here's the key insight that separates interview level knowledge from production level knowledge. In an interview, when you draw a box labeled cache on your architecture diagram, then you just kind of move on. However, in production, that box needs a TTL strategy, an invalidation strategy, a plan for cache failures, and a cache warming process. This section is about turning those simple block boxes into a real production-ready architecture. This caching matters so much. Without a cache, every request hits your database. If a user requests a profile, the request goes to application server. The application server queries the database, which talks about 50 milliseconds, and the result goes back to the user. If 1000 user requests the same profile, that is 1000 database queries, which is 50,000 milliseconds of database time. Your database is doing the same work over and over again for the same data. With the cache, the first request still hits the database, but the result gets stored in the cache. The next 999 requests hit the cache instead, which takes about 1 millisecond per lookup. So 1000 requests cost you 1 database query plus 999 cache hits, totaling about 1 second of combined processing time. That will be a 50x reduction in database load. Now let us do the math on cache hit rates. If you achieve a 95% cache hit rate, then 95% of your requests are served in 1 millisecond from the cache, and only 5% of the requests take 50 milliseconds because they hit the database. Your average latency should be 0.95 times 1 plus 0.05 times 50, which equals to 3.45 milliseconds. If you compare that to 50 milliseconds without any caching, that is roughly a 15x improvement in your average response time, and your database is handling 20 times fewer queries. This is why caching should be one of the first things you add when optimizing a system. The impact on both the latency and database load is dramatic, and the implementation complexity is relatively low compared to other performance optimizations. Now, caching is not a single thing. In a production system, there should be multiple layers of caching, each serving a different purpose and operating at a different level of the request path. The caching hierarchy from the closest to the user to the furthest should be browser cache, CDN cache, application cache, and database cache. Let us walk through each layer. The first is the browser cache, which lives on the client device. Latency should be effectively 0 milliseconds because there is no network request at all. It caches static assets like images, CSS, and JavaScript, as well as API responses. The second is the CDN cache, which lives on the edge servers distributed around the world. Latency ideally should be 10 to 15 milliseconds depending on how far the nearest edge server is. It caches the images, CSS, JavaScript, and sometimes API responses as well. The third is the application cache, which is typically Redis or Memcache running alongside your application servers. Latency should be 1 to 5 milliseconds. It caches session data, computer results, and frequently access database records. And the fourth is the database cache, which is a memory buffer pool built into the database engine itself. Latency should be 0.1 to 1 millisecond. It caches recent query results and index data in the memory. When a request comes in, it should check each cache layer in order. It should be checking the browser cache first. If that misses, you should be checking the CDN cache. If that misses, check the application cache in Redis. And if that misses, then it should check the database's internal cache. And if that misses, gets missed, then it reads from the disk for the database. And on the way back, each layer stores the results so that the next request can be served faster. The takeaway here is that effective caching should be a layered strategy, not a single cache. Each layer reduces the load on the layer below it, and together they create a system where the database only handles a very small fraction of the actual results. Now let's look at the most common caching pattern in production systems, which is the cache aside pattern, sometimes called lazy loading. The flow should be pretty straightforward. When the application needs data, it first checks the cache. If the data is in the cache, that is a cache hit, and it returns the cache data immediately. If the data is not in the cache, that is a cache miss, and the application queries the database, stores the results in the cache with a TTL of, let's say, 3600 seconds, which is 1 hour, and then returns the data. In the code example here, the getUser function builds a cache key like user colon 12345. It checks Redis for that key and returns immediately if it finds a value. If there is a cache miss, it queries the database, stores the results in the cache, and returns the fresh data. There are 4 important characteristics of cache aside pattern. The first is the read path. The application always checks the cache first, then falls back to the database. The second is the write path. Writes go directly to the database and they do not touch the cache. The third is cache population. The cache is populated lazily, meaning only when a cache miss occurs. Data that is never requested is never cached. And the fourth is consistency. The pattern is eventually consistent because after a database, the cache still holds the old value until the TTL expires. This should be a default caching pattern unless you have a specific reason to use something else. It is simple to implement, it is well understood, and it naturally caches only the data that is actually being accessed. Now let us look at alternative caching patterns that move more responsibility into the cache layer itself. The first is read-through cache. In this pattern, the application does not talk to the database at all. It only talks to the cache. When the application requests data and the cache does not have it, the cache itself is responsible for loading the data from the database. The application code becomes much more simpler because it just calls the cache.get and the cache handles everything behind the scenes. The difference from cache side should be subtle but important. In cache side, the application manages both the cache and the database. In read-through approach, the application only manages the cache and the cache manages the database. This pushes the complexity of cache population out of your application code and into the cache layer. The second is the write-through cache. In this pattern, writes also go through the cache. When the application updates data, it writes to the cache and the cache is responsible for processing that write to the database. The write is not acknowledged to the application until both the cache and the database have been updated. This gives you strong consistency because the cache always has the latest data, but it increases the write latency because every write now has to update two places synchronously. There is a third variant called write behind or write behind cache. In this pattern, the application writes to the cache immediately acknowledges the write back to the application, and then the cache processes the data to the database asynchronously in the background, often batching multiple writes together. Write latency should be very low because the application only waits for the cache write, not the database. But the trade-off is that so that you can lose data if the cache crashes before processing to the database. The writes that were in the cache but not yet flushed to the database would be lost. Now let's compare all the four patterns together. Cache aside has low read latency on hits, low write latency, eventual consistency, and low complexity. Read through has low read latency on hits, low write latency, eventual consistency, and medium complexity. Write through approach has low read latency, higher write latency because both cache and database are updated synchronously, strong consistency, and medium complexity. The write behind approach has low read latency, very low write latency because database writes are synchronous, eventual consistency, and high complexity. The production recommendation should be to use cache aside as your default because it is the simplest and most widely understood pattern. You should be using write through approach for critical data where you need the cache to always reflect the latest database state, and you should avoid the write behind approach unless you can genuinely tolerate data loss because the risk of losing unflushed writes is real. Now let us talk about TTL, which stands for time to live. This is how long a cache entry exists before it expires and gets erected. Without TTL, you have three problems. The cache grows unbounded until you run out of memory. Stale data is never refreshed, and eventually the cache consumes all available memory and the process crashes. With TTL, cache expires, entries actually expire automatically, staleness is bounded to the TTL duration, and memory gets recycled as all entries are erected. The right TTL actually should depend entirely on the type of data, so let me walk you through the guidelines. For user profiles, a TTL of 1 hour should be appropriate because profiles change infrequently. For user sessions, 15 minutes should be appropriate because this is primarily a security requirement to limit the session duration. For feed content, 5 minutes should balance freshness with database load. For product catalogs, 1 hour should work because catalogs typically update on a daily basis. For stock prices, 1 second should be the maximum because this data needs to be near real time. And for the static assets with version URLs, 1 year should be fine because the URL changes when the content changes, so the old cache entry will simply never be requested again. Now let us look at the trade-offs of short versus long TTLs. A short TTL of let's say 1 minute gives you more fresh data, but it means higher database load because the cache is constantly expiring and repopulating. You also get a lower cache hit rate and more consistent data. A long TTL of let's say 1 hour gives you more stale data, but it significantly reduces the database load. You get a higher cache hit rate, but the data might be up to 1 hour behind. Now here is a more sophisticated approach, dynamic TTL. Instead of using a fixed TTL for all entries of the same type, you can vary the TTL based on how popular the item is. In this code example, the getTTL function has base TTLs for each data type, 3600 seconds for user profiles, 300 seconds for feeds, and 60 seconds for trending content. But if the item has popularity score above 1000, it doubles the TTL. Why? Because popular items get accessed much more frequently, so each cache hit saves more database load, and the benefit of caching them longer outweighs the cost of slightly staler data. The production practice should be to start with longer TTLs and reduce them only if you receive staleness complaints or observe the consistency problems. It is much easier to shorten a TTL than to deal with the database load spike that comes from making TTLs too short. And you should also monitor your cache hit rate continuously. If your hit rate is below 90%, your TTLs might be too short or your cache size might be too small. There is a famous code in computer science, which is that there are only two hard things in computer science: cache invalidation and naming things. And having spent years dealing with production caching systems, I can confirm that caching invalidation actually is a very hard problem to solve. Here's why invalidation is super hard. A user updates their profile, the database gets updated immediately, but the cache still has the older version of the profile. Other users who request that profile get the stale pre-update version from the cache until the TTL expires. Now, depending on your TTL, that could be minutes or hours of serving incorrect data. There are three main invalidation strategies. The first is TTL expiration, where you simply wait for the cache entry to expire naturally. Consistency should be eventual, bounded by the TTL. Complexity should be low because you do not have to do anything special. Now the second is explicit delete, where you actually actively delete the cache entry when the underlying data changes. Here, consistency should be strong because the next read will miss the cache and fetch fresh data. Complexity should be medium because you need to remember to invalidate the cache on every write path. And the third here is publish subscribe, where you broadcast an invalidation event whenever the data changes, and all cache instances that subscribe to that event invalidate their copies. Consistency should be strong. Complexity should be high because you need an event bus and subscriber infrastructure for this approach. Now let us look at each strategy in detail with code. Strategy 1 is TTL expiration. This is a passive approach. When you update a user in the database, you do nothing to the cache. You just let it expire based on its TTL. This should be the simplest approach, and it works well for data where brief staleness is acceptable. But it means that the cache could serve stale data for up to the full TTL duration. Strategy 2 is explicit delete. When you update a user in the database, you immediately delete the corresponding cache key. The next time someone reads the user data, the cache will miss, and the application will query the data for the fresh database for the fresh data, and then the cache will be repopulated with the updated version. This gives you strong consistency with moderate complexity. Strategy 3 is explicit update. Instead of deleting the cache entry, you update them with the new data immediately after the database write. The cache always has the latest data, but there is a subtle risk here. What happens if the database write succeeds, but the cache update fails? Now your cache has old data, and there is no TTL-based mechanism to refresh it. You need error handling around the cache update, which adds complexity. Strategy 4 is publish subscriber invalidation. When service A updates user, it publishes a user.updated event to an event bus. A cache subscriber listens for that event and invalidates the cache entry. Other subscribers can also react to the same event. This should be the right approach when you have multiple services that cache the same data. If the user service, the recommendation service, and the notification service all cache user profiles, you cannot rely on the user service to invalidate all of their caches. Instead, each service subscribes to the user.updated event and invalidates its own cache when it receives the event. So when should you use each strategy? Use the TTL only when the staleness is acceptable, like for analytics data or recommendation feeds. Use the explicit delete when a single service owns the data and needs to ensure freshness after writes. And use the pub/sub approach when multiple service caches the same data and all needs to be invalidated simultaneously. The takeaway is that there is no perfect cache invalidation strategy. Each one makes trade-offs between consistency, complexity, and performance. Your job should be to choose the strategy that matches your specific consistency requirements for for each type of data. Now let us talk about a failure mode that can turn your cache from performance optimization into a cause of outages, which is the thundering herd problem. Now here's the scenario. You have a popular item cache with a TTL of 60 seconds. 10,000 users are currently viewing that item. At the 60-second mark, the cache entry expires. All 10,000 users, let's say they make a request at roughly the same time. All 10,000 requests check the cache and see that it is empty, and all 10,000 requests hit the database simultaneously. The database gets overrun by 10,000 concurrent queries for the exact same data, latency spikes, and potentially crashes. This happens because of three factors. The first is popular content, meaning many users are waiting for the same data. The second is a fixed TTL, meaning all copies expire at exactly the same time. And the third is no coordination, meaning each request independently decides to query the database without knowing that other thousands of others are requests are actually doing the same thing. This is not a theoretical problem. It happens in the production, particularly during high traffic events. And the irony is that the item causing the problem is your most popular item, which means that the thundering herd affects the largest number of users simultaneously. Now let us look at two solutions for the thundering herd problem. Solution 1 should be jitter TTL. Instead of setting a fixed TTL of 3600 seconds for every cache entry, you add a random jitter. The TTL becomes 3600 plus a random value between 0 and 10% of the base TTL. So different cache entries for the same data across different application servers will expire at a slightly different times. Instead of 10,000 requests all hitting the database at the exact same moment, the cache misses get spread out over a window of few minutes. This should be the lowest complexity solution and reduces the severity of the thundering herd without eliminating it entirely. Solution 2 should be lock and single fetch. When the cache misses, the first request tries to acquire a distributed lock. If it gets the lock, it fetches the data from the database, populates the cache, and releases the lock. All other requests that arrive during that window see that lock is held, wait briefly, and then retry. When they retry, the cache has been populated by the first request, so then they get a cache hit. In the code example over here, the lock is implemented using Redis set nx command, which only sets the key if it does not already exist. The lock automatically expires after 5 seconds as a safety measure. If the first request crashes or takes too long, the lock expires and other requests can take over. This approach should eliminate the thundering herd entirely. Only one request ever hits the database, regardless of how many concurrent requests arrive. The trade-off is slightly higher latency for the requests that have to wait for the lock holder to complete. Solution 3 should be stale while revalidate. This is the most elegant approach. When the cache entry is fresh, meaning its age is less than the TTL, you return it immediately. When the cache entry is stale, but still within an acceptable staleness window, you return the stale data immediately to the user and trigger an asynchronous background refresh. The user gets a fast response, and by the time the next request comes in, the cache will have been refreshed. In the code example, the base TTL is 3600 seconds and the stale TTL is an additional 300 seconds. So for the first 3600 seconds, the data is considered fresh. Between 3600 and 3900 seconds, the data is considered stale, but still acceptable. During this window, the function returns the stale data immediately and queues a background job to refresh it. Beyond 3900 seconds, the data is too stale and the function fetches fresh data synchronously. Now let us compare all three solutions. Jitter TTL has the same latency as no solution, the same freshness, and low complexity. It should be your starting point. Lock and single fetch has high latency because some requests wait for the lock holder, but data should be perfectly fresh and the complexity is medium. Stale while revalidate has low latency because stale data is returned immediately. Data should be slightly stale during the revalidation window, and the complexity for this approach is medium. In practice, the best approach is often to combine jitter TTL with stale while revalidate. The jitter spreads out the expirations, and stale while revalidate approach ensures that even when an expiration does happen, no user experiences a slow response. Now let us talk about a caching challenge that is closely related to the hot partition problem we discussed earlier, the hot key problem. Here's the scenario. You have a trending post with key trending underscore post colon 123 that is receiving 100,000 requests per second, but a single Redis server can handle a maximum of 50,000 operations per second. You have more traffic for a single key than a single Redis instance can handle. The result is Redis become overloaded and latency spikes for everyone, not just for users requesting the trending post. This happens in several predictable scenarios. The first is viral content, like a tweet from a celebrity. The second is flash sales, like a product featured on the homepage. The third is breaking news, where millions of people are refreshing for updates. And the fourth is live sport events, where everyone wants their current score. The difference between the hot partition problem and the hot key problem should be clear. Hot partitions are about uneven distribution of data across database shards. Hot keys are about a single cache key receiving more traffic than a single cache node can handle. The solutions are related but distinct. Solution 1 should be local caching. Instead of sending every request to Redis over the network, you cache hot keys in the application server's own memory. The get with local cache function checks the local memory cache first. If the key is in the local cache and it has not expired, it returns immediately with zero network overhead. If the key is not in the local cache, it checks Redis as usual. And if the key is identified as a hotkey, it stores a copy in the local cache with a very short TTL of 1 second. So why should the TTL be so short? Because local caches do not get invalidated when the underlying data changes in Redis. If you set a 60-second local TTL, your application servers could be serving data that is up to 60 seconds stale even after the Redis cache has been updated. A 1 second local TTL limits the staleness window while still dramatically reducing Redis load. If you have 100 application servers and each one caches locally for 1 second, you reduce Redis traffic for 100,000 requests per second to roughly 100 requests per second. That is a 1000x reduction. Solution 2 should be key replication. Instead of storing the data under a single cache key, you replicate it across multiple keys with a numerical suffix. When writing, you set 10 keys, trending underscore post colon 123 colon 0, through trending underscore post colon 123 colon 9. When reading, you randomly pick one of those 10 keys. This distributes the read load across multiple cache keys, and in a Redis cluster, those keys will likely hash to different nodes. So instead of a single Redis node handling 100,000 requests per second, you have 10 nodes each handling 10,000 requests per second. This is well within each node's capacity. Solution 3 should be read replicas. You configure your system to detect hotkeys and route their reads to dedicated read replicas. Normal keys still go to the primary Redis instance, but hotkeys get distributed across multiple read replicas. The approach should be incoming request should go through the check. If the key is not hot, the request goes to the primary Redis. If the key is hot, the request gets routed to one of the several read replicas. This gives you horizontal read scaling specifically for the keys that need it. Each of these solutions should be applied based on specific characteristics of your hotkey problem. Local caching should be a first line of defense because it requires no additional infrastructure. Key replication should be your next step if local caching is not sufficient. And dedicated read replica should be the solution for sustained hotkey problems that need the most headroom. Now let's talk about cache farming, which is the practice of pre-populating your cache before the traffic hits it. There are 4 scenarios where cache farming should be important. The first is application restart. When your application restarts, the cache is empty and every single request will be a cache mess that is the database. If you get 10,000 requests per second, your database suddenly has to deal with 10,000 queries per second instead of the usual 500 queries per second that might be used to. That search can overrun the database. Now, the second is a new feature launch where you expect high traffic on new data that has never been cached. The third is after maintenance where the cache was cleared. And the fourth is before scheduling a traffic spike, like a sale or a game. The cache farming implementation should query the database for the most popular items and pre-populate the cache before any user traffic arrives. In this code example, the warm cache function queries the 10,000 most popular users by follower count, fetches their full profile from the database, stores each one in the cache with a 1-hour TTL, and logs the result. By the time user traffic starts flowing, all 10,000 popular user profiles are already in the cache and those requests will be served in 1 million millisecond instead of 50 milliseconds. There are 4 warming strategies depending on the scenario. The first is on deploy warming, which runs as a background job after each deployment. The second is scheduled warming, which runs as a cron job before an expected traffic spike. The third is an on-demand warming, which is triggered manually through an admin endpoint. And the fourth is lazy warming with preload, which runs during low traffic periods as a background job. Now, one important detail is that you should warm the cache gradually, not all at once. If you try to warm 10,000 items simultaneously, you will overwhelm the database with 10,000 concurrent queries. The gradual warm function processes items in the batches of 100, pauses for 100 milliseconds between batches. This gives the database time to handle each batch without spiking its CPU. There are 3 production practices to keep in mind. First, warm the cache during deployment, but before accepting the traffic. Your deployment pipeline should warm the cache as one of its steps and only start routing traffic to the new instance after the warming is complete. Second, monitor your cache hit rate during warming to make sure it's progressing as expected. And third, have a fallback strategy if the warming fails. The application should still work correctly by serving a request from the database just with high latency until the cache fills up organically. Now let us move from application level caching to network level caching. Let us talk about CDNs, which are for content delivery networks. Here is a fundamental problem CDN solves. Without a CDN, a user in Tokyo requesting content from a server in Virginia has to make a round trip across the Pacific Ocean. The speed of light in fiber optic cable puts a hard floor on the route trip of about 200 milliseconds each way, so 400 milliseconds minimum just for the network round trip. You cannot optimize this away with better code or faster hardware. Here the physics is a bottleneck. With the CDN, the content is cached on the edge server in Tokyo. The round trip from the user to the edge server which should take about 20 milliseconds each way, which is about 40 milliseconds total. That is roughly 10x improvement in the latency, and you achieve it simply by putting the data close to the user. CDNs should typically provide 4 key benefits. The first is the lower latency because the content is now being served from edge servers near the user. The second is reduced origin load. So because over 80% of the requests can be served entirely by the CDN without ever reaching your origin servers. So the load on your origin servers are reduced by 80%. The third is DDoS protection because CDN providers have massive network capacity. They can absorb the attack traffic. And the fourth is the cost reduction because bandwidth from CDN edge servers is typically cheaper than the bandwidth from your origin servers. Now, not everything should be cached on a CDN. Let us talk about what to cache and what to not cache. Static content should always be cached on the CDN. This includes images, CSS files, JavaScript files, fonts, and videos. These assets typically get a TTL of 1 year because the content does not change. Instead, when you update a CSS file, you give it a new file name with a content hash like styles.abc123.css. The old cache version naturally stops being requested because no HTML page references it anymore. Now, dynamic content can sometimes be cached, but you need to be very selective. API responses might be cached for let's say 1 to 60 seconds, but you have to be careful with user-specific data. HTML pages might be cached for 1 to 5 minutes, but you need to invalidate when the content changes. Search results might be cached for 5 to 60 seconds since they are query dependent. And there is content you should never cache on a CDN. Authenticated user data because different users should see different content. Shopping carts because these are unique to each user and they change frequently. Payment information for obvious security reasons. And real-time data like live scores or stock tickers because even a few seconds of stateless would be unacceptable in these situations. The key distinction should be if the same response can be served to multiple users, it is a good CDN candidate. If the response is unique to a specific user, it should not be on the CDN. And the way you tell CDNs how to cache your content is through HTTP cache headers. Let us go through the key headers. The first is cache control, which tells the CDN how long to cache the content. The second is ETAG, which is the content version identifier that allows the CDN to check whether its cache copy is still current. The third is vary, which tells the CDN that different variations of the same URL should be cached separately, for example, based on the accept encoding header. And the fourth is surrogate control, which is a CDN specific header that overrides the cache control just for the CDN layer without affecting browser caching. Let me walk through the most common cache control directives. For immutable assets like the versions, CSS, and JavaScript files, you should use public max age equals to 315.36.000 immutable. That is 1 year, and immutable flag tells the browsers not to even bother checking for updates. For content that changes periodically, you should use something like public max age equals 300 stale revalidate equals 60. That caches for 5 minutes and then allows serving stale content for additional 60 seconds while revalidating the background. For content that should never be cached, you should be using no store, no cache, must revalidate. And for content that should be cached by the browser but not by the CDN, you should use private max age equals 3600. The private directive tells the intermediate caches like CDNs not to store the response. Practical problem with CDN caching, which is cache bursting. How do you force the CDN to serve a new version of the file when the content changes? The naive approach is to use the same URL for every version of a file. If your style sheet has that, let's say styles.css, and you update it, the CDN might continue serving the old version until the TTL expires. This could even be up to a year if you followed the recommendation for static assets. The better approach should be to include a version identifier in the URL itself. There are two ways to do this. The first is putting the version in the file name, let's say styles.abc123.css, where abc123 is the hash of the file contents. The second is putting the version in a query string like styles.css be equal to abc123. Both work, but the file name approach is generally preferred because some CDNs do not cache URLs with query strings by default. The implementation should be automated. The asset URL function takes a file name, generates an MD5 hash with the file contents, takes the first 8 characters of that hash, and inserts it into the file name. So styles.css becomes styles.abc123.css. When the file content changes, the hash changes, and the URL changes, and the CDN fetches a new version. The old version must still sit in the CDN cache for months, but will never be requested because no HTML page references the old URL anymore. There is a pattern that makes 1 year TTL safe. You never need to invalidate because you never reuse a URL. Chain content gets a new URL, and old URLs simply age out of the cache naturally. And that wraps up our section on CDN fundamentals and how they extend your caching strategy all the way to the network edge. Now let's talk about CDN cache invalidation, which is one of those operations you rarely need, but when you do need it, you need to know exactly what you're doing. So your content is cached at edge locations around the world. That is great for performance, but what happens when you need to update that content, or worse, when you have pushed something which is broken or insecure to your CDN? You need a way to clear that cache. There are 4 main methods for invalidating CDN cache. The first is TTL expiration, which is essentially just waiting for the cache to expire naturally. This is slow because you are waiting, but it is free and it is how normal operations should work. The second is purge by URL. When you invalidate a specific file, this is fast, typically completing in seconds globally and costs you per request. You would use this when you have updated a single file and you need it to be live immediately. The third option is to be purged by prefix, where you actually invalidate everything under a certain path, like purging everything under /images/campaign ID. This is also fast and costs per request, and you would use it when you have updated an entire directory of assets. And the fourth option is purge all, which clears your entire CDN cache globally. This is fast but very expensive, both in terms of what you pay and in terms of the thundering herd problem that will hit your origin servers immediately after. You should reserve this for emergencies only. Now here's something important. You should not be reaching for the purge button every time you update the content. Let me walk you through when purging actually makes sense. You should purge when you have a security vulnerability in your JavaScript, for example, because you cannot wait for TTL when malicious code is being served to users. You should purge when incorrect data is being served and its caching causing user harm or business impact. You should also purge when there is a compliance or legal issue, maybe content that should not have been published in the first place. And you should purge when there is a breaking bug in production that is affecting users. But here's what you should not be doing. You should not be purging for normal content updates. Instead, you should be using version URLs. If your JavaScript file changes, the URL should change from app.v1.js to, for example, app.v2.js. That way, the new file is a cache miss and loads fresh while the old file can expire naturally. And you should not be purging for minor fixes as well when you can just afford to wait. If the TTL is 1 hour and the fix is not urgent, you should just be waiting. For the implementation, let me walk through how a purge looks using the Cloudflare API. You would import the Cloudflare library, then you would define a purge underscore function, URL function that takes the URL you would want to purge. Inside that function, you create a client using your API key. Then you call cf.zones.purge underscore cache.post, passing in your zone underscore ID and a data dictionary containing a files array with the URL you would want to purge. This clears that specific file from all edge locations globally. The key insight here is this. Aggressive cache invalidation is a sign that your caching strategy might need improvements. In a well-designed system, you should be rarely needing to purge. Version URLs and appropriate ETLs should handle 99% of your content update needs. You should be saving the purge for true emergencies. Now let us shift gears and talk about message queues. This is one of the most important patterns in production systems and it fundamentally changes how you think about building scalable applications. Let me start with the problem. Imagine you have an API endpoint that sends a welcome email when a user signs up. Without a queue, your API calls the email service synchronously. The email service would take 2 seconds less to send that email, which would mean that your user is sitting there waiting 2 seconds just to complete the sign up. That's a very bad user experience. Now let's see what happens when we use a queue. Instead of calling the email service directly, your API just drops a message onto a message queue. The enqueue operation takes about 5 milliseconds. Your user gets the response almost instantly. Then in the background, an email worker picks up that message from the queue and sends the email. The user does not need to wait for the email to actually send to complete the sign-up operation. This pattern gives you 4 major benefits. The first is decoupling, where a producer and consumer becomes completely independent. Your API does not need to know anything about how emails are sent. It just says here is a message and someone needs to deal with this. The second is buffering, where the queue can absorb traffic spikes. If you suddenly get, let's say, 10 times the normal traffic, the queue just grows and your workers process the messages at whatever rate they can handle. The third is reliability. When messages persist in the queue until they are successfully processed, so if your email worker, let's say, crashes, the message is still there waiting to be picked up, so it will still be there when the email worker comes back up. And the fourth is scaling, where you can actually add more consumers to increase the throughput. If you just need to send more emails per second, you should just be able to spin up new email workers. The key insight is that message queues let you turn synchronous blocking operations into asynchronous background work, which fundamentally changes how responsive your system feels to the users. Now that we understand why queues are useful, let us talk about one of the most important concepts in message queue design, which is delivery guarantees. This is something you will definitely be asked about in system design interviews, and it's very important to understand for production systems. There are 3 delivery guarantees you need to know. The first is at most once, which is sometimes called fire and forget. With at most once, you send a message and you do not wait for an acknowledgement. If the consumer crashes before processing the message, that message is lost forever. You might think that sounds terrible, but it's actually useful for things like metrics, logs, and non-critical notifications, where losing an occasional message is acceptable and you prioritize throughput over reliability. The second is at least once, which is the default for most production queue systems. With at least once, you send a message and you wait for an acknowledgement. If the consumer does not acknowledge, the message gets redelivered. This means your message is guaranteed to be processed, but it might be processed multiple times if something goes wrong between the processing and the acknowledgement. This is what you should use for most business operations, but you need to design your consumers to be able to be idempotent, which we'll be talking very shortly. The third is exactly once, which sounds ideal but is actually very rare and very expensive. With exactly once, you send a message, deduplicate it, process it, and acknowledge it. This requires distributed transactions to coordinate between the queue and your processing system. You would use this for financial transactions where you absolutely cannot process something twice, but it comes with significant complexity and performance overhead. The key takeaway here is that understanding the trade offs. At most once gives you speed, but it risks the message loss. At least once gives you reliability, but requires idempotent consumers. Exactly once gives you the correctness, but it's very expensive. Now, let me share what actually works in production. The reality is that exactly once delivery is essentially a myth in distributed systems. The practical approach that almost everyone uses is at least once delivery combined with idempotent consumers. Let me walk you through this, which what it looks like in code. Imagine you have a process underscore payment function that receives a message. The first thing you would do is to extract the payment underscore ID from that message. Then you check if this is a payment that has already been processed by querying your process underscores tables. If it already exists there, you simply return early because the work is already done. If it does not exist, you proceed to charge the card with the amount from the message. After the charge succeeds, you insert the payment underscore ID into your process underscores table to mark it as complete. Finally, you acknowledge the message to the queue so it does not get redelivered. Now let's talk about how to choose your idempotency key. There are three main strategies. The first is using the message ID that the queue provides. This works well for simple cases. The second is using a business identifier, let's say order underscore ID or payment underscore ID. This is often the best choice because it ties directly to your domain logic. The third is using a content hash of the message contents. This works when you do not have a natural business identifier. Here's the key insight that I would want you to remember. Exactly once is actually a myth in distributed systems, so you should not be chasing for the pure perfection here. Instead, you should be designing for at least once with idempotent consumers. This is what every major production system does, from payment processes to social media platforms. You should be accepting that messages may be delivered multiple times and make your processing logic actually handle that gracefully so that they only get processed once. Now let's talk about another critical aspect of message queues, which is ordering guarantees. This matters a lot more than people initially realize, especially when you're dealing with state changes. Let me give you a concrete scenario. Imagine a user updates their profile name. First, they set it to Alice, let's say, then they change their mind and set it to Bob. That generates two messages. Message 1 will set the name equal to Alice, and message 2 will set the name equal to Bob. Now, here's the problem. If these messages get processed out of order, the final name ends up as Alice instead of being Bob. That is incorrect, and your user will be confused and frustrated. So, how do queries handle ordering? There are three main approaches. The first is standard queue, which provides no ordering guarantee. Messages can be processed in any order. This gives you high throughput but no ordering. The second is FIFO queue, which is first in first out, which provides strict ordering. Messages are always processed in exactly the order they were sent. This guarantees correctness but limits the throughput because you cannot parallelize as aggressively. The third is a partition queue, which provides per partition ordering. Messages with the same partition key are processed in order, but different partition keys can be processed in parallel. This gives you both high ordering when you need it and high throughput as well. The partition queue pattern is what most production systems use. Let me show you exactly how it works. You choose a partition key, typically something like a user ID. When you send a message, you include this partition key. The queue ensures that all messages with the same partition key go to the same partition and are processed in order. So a profile update, for example, you would set the partition underscore key to the user ID. Both the Alice and Bob messages have the same user ID, so they go to the same partition and get processed in the same order. The key takeaway here is that you should think carefully about ordering requirements. If order matters for a use case, you should be using FIFO, which is first in first out approach, or partition queues with an appropriate partition key. Let us go deeper on when to use each type of queue ordering. You should use a standard queue when you have an independent events that do not relate to each other, like notifications that can arrive in any order, analytic events where order does not affect the analysis, or log processing where you are just aggregating data. In these cases, strict ordering adds overhead without benefit. You should be using FIFO, which is first in first out, or partition queues when you have state changes that must be applied in order, like a user profile updates, where the final state depends on the sequence of changes. Order status changes when you need to go from pending to processing to shipped in sequence, or financial transactions where the order of operations actually affect the final balance. Now here's a pattern that gives you even more flexibility. Handling out of order messages with version numbers. Let me walk you through the code here. You have a process with a version function that takes a message. You extract the user ID and the version number from the message. Then you query the database to get the current version for that user. If the versions in the message is less than or equal to the current version, you skip processing because this is an old message that has already been processed. So if the version is higher, you apply the update and set the new version. This pattern is powerful because it allows you to use standard queues for higher throughput while still maintaining correctness. Even if messages arrive out of order, you only apply updates that move the version forward. This is called last writer wins with version checking, and it is used extensively in distributed systems. The key insight is that version numbers gives you a safety net. Even with perfect queue ordering, things can go wrong. Version checking is your defense in depth. Now let's talk about what happens when things go wrong with queues, which is back pressure. This is when your producers are generating messages faster than your consumers can process them. Let me walk you through the math to show you how quickly this becomes a problem. Imagine your producer is generating 10,000 messages per second, but your consumer can only process 5,000 messages per second. That means your queue grows by 5,000 messages every second, and after just 1 hour, you will have 18 million messages queued up. Eventually, your queue will run out of memory and bad things will happen. Messages will get dropped, your system will become unresponsive, and you are in incident response mode. So, how do you detect back pressure before it becomes a crisis? You need to monitor three key metrics. The first is queue depth, which is how many messages are waiting in the queue. Healthy messages should be less than 1000 messages. Warning is 1000 to 10,000 messages. Critical is more than 10,000 messages. The second is the message age, which is how long the oldest message has been waiting. Healthy should be less than 1 minute. Warning is 1 to 5 minutes. Critical is more than 5 minutes. The third is consumer lag, which is how far behind your consumers are. Healthy should be less than 100 messages. Warning is 100 to 1000 messages, and critical is more than 1000 messages behind. These thresholds will vary based on your specific system, but the principle remains the same. You need visibility into these metrics, and you need alerts that fire before things get critical. Do not wait until you have 18 million messages queued up to find out that there is a problem in your queue. The key insight is that back pressure is inevitable in any system where production and consumer rates can diverge. The question is not if it will happen, but you should be actually like when it does happen, how you will be detecting it and how you will be handling it. Now let us talk about how to actually solve back pressure when it happens. And there are three main strategies, and in practice you will probably use a combination of them. The first solution is to scale your consumers. If your queue is growing because your consumers cannot keep up, you add just more consumer instances. You might go from one consumer to 4 consumers, each pulling messages from the same queue and processing them in parallel. Keep adding more consumers until the queue starts draining. This is the most common and usually the first thing you should be trying. The second solution is to rate limit your producers. If you cannot scale your consumers fast enough, you can push back on the producers. Let me walk through the code, and in that you can see how to implement that. In your publish with back pressure function, you first check the queue depth by calling the queue.get_depth method. If the queue depth is greater than 10,000, you raise a back pressure error telling the caller that the queue is full and to try again later. Only if the queue has capacity do you do actually send the message. This protects your queue from unbounded growth, but it means that some requests will fail. You need to make sure your producers can handle this gracefully. The third solution is to drop low priority messages. Not all messages are equally important. In your publish with priority function, you should check both the queue depth and message priority. If the queue depth is greater than 5000 and the priority is low, you simply return without sending the message. High priority messages still get through, but you shed load by dropping the less important ones. There is a form of load shedding that preserves your system's ability to handle what matters most. The key insight is that you need all these three strategies in your toolkit. You should be scaling consumers when you can. You should rate limit your producers when scaling is not enough. And you should be dropping low priority work when you need to shed load. Having these mechanisms in place before you need them is what separates production ready systems from systems that fail under load. Now let us shift from queues to the workers that consume from them. Understanding how background workers should be structured is essential for building reliable async systems. Let me walk you through the basic worker loop that forms the foundation of most job processing systems. You have a worker class with a run method that loops forever. Inside the loop, you first fetch a message from the queue with a wait time of 20 seconds. That wait time means that the worker will long poll, waiting for up to 20 seconds for a message before returning. If no message comes back, you continue to the next iteration of the loop. If you do get a message, you wrap the processing in a try except block. You call your process method to do the actual work. If that succeeds, you acknowledge the message to the queue so it does not get redelivered. If an exception occurs, you call the handle error to deal with the failure appropriately. This pattern has several important characteristics. The long polling with a 20-second wait time is more efficient than constant polling because you are not making requests when there is no work to be done. The explicit acknowledgement after successful processing ensures that the message only gets removed from the queue when they actually have been handled. And the try except with the error handling gives you a place to implement retry logic, dead letter queue routing, and alerting. One thing to note is that the process method is where your business logic goes. Everything else in this worker loop is infrastructure code that should be consistent across all your workers. Many teams extract this into a base class or a framework so that the individual workers only need to implement the process method. The key insight is that this simple loop pattern is the foundation of reliable job processing. You should get this right, and you will be having a solid base to build a foundation on. And if you didn't get this wrong, you'll be debugging mysterious failures in productions. Now, let us level up from a single worker to a worker pool that can process multiple messages concurrently. Let me walk through the worker pool class. In the constructor, you create a threaded pool executor with a configurable number of workers defaulting to 10. In the run method, you loop forever. You fetch a batch of messages from the queue up to 10 at a time using receive_batch. Then you submit each message to the thread pool for processing. You store tuples of the message and its futures so you can track completion. After submitting all the work, you iterate through the futures. For each one, you call future or result to wait for the completion. If it succeeds, you acknowledge the message. If it raises an exception, you can call handle error. This pattern gives you concurrency within a single worker process. Instead of processing one message at a time, you can process 10 messages in parallel. This is particularly useful when your processing involves I/O operations like database calls or API requests, where the thread can be waiting while other threads make progress. Now let us talk about scaling workers at the infrastructure level. You should monitor three metrics to decide when to scale. If queue depth is increasing, you should add more worker instances. If workers are idle most of the time, you can remove worker instances to save resources. If CPU or memory usage is high, you might need large instances rather than the more instances. The key insight is that you have two levels of scaling: concurrency within a worker through threaded pools and horizontal scaling by adding more worker instances. You should be using both levers to match your processing capacity to your workload. Now let's talk about what happens when a message processing fails, because eventually it will fail in any production system. The question is how you handle those failures gracefully. Let me walk you through a retry pattern with exponential backoff. Your process with retry function takes a message, You extract the attempt count from the message, defaulting to 1 for the first attempt. You define your max attempts, let's say 5. In a try block, you call the do work method to process the message. If that succeeds, you acknowledge the message and you are done. If you catch a retriable error, you first check if you have exhausted your retries. If attempt is greater than or equal to max attempts, you give up, send the message to a dead letter queue for investigation, and acknowledge that the original message so it stops being redelivered. If you have retries remaining, you calculate the delay using an exponential backoff, which is 2 to the power of the attempted number, capped at 300 seconds or 5 minutes. You increment the attempt counter in the message and you send a new copy of the message to the queue with that delay, and you then acknowledge the original message. If you catch a fatal error, meaning something that will never succeed no matter how many times you retry, you immediately send to the dead letter queue and acknowledge. There is no point retrying something like a validation error or a permanently missing resource. This pattern distinguishes between retriable failures like timeouts and server errors and fatal failures like invalid data or missing permissions. Making this distinction is crucial because retrying fatal errors just wastes resources and delays your ability to investigate the real problem. The key insight is that not all errors are created equal. Design your retry logic to distinguish between transient failures that might succeed on retry and permanent failures that need human investigation. Now let us talk about a crucial refinement to retry logic, which is to add jitter to your backoff delays. Let me walk you through the get retry delay function. You start with exponential backoff, calculating 2 to the power of the attempt number as your base delay. Then you cap that delay at 300 seconds or 5 minutes, so your retries and do not wait forever. Finally, and this is the key part, you add jitter by adding a random value between 0 and 50% of the cap delay. Now let me explain why jitter matters with a concrete scenario. Imagine 1000 messages all fail at the same time, maybe because a downstream service went down briefly. Without jitter, all 1000 messages retry at exactly the 2-second mark. They all fail again because they are hitting the service simultaneously. Then all 1000 retry exactly at the 4-second mark. You have created a thundering herd problem that keeps hammering the service in synchronized waves which can prevent it from recovering. With jitter, those same 1000 messages spread their retries across a range. Instead of all 1000 messages retrying at 2 seconds, they retry somewhere between 2 and 3 seconds. The load is distributed, the downstream service now has a chance to recover, and your success rate improves dramatically as well. Let me describe what the retry sequence looks like with jitter. On attempt 1, the base delay is 2 seconds, but with jitter it could be anywhere from 2 to 3 seconds. On attempt 2, base is 4 seconds, with jitter 4 to 6 seconds. On attempt 3, base is 8 seconds, with jitter 8 to 12 seconds. On attempt 4, base is 16 seconds, with jitter 16 to 24 seconds, and so on. The key insight is that jitter is not optional in production systems. Anytime you have a retry logic, you need to have a jitter. It is a simple change that prevents a whole class of cascading failures in your system. Now let us talk about the single most important property your background workers must have, which is idempotency. I cannot stress this enough. If you take one thing from this section, it should be this. Let me show you why idempotency matters with a payment example. You receive a message that says charge customer, let's say $100. Your worker processes that message and charges the customer, but before the worker can acknowledge the message, it crashes. The queue does not know that the message has been processed, so it redelivers the message. Another worker then picks up the same message and charges the customer again. Now your customer has been charged $200 instead of $100. This is a disaster for a business and your customers' trust. Now let us see what happens with idempotency. Same scenario, the message comes in which is to charge the customer $100. Your worker processes the message and charges the customer. The worker now crashes before acknowledging. The message gets redelivered, but this time when the new worker starts processing, it first checks, has this payment already been charged? It finds that yes, it has. So it then skips the charge and just acknowledges the message. The customer is charged exactly $100 even though the message was processed twice. This is not a theoretical concern. In any At least once delivery system, which is most production queues use, duplicate delivery will happen. Network blips, worker crashes, timeout mismatches, all of these can cause a message to be delivered more than once. Your system must be able to handle this correctly. The key insight is that idempotency is mandatory, not optional. Every operation that your background workers perform must be safe to execute multiple times. If it is not naturally idempotent, you must make it idempotent through patterns, which we'll cover in the next few slides. Now let me show you the most common pattern for implementing idempotency, which is storing idempotency keys in your database. Let me walk through the charge underscore customer function. You extract the idempotency key from the message, then you check if the key already exists in your payments table by querying for it. If you find an existing record, you return the record immediately. The work was already done, so you just return the result with return the same result. If no existing record is found, you proceed to process a payment by calling your payment provider. After the charge succeeds, you insert a record into your payments table that includes the idempotency key and the result. For future duplicate messages, this record will be found and the charge will be skipped. Now there is a subtle thing that is worth discussing. What happens if two identical messages arrive at almost the exact same time? Both workers query the database, neither finds the existing record, and both proceed to charge. This is called a race condition and you need to handle it. The solution is to use a unique constraint on the idempotency key column in your database. That way, even if two workers try to insert at the same time, only one will succeed. The other will get a unique constraint violation. You catch that exception and treat it as a signal that the work was done by another worker, then query for the result and return it. The key insight is that idempotency requires both checking before processing and protecting against race conditions. The database unique constraint is your safety net for concurrent processing. So let me show you two more patterns for implementing idempotency that work in different situations. The first pattern is conditional updates. This is useful when you're updating a value and you know that the current value should be. Let me walk through the update inventory function. You extract the product ID, expected quantity, and the new quantity from the message. Then you execute an update statement, but you add a where clause that checks not just the product ID, but also the current quantity matches the expected quantity. If the row was already updated to a different value, the where clause will not match, row count will be 0, and you know the update was already applied or superseded. This pattern is sometimes called optimistic concurrency control. You are optimistic that you have the current state and the database confirms or denies that assumption. If the state has moved on, your update is a no-op, which is exactly the idempotent behavior would want. The second pattern is natural idempotency, where some operations are inherently idempotent without any extra work. The set user email function is a good example. You execute an update statement that sets the email to a specific value. If you run the same update twice with the same email value, the second run changes nothing. The operation is naturally idempotent because setting something to the same value is a no-op. Whenever you are designing a new operation, you should be asking yourself, is this naturally idempotent? If you are setting a value to a specific state rather than an incrementing or appending, it often is. Prefer these natural idempotent designs when possible because they require less infrastructure to be safe. The key insight is that you have multiple tools for achieving idempotency. Use idempotency keys for operations with external side effects like payments. Use conditional updates for state changes where you know the expected current state. And recognize natural idempotency when it exists. Now let us talk about a particularly serious problem, which is poison messages. These are messages that cause your consumer to fail every time they are processed. Let me give you some examples of what creates a poison message. It could be an invalid JSON format where the message cannot even be parsed. It could be a missing required field that your processing code assumes will be there. It could be a reference to a data that has been deleted, so when you try to look it up, you get nothing. Or it could also be a message that triggers a bug in your application code. The danger of poison messages is that they create an infinite loop. Here is how it happens. Your worker will receive a poison message. The worker crashes or throws an exception while trying to process it. The message goes back to the queue because it has not even acknowledged. The worker receives the same message again. The worker crashes again. This cycle repeats forever. Meanwhile, all the legitimate messages behind the poison message are not being processed. Your queue is effectively blocked. I've seen this happen in production and it's pretty painful to debug because the symptoms are pretty confusing. Your workers look like they are running, messages are being received, but nothing is actually getting processed successfully, and your queue will keep growing. The key insight is that poison messages are inevitable, so you will have bugs, you will have malformed data, and you will have edge cases you did not anticipate. The question is whether your system can detect and isolate poison messages before they block everything else. Now let me show you how to detect and handle poison messages. Let me walk through the example here. So if you look at the process with poison detection function, you extract the message ID from the message, then you increment a delivery counter in your cache using the message ID as a key. If the delivery count is greater than 5, you know the message has failed too many times. At that point, you send it to the dead letter queue, acknowledging that the original message so that it stops being redelivered. You will then fire an alert so someone can investigate and return early. If the delivery count is still within acceptable limits, you proceed with normal processing in a try block. If processing succeeds, you acknowledge the message and delete the delivery counter from the cache since it no longer is needed. If processing fails, you let the exception propagate, which means the message will be redelivered and the counter will increment on the next attempt. Now here is the good news. Most queue systems have built-in support for this pattern. AWS SQS has a max receive count setting that automatically moves messages to a dead letter queue after a specified number of failed deliveries. RabbitMQ track redeliveries with an X delivery count header. Kafka requires application level tracking, but the pattern is pretty similar. The key insight is that you should be able to configure a maximum delivery count for every queue you operate. The exact number depends on your use case, but 5 is a reasonable default. After 5 failures, the message is almost certainly poison, and you should isolate it before it causes even more damage. Now let us talk about where those poison messages and other failed messages should go. The dead letter queue, often abbreviated as DLQ. The flow works like this. A message comes into your main queue. Workers process them. If a message succeeds, it is done. If a message fails too many times, it gets moved to a dead letter queue. From there, someone needs to go manually review what went wrong. After investigation and fixes, you can replay the message back to the main queue. The dead letter queue serves 4 important purposes. The first is preserving failed message so you do not have to lose data. Even if a message cannot be processed right now, you keep it around for later investigation. The second is unblocking your main queue by removing poison messages so they do not hold up everything else. The third is enabling the investigation by giving you a place to examine failures in detail, understanding what went wrong, and fix the root cause. The fourth is allowing replay, where after you have fixed a bug or resolved the dependency issue, you can process the messages and recover. Think of dead letter queue as a hospital for, let's say, sick patients or sick messages. Messages that go there when something is wrong with them, not to be forgotten but to be diagnosed and treated. The key insight is that every production queue system should have a corresponding dead letter queue. It is not optional. Without it, you will lose data and you will have no way to recover from certain classes of failures. Now let me show you how to actually set up a dead letter queue. In AWS SQS, you configure this using a retrieve policy. The policy has 2 key fields. The first is dead letter target ARN, which is the ARN of your dead letter queue. The second is max receive count, which is how many times a message can be received before it gets moved to the dead letter queue. Setting max receive count to 5 means that after 5 failed processing attempts, the message will automatically move to the dead letter queue. When a message lands in the dead letter queue, it carries a metadata that will help you investigate. The message body is the original message content exactly as it was sent. The attributes include approximate receive count showing how many times it was received, send timestamp showing when it was originally sent, and dead letter queue source ARN showing which queue it came from. The metadata is valuable for debugging. The receive count tells you if it failed quickly or took multiple attempts. The send timestamp tells you how old the message is and helps you correlate with other events. The source queue tells you which part of your system generated this message. The key insight is that dead letter queue configuration is something you should set up when you create the queue, not after you have an incident. You should be making part of your standard queue provisioning process. Now let us talk about what you should actually do with the dead letter queue. You should be able to monitor it and replay messages when appropriate. Let me walk through a simple monitoring function. Your monitor DL queue function checks the queue depth. If the depth is greater than 0, you fire an alert because any messages in the DL queue, which is a dead letter queue, represents a problem. If the depth is greater than 100, you page the on-call engineer because this is pretty important. This might seem aggressive, but I would want to emphasize here something pretty important. Any messages in your dead letter queue represent a problem. Unlike your main queue where some backlog might be acceptable, the dead letter queue should ideally be empty. Every message there represents the data that did not get processed correctly. You should be able to investigate immediately, not wait until it becomes a big problem. For replaying messages, the process is pretty straightforward. You loop through the DL queue, receives messages one at a time. Optionally, you transform or fix the message if you know what was wrong. Then you send it back to the main queue for reprocessing. Finally, you acknowledge and remove it from the DL queue. The key insight is that the dead letter queue is not a trash can where just messages that go to die. It's a staging area for messages that need attention. Investigate every message, fix the root cause, and replay or intentionally discard. Now, let me go deeper on the considerations for replaying messages from the dead letter queue. Before you replay anything, you need to understand why the messages failed in the first place. If there is a bug in your consumer code, you should fix the bug before replaying. Otherwise, you will just send this message right back to the DL queue. If an external dependency was down, wait for it to recover. Replaying while the dependency is still down will accomplish nothing. If the data in the message is invalid, you need to decide whether to transform the data to make it valid or discard the messages entirely. And if ordering matters for your use case, replay messages in the order they were originally sent, not the order they hit the DL queue. You should also think about retention and archival. You should keep the messages in the DL queue for at least 14 days so you have time to investigate and replay. Before messages expire, archive them to long-term storage like S3 for compliance purposes, and document why each batch of messages failed so you can prevent similar issues in the future. Here's the key insight I would want to leave with you and on dead letter queues. The dead letter queue is not a trash can. You should think of it more like a hospital for sick messages, sick patients. Every message in there actually deserves attention. You should be investigating, fixing the root cause, and then either replaying the message or intentionally discarding it with documentation of why. Never just let the messages stay in the DL queue until they expire. Now, let us shift to the topic that bridges the technical and the human understanding here. So, how do users experience eventual consistency? When you build async systems with queues and background workers, you introduce delays that users will notice if you do not handle them carefully. Let me show you the gap between what users expect and what actually happens. When a user posts something, they expect to see it immediately, but in reality, the post might not even appear for 1 to 5 seconds while it propagates through the system. When a user likes a post, then they expect the count to increase immediately, but the count updates eventually, not instantly. So when a user sends money, they expect the balance to change immediately, but the balance might not even update until the transaction has been confirmed. So how do you make eventual consistency invisible to the users? The first pattern is optimistic UI. Let me walk through the code for a like button. When the user clicks like, you immediately update the UI to show the incremented count and the like state. This happens before even the server even receives the request. Then you send the API call in the background. If it succeeds, great, the UI already shows the right state. If it fails, you roll back the UI to the previous state. This pattern makes the app feel instant even though the actual persistence is asynchronous. The user sees immediate feedback, which is what they expect from a responsive application. Now, the key insight is that eventual consistency is a technical reality, but it does not have to be a user-facing problem. With the right UI patterns, you can hide the async nature of your system and deliver an experience that feels pretty responsive. Let me show you two more patterns for handling eventual consistency in user interface. The second pattern is read your writes, which ensures users always see their own recent actions. Let me walk through the code. In your create post function, after inserting the post into the database, you also push the post ID to a user specific cache list. When you fetch post for that user in the get user post function, you retrieve both the post from the cache and the post from the database, then merge and reduplicate them. So why does this matter? Imagine a user that creates a post and immediately views on their profile. Without read your writes, the post might not have replicated to the read replicate yet, so they do not see it. They think that their post was lost and try again and they will create a duplicate. With read your writes approach, the user will always see their own recent post even if replication has not been completed. The third pattern here is the explicit loading states. Instead of showing stale data as it was fresh, you show the user that something is loading. In a React component, you check if the data is still loading. If it is, you show a skeleton placeholder. Only when the loading completes do you show the actual content. This is better than showing stale data because it sets the right expectation. The user knows that something is happening. They are not confused by seeing the old content or missing content. And when the fresh data appears, it feels like natural completion of an action rather than a mysterious update. The key insight is that you have three tools for managing eventual consistency in the UI: optimistic updates for instant feedback, a read your writes approach for user specific consistency, and loading states for transparency. You should be using them together to create an experience that feels responsive and trustworthy. Now let us talk about when eventual consistency actually breaks down and causes real problems. There are scenarios where you simply cannot use eventual consistency because the consequences of stale data are too severe. Let me walk through the first scenario, which is inventory oversell. Imagine you have one item left in stock. User A reads inventory and sees one available. User B reads inventory at almost the same time and also sees one available. Because they're reading from the replica that has not received user A's purchase yet. User A purchases the item, setting quantity to 0. User B also purchases the item, setting quantity to -1. You now have sold an item you do not have. The solution here is strong consistency with pessimistic locking for inventory operations. You cannot accept the risk of overselling. The second scenario is double spend. Imagine a user that has $100 in their account. They read their balance and they see $100. They initiate a transfer for $80. Before that transfer completes, they initiate another transfer for $50 because their balance still shows $100. Both transfers will succeed and now their balance will show -$30. The solution here is synchronous balance checks within a database transaction. Financial operations require strong consistency. The key insight is that dimensional consistency is not appropriate for all operations. You need to identify which operations in your system can tolerate staleness and which operations cannot. Then you use the appropriate consistency model for each. So let me show you a third scenario and then summarize when to use strong consistency. The third scenario is duplicate actions. A user clicks the submit order button, but the page is slow, so they click it again. Both click results in API requests. Both requests gets processed. The user ends up with two orders instead of one. The solution here is add importancy keys on the client side. When the user clicks submit, you generate a UID as an idempotent key. The same key is sent with all retries. The user uses this key to deduplicate. Let me give you a summary of when you should use strong consistency instead of eventual consistency. You should use it for financial transactions where money must not be lost or duplicated. You should use it for inventory management where you cannot sell what you do not have. You should use it for booking systems where double booking actually will destroy the user trust. And you should use it for user authentication where security is pretty important. For everything else, eventual consistency with proper UI handling is usually fine. Social media posts, notifications, analytics, recommendations, all of these can tolerate some staleness without causing harm. The key insight is that consistency requirements should be driven by business impact. You should be asking yourself, what is the worst thing that could happen if the user sees stale data? If the answer involves money loss, legal liability, or safety issues, you should be using strong consistency. Otherwise, you should be designing for eventual consistency and handle it gracefully in the UI. Let us pause and summarize the key takeaways from everything we have covered on caching and async processing. For caching, there are 5 things to remember. First, you should use cache aside as a default pattern because it is simple, flexible, and works for most use cases. Second, TTL is a trade-off between freshness and load. Shorter TTL means fresher data but more origin hits. Longer TTL means better performance but staler data. Third, cache invalidation is hard, so prefer TTL based expiration combined with explicit deletes when data changes. Fourth, handle thundering herd problem with jitter, so locks or stale while revalidate to prevent the cache messages from overwhelming your origin. Fifth, you should be warming up your cache before expected traffic spikes so users do not have to experience the cold cache penalty. For CDNs, there are three things to remember. First, cache the static assets with long TTLs and use version URLs so the new deployments get new content without invalidation. Second, you should be using cache control headers to precisely control caching behavior at the CDN, browser, and intermediate proxy levels. Third, purge only for emergencies, not routine updates. If you're purging regularly, your caching strategy needs work. These patterns form the foundation of high performance systems that can handle massive scale while keeping the response times fast. Now, continuing our summary section, let me cover the message queues, background workers, and eventual consistency. For message queues, there are four things to remember. First, you should be designing for at least once delivery with idempotent consumers. You should not be chasing exactly once delivery because it is essentially a myth in distributed systems. Second, you should be using partition queues when message ordering matters, with a partition key that groups related messages together. Third, you should be monitoring queue depth for back pressure because a growing queue is an early warning sign on problems. Fourth, you should be scaling your consumers based on queue depth and processing time to match the capacity with the demand. For background workers, there are four things to remember. First, you should be implementing exponential backoff with jitter to avoid the thundering herd problem during retries. Second, idempotency is mandatory, not optional, so every worker operation must be safe to execute multiple times. Third, detect and handle poison messages before they block your entire queue. Fourth, use dead letter queues for failed messages and investigate every message in the DL queue. For eventual consistency, there are four things to remember. First, you should be using optimistic UI to make async operations feel instant to users. Second, implement read your writes approach so that users always see their own recent actions. Third, you should be using strong consistency for financial and inventory operations where staleness causes real harm. Fourth, you should be designing for acceptable staleness, not zero staleness, because zero staleness is often impossible and rarely necessary. Now we are entering what I consider one of the most important sections of this entire course, which is reliability and failure handling. Everything we have covered so far, whether it's caching, the queues, the async processing, all of it can fail. Now this section is about what happens when it actually does. Let me show you the reliability toolkit that we will cover. We'll start with timeouts, which are your first line of defense. Then we'll move to retries, which can give your operations a second chance. Then we'll move to circuit breakers, which stop calling you services that are failing. Then we move to bulkheads, which isolate the failures so that they do not spread. Then we'll cover graceful degradation, which keeps your system partially function when components fail. And finally, we'll cover load shedding, which protects your system by rejecting work it cannot handle. Here's a fundamental mindset shift I want you to make. In interviews, people often design for success. They assume that services are available, the network is reliable, and dependencies respond quickly. In production, you must design for failure. Services will fail, then the network will partition, and dependencies will time out. The question is not will it fail. The question is how will we handle it personally when it actually does fail. This is what this section is all about. The key insight is that reliability is not about preventing all failures. This is pretty impossible. So our goal with reliability is that it's about detecting failures quickly, containing their impact, and recovering gracefully. Let us see how we can do that. Before we dive deep into the solutions, let us also understand the different types of failures you will encounter in the production systems. There are typically 5 categories of failures. The first is crash failures, where a process dies or a server reboots. This is pretty common, but it's also the easiest to handle because the failure is pretty obvious. The second is omission failures, where the network drops a packet or a request gets lost. This is also common and can be handled with retries. The third is timing failures, where a response comes back too slowly or times out. This is very common and is actually the most frequent type of failure in production. The fourth is response failures, where the service actually responds but with the wrong data. This is occasional and can be harder to detect. The fifth is Byzantine failures, where a node behaves maliciously or in a corrupted way. This is rare in most systems and typically only matters for systems that need Byzantine fault tolerance. Here is the distribution of failures in most production systems. About 60% of the are timing failures, meaning slow dependencies. To about 25% are cache failures, which means processing or a server actually getting shut down randomly. About 10% are mission failures, meaning network issues, and about 5% are response or Byzantine failures. Notice that timing failures will actually dominate. This is why timeouts are so critical. Most of your failure handling work will be dealing with services that are either too slow or services that may are taking way too long to respond to. The key insight is that slow services are actually worse than dead services. Because the dead services they actually fail immediately. Slow services will consume resources like threads and connections while failing. They are harder to detect and more likely to cause cascading failures. Now let us talk about partial failures, which are the trickiest to handle because the system is neither fully up or nor fully down. Imagine an API gateway connects to four downstream services: user service, order service, payment service, and notification service. User service and order service are working fine. Payment service is completely down. Notification service is slow but responding. So now what do? Some features work, some do not. You cannot return a 500 error for everything, but you also cannot pretend everything is fine. So now let me show you how failures propagate if you are not careful. Payment service will become slow and taking, let's say, 2 seconds to respond instead of 200 milliseconds. Order service is calling payment service and waiting. Order service threads are now blocked waiting for the payment responses. More requests come in, more threads block. Eventually, order service exhausts the thread pool. Order service stops responding entirely. API gateway times out and waiting for order service. User will see more errors, user retry, generating more load. The whole system will collapse. This is called a cascading failure, and it is one of the most common ways production systems go down. One slow service takes on multiple other services that depend on it. The key insight is that a slow service is worse than a dead service. A dead service will fail fast. You call it, it fails immediately, and you can handle the error and move on. A slow service ties up your resources while failing. It will block your thread, hold connections, and spreads the slowness to everything that depends on it. The patterns we cover next are designed to prevent exactly this scenario. Now let's talk about the single most important reliability pattern, which is timeouts. Every external call in your system must have a timeout, no exceptions ever. Let me show you what happens without a timeout. You have a get user profile function that calls the user service.get. If the user service hangs, your thread will hang as well. As more requests come in, more threads will hang. Eventually, your thread pool is exhausted and your service dies, all because you did not set a timeout. Let me show you the same function with a timeout. You call the user service.get with a timeout of 2 seconds. If the service does not respond within 2 seconds, you cache the timeout error and fall back to getting the user from the cache. Your thread is freed up after 2 seconds, regardless of what the downstream service is doing. This is a timeout golden rule. Every external call must have a timeout. This includes database queries, HTTP requests to other services, external API calls, cache operations, anything that leaves the process. If you're calling something external, you should be setting a timeout. I have seen production outages caused by a single missing timeout. And everything that has worked fine for let's say months, then one day a downstream service got slow and the calling service collapsed because it kept waiting forever for responses that were not coming. The key insight is that timeouts are your first line of defense against cascading failures. They ensure that no matter how badly your dependency behaves, your service can recover and continue serving requests. Now let us talk about how to actually choose timeout values. This is more nuanced than it might seem. A timeout needs to account for four things: network latency to reach the service, queue time waiting for the service to pick up a request, processing time for the service to do the work, and the response latency for the data to come back. All of these do add up. Here's a simple formula that works well in practice. Take P99 latency, meaning the latency that 99% of requests are faster than, multiply it by 2 to give you some headroom, then add a buffer for variance. So if your P99 latency is 200 milliseconds, your timeout would be 200 times 2 plus 100 millisecond buffer, which gives you 500 milliseconds. Let me give you some typical timeout ranges for different types of calls. For database queries, 1 to 5 seconds is typical because it's local network and should be fast. For internal service calls, 1 to 3 seconds is pretty typical because you are in the same data center typically. For external API calls, 5 to 30 seconds is typical because internal latency varies widely. For file uploads, 30 to 120 seconds is typical because you are moving large payloads. For background jobs, it depends on the workload, but minutes to hours is not unusual. The key insight is that timeout value should be based on major latency, not guesses. You should be instrumenting your services, collect the P99 latency metrics, and set timeouts accordingly. You should be reviewing and adjusting them as your system evolves. Talk about layered timeouts, which is critical when you have multiple services calling each other. Imagine a request flow from client to API gateway to service A to service B to the database. So each layer needs its own timeout, and here is a crucial rule. Inner timeouts must be shorter than outer timeouts. Let me explain why what is wrong with the first approach. So if your API gateway has a 5-second timeout but service A has a 10-second timeout, service A will never complete before the gateway gives up. The gateway times out, returns an error to the client, but service A is still running. You have wasted resources and the client did not even get the result. The correct approach is cascading timeouts where each layer is shorter than the one above. The client might have a 10-second timeout, the API gateway has 8 seconds, service A has 5 seconds, service B has 2 seconds, and then the database has 1 second. This way each inner layer completes or fails before the outer layer gives up. You also need to leave time for error handling and retries at each layer. If service A has a 5-second timeout for calling service B and it wants to retry once, service B's timeout needs to be less than 2.5 seconds to allow for 2 attempts within the 5-second budget. The key insight is that the timeout values across your system needs to be coordinated. Draw out your service call graph annotated with timeouts and make sure that the math works out. Inner timeouts must always be shorter than the outer timeouts. Now let's get more precise about timeout types. There are actually 2 different types of timeouts you need to configure for most HTTP calls: connection timeout and read timeout. The connection timeout is how long you wait to establish a TCP connection to the server. This detects whether the server is up and reachable. In Python requests, you can set both timeouts as a tuple. The first value is the connection timeout and the second is the read timeout. So a call with the timeout set to 1, 10 means actually 1 second to connect, 10 seconds to read. The read timeout is how long you wait to receive the response after the connection has been established. This detects whether the server is slow or overloaded. Here is a common mistake I see happening many times in production systems. People set a single timeout value like 10 seconds. That means both connection and read timeouts are 10 seconds. The problem is that if the server is completely down, you wait 10 seconds just to discover that you cannot even connect. This is pretty wasteful. A better approach is short connection timeout with a longer read timeout. If you use 1 second for connection and 10 seconds for read, you fail fast when the server is unreachable, but you still give the server enough time to process your request when it is up but slow. The key insight is that the connection failures and read failures are different conditions that deserve different timeout values. Connection failures mean something is fundamentally wrong. Read timeouts mean the server is struggling. You need to tune them independently. Now let me give you a more complete picture of timeout configuration and best practices. For connection timeouts, 1 to 3 seconds is typical because a network round trip to establish a connection should be fast. If you cannot connect in 3 seconds, something is wrong. For read timeouts, 5 to 30 seconds is typical because the server needs time to actually process a request. For write timeouts, when you are uploading data, 5 to 30 seconds is also typical. For idle or keep alive timeouts that determine how long to keep a connection open for reuse, 30 to 120 seconds is typical. Let me show you a production ready configuration using Python request. You create a session object for connection pooling. You create an HTTP adapter with pool collections and pool max size set to 100 and max retry set to 3. You mount this adapter to handle all the HTTP requests. Then when you make a request, you always pass a timeout tuple with connection timeout of 3 seconds and read timeout of 10 seconds. This configuration gives you connection pooling for efficiency, automatic retries for transient failures, and appropriate timeouts for both connection and read phases. The key insight is that the timeout configuration should be centralized and consistent across your application. You should be creating a configured HTTP client and use it everywhere rather than configuring timeouts on each of the individual requests. Now let us move from timeouts to retries. When a request fails, should you try again? It depends on the type of failure. Let me walk you through which HTTP status codes are retriable. A 500 internal server error is retriable because it often indicates a transient server issue. A 502 bad gateway is retriable because the upstream server was temporarily down. A 503 service unavailable is retriable because the server is overloaded but may recover. A 504 gateway timeout is retriable because the request was slow but might succeed on retry. A 429 too many requests is actually retriable but with backoff because you need to wait before trying again. However, a 400 bad request is not retriable because it is a client error that will fail again. A 401 unauthorized is also not retriable without new credentials. HTTP 404 not found is not retriable because the resource does not exist. For exceptions, connection errors and timeout errors are generally retriable because they indicate transient network issues. Validation errors are not retriable because the request itself is invalid. The key insight is that retry should only happen for transient failures that have a reasonable chance of succeeding on the next attempt. Retrying permanent failures just wastes resources and delays error handling. Now let's talk about how to retry. The naive approach is to retry immediately when something fails. This is almost always wrong. Let me show you the bad approach first. You have a call with retry function that loops through attempts and just continues immediately when it catches a retriable error. The problem is that if the server is overloaded, hammering it with immediate retries makes things worse. You are adding load to an already struggling service. The good approach is exponential backoff. Instead of retrying immediately, you wait before each retry and you wait longer each time. Let me walk you through the code. Your call with backup function loops through max retry attempts. When you catch a retriable error, you first check if this was the last attempt, and if so, you raise the exception. Otherwise, you calculate a delay of 2 to the power attempt, which gives you 1, 2, 4, 8, 16 seconds for successful retries. Then you sleep for that delay before trying again. This pattern gives the failing service time to recover. Instead of hitting it with 5 requests in 1 second, you spread those 5 requests over about 30 seconds. The service has been breathing room and your success rate actually improved. The key insight is that immediate retries can turn a minor service hiccup into a major outage. Exponential backoff is essential for preventing retry storms for overwhelming already stressed services. Now let us add an important refinement to our backoff strategy, which is jitter. We touched on this earlier with background workers, but is equally important for synchronous retries. The problem with pure exponential backoff is that the requests tend to be correlated. If a bunch of requests all fail at the same time, they will all retry at the same time too. 1,000 requests fail at time 0, then they all retry at the time 1 second, then they all fail again. They all retry at, let's say, 3 seconds at the same time. And then you have a synchronous wave for retries that keep hitting the service at the same moment. The solution is to add randomness to the backoff delay. Let me walk you through the get backoff delay function. You calculate the exponential delay as base times 2 to the power attempt. You cap it at some maximum like 60 seconds. Then instead of using that value directly, you return a random value between 0 and the cap delay. This is called full jitter. With full jitter, those 1,000 requests that fail at time 0 will retry random times between 0 to 2 seconds. Some retry will happen at 0.3 seconds, some will happen at 1.7 seconds, spreading the load. On the second attempt, the spread will happen between 0 and 4 seconds. The synchronized waves become a smooth distribution of requests. Now let me give you concrete numbers. On attempt 1, the exponential delay is 2 seconds, but with full jitter, the actual delay is randomly between 0 and 2 seconds. On attempt 2, it's between 0 and 4 seconds. On attempt 3, it's between 0 to 8 seconds. On attempt 4, it's 0 to 16 seconds, and so on. The key insight is that the jitter breaks correlation between retry attempts. Combined with exponential backoff, it is one of the most effective patterns for preventing cascading failures. Now let us talk about a more advanced retry pattern, which is retry budgets. This limits the total impact of retries on your system. Now here's the problem. Your service receives 1000 requests per second, 10% of them will fail and need to retry. Each failure retries 3 times. That means you are generating an extra 300 requests per second, which is 30% additional load on your already failing service. Your retries are making the problem worse. The solution is a retry budget, which caps the percentage of requests that can be retries. Let me walk through the retry budget class. In the constructor, you set a budget percentage like 20% and a window seconds for how long to track. You keep list of request timestamps and retry timestamps. The can retry method checks if you are within the budget. You count recent requests and recent retries within the time window. You calculate the retry percentage. If it is below the budget, you can retry. If it is at or above the budget, you should not retry. You also have record request and record retry methods to track each request and retry attempt. This ensures that no matter how bad things get, retries never exceed 20% of your total request volume. You are protecting the downstream service from being overwhelmed by retry traffic. The key insight is that individual retries are beneficial, but unlimited retries at scale can cause cascading failures. A retry budget ensures that the collective retry behavior stay within safe bounds. Now let me show you how to actually use the retry budget in practice. You create a retry budget instance with your desired budget percentage like 20%. In your call with budget function, your first record that the request is happening is by calling the retry budget.record request. Then you loop through your retry attempts. If you catch a retriable error, you check if you have more attempts. If not, you raise. If you do have more attempts, you check if the retry budget allows a retry by calling retry budget.canRetry. If the budget is exhausted, you raise the retry budget exceeded error instead of retrying. If the budget allows it, you record the retry, calculate the backup delay, sleep, and try again. This pattern gives you 4 benefits. First, it limits the amplification so retries cannot multiply your traffic beyond a control factor. Second, it preserves the capacity for downstream service by not overwhelming it with retry traffic. Third, it fails fast under load by stopping retries when the budget is exhausted rather than continuing to pile on. Fourth, it is self-healing because the budget replenishes as the window slides forward. When things recover, retries are allowed again. The key insight is that retry budgets are especially important in high traffic systems where even a small percentage of retries can represent a significant load. If you're processing millions of requests, even 10% retrying creates hundreds of thousands of additional requests. Now let us address the critical requirement for retries, which is idempotency. If you're going to retry a request, those requests must be safe to execute multiple times. Let me show you the danger with a concrete example. You send a request to transfer $100 from account A to account B. The server receives the request and processes it, transferring the money. But then the response gets lost due to network blip. Your client did not receive a response, so it retries. The server receives what looks like a new request and processes it again, transferring another $100. Now you have to transfer $200 instead of $100. The solution is to include an idempotency key with every request that might be retried. Let me walk through the safe pattern. Your transfer money function takes from account, to account, amount, and idempotency key. First, you check if a transfer with this idempotency key already exists in your database. If it does, you return the existing result. If it does not exist, you execute the transfer, store the result with the idempotency key, and return. Now, when the client retries with the same idempotency key, the server recognizes that this transfer has already been processed and returns the cached result instead of processing it again. The key insight is that retries and idempotency go hand in hand. You cannot safely implement retries without idempotent operations. Before adding retry logic to any request, make sure the server-side operation is idempotent. Let me go deeper on idempotency key strategies and client implementation. There are 4 main strategies for generating idempotency keys. The first is the client-generated UOID. This is the most general purpose option. The client generates a UOID, like for example as shown in the screen here, starting with 550 and ending in 000, and it sends that with the request. The second is a business identifier like order-12345. This is great for order processing because order ID is a natural idempotency key. The third is a content hash, where you hash the user ID plus amount plus timestamp. This works well for deduplication when you do not have a natural identifier. The fourth is a request ID from the request header, which is useful for API calls where the client is already generating request IDs for tracing. Now let me show you how the client should implement this. Your make request with retry function takes an endpoint, data, and max retries. The critical step is that you generate the idempotency key once before the retry loop. Then, in the loop, you send the same idempotency key with every attempt. If you catch a retriable error, you calculate the backup delay, sleep, and try again with the same key. The key insight here is that the idempotency key must be generated once and reused across all retry attempts. If you generate a new key on each retry, you lose the protection that idempotency provides. The server will see each retry as a new unique request. Now let us talk about circuit breakers, which are one of the most important patterns for preventing cascading failures. Let me walk you through what happens without a circuit breaker. The payment service goes down, and the order service keeps calling the payment service. Every call times out after 5 seconds. Order service threads are blocked waiting for these timeouts. The thread pool gets exhausted because threads are tied up waiting. Order service becomes unresponsive. The failure cascades across your entire system. The circuit breaker pattern prevents this by detecting when a service is failing and stops calling to it. Think of it like an electric circuit breaker that trips when there is too much current. When failures exceed the threshold, the circuit opens. While open, calls fail immediately without actually trying to reach this failing service. After some time, the circuit moves to half open to test if the service had recovered. If the test succeeds, the circuit closes and normal operation resumes. If the test fails, the circuit opens again. The state machine has 3 states and 4 transitions. From closed, when failures exceed the threshold, you transition to open. From open, when the timeout expires, you transition to half open. From half open, if the test request succeeds, you transition back to closed. From half open, if the test request fails, you transition back to open. The key insight is that circuit breakers protect the service from wasting resources on calls that are almost certain to fail. They let you fail fast and apply fallback logic instead of tying up threads waiting for doomed requests. Let me explain each circuit breaker state in more detail. In the closed state, this is normal operation. Requests pass through to the downstream service normally. You are counting failures as they occur. When the failure count exceeds your threshold, you transition to open state. Most of the time, your circuit breaker must be in this state. In the open state, the circuit breaker is protecting your system. Requests are immediately rejected without making an actual call to the downstream service. Instead of waiting for a timeout, you return an error or fall back instantly. This continues until a reset timeout expires, at which point you transition to half-open state to test recovery. In the half-open state, you are testing whether the downstream service has recovered. You allow a limited number of requests through, usually just 1 to 3. If these test requests succeed, the service has recovered and you transition back to closed. If any test request fails, the service is still unhealthy and you transition back to open. Let me also give you the sales transition table as a reference. From closed, when failure threshold is exceeded, you go to open. From open, when reset timeout expires, you go to half open. From half open, when test request succeeds, you go to closed. From half open, when test request fails, you go to open. The key insight is that the half open state is crucial. Without it, you would have no way to detect when the service recovers. You would be stuck in open forever, or you would have to manually reset the circuit. Now let me show you how to actually implement a circuit breaker. The circuit breaker class constructor takes 2 parameters here, for example, failure threshold, which defaults to 5, and reset timeout, which defaults to 30 seconds. You initialize failure count to 0, state to closed, and last failure time to none. The call method is where the logic lives. First, you check if the state is open. If it is, you check if enough time has passed since the last failure. If the reset timeout has expired, you transition to half open to test recovery. If not, you raise a circuit open error immediately without calling the function. If you're not in the open state, you try to call the function. If it succeeds, you call on access to reset the failure count and potentially close the circuit. If it raises an exception, you call on failure to track the failure and potentially open the circuit, then re-raise the exception. This is core pattern. The circuit breaker wraps calls to external services and manages state based on success and failure. When the circuit is open, calls fail fast without actually attempting the operation. The key insight is that the circuit breaker acts as a proxy between your code and the external service. It observes the outcomes and changes its behaviors accordingly. When things are healthy, it is transparent. When things are failing, it protects you. Let me show you the success and failure handling methods that complete the circuit breaker implementation. The on success method is called when a request succeeds. You reset this failure count to 0 because the service is healthy. If the state is half open, meaning you were testing recovery, you transition to closed because the test succeeded and normal operation can resume. The on failure method is called when a request fails. You increment the failure count. You record the current time as last failure time, which is used to determine when to open the transition from open to half open. If the failure count is at above the failure threshold, you transition to open. Also, if you are in half open state and a state request fails, you transition back to open because the service has not been recovered. Now let me show you how to use this in practice. You create a circuit breaker instance for the payment service with a failure threshold of 5 and reset timeout of 30 seconds. In your process payment function, you wrap the call to payment service.charge in the circuit breaker's call method using the lambda. If you catch a circuit open error, you know the circuit is open and you should use a fallback like queuing the order for later processing. The key insight is that you need fallback logic for when the circuit is open. The circuit breaker tells you not to call the service, but you still need to handle the request somehow. Queue it for later, return the cache data, or return a sensible default. Tune circuit breaker parameters. Getting these right is important for balancing fast failure detection against false positives. There are 5 key parameters to configure. The first is failure threshold, which is how many failures trigger the circuit to open. Typical values are 5 to 10 failures. Too low and you will open a circuit on normal transit errors. Too high and you will keep calling a failure service for too long. The second is reset timeout, which is how long to wait before testing recovery. Typical values are 30 to 60 seconds. The third is half open requests, which is how many test requests are allowed in half open state. Typical values are 1 to 3. The fourth is failure window, which is the time window over which failures are counted. Typical values are 60 to 120 seconds. The fifth is success threshold, which is how many consecutive successes are needed to close the circuit from half open. Typical values are 3 to 5 successes. The sliding window is important. Let me show you a sliding window circuit breaker implementation. Instead of counting all time failures, you track failure timestamps in a list. When you record a failure, you add the current timestamp and filter out any failures older than the window size. Then you check if the count or recent failures have exceeded the threshold. This prevents old failures from keeping the circuit open when the service has been healthy for a while. The key insight is that circuit breaker configuration is not one size fits all. It depends on the characteristics of service you are protecting and your tolerance of false positives versus slow failure detection. Let me show you a pattern for managing circuit breakers across multiple operations. That is the circuit breaker registry. You create a circuit breaker registry class that holds a dictionary of circuit breakers. The get method takes a name and optional configuration parameters. If a circuit breaker with that name does not exist, you create one with the provided config. If it already exists, you return the existing one. Then you create different circuit breakers for different operations. For payment, you might use a failure threshold of 5 and a reset timeout of 30 seconds because payment failures are critical and you want to be aggressive. For inventory, you might use a failure threshold of 10 and reset timeout of 60 seconds because inventory checks are important but slightly more tolerant of errors. For notification, you might use a failure threshold of 3 and a reset timeout of 10 seconds because notifications are optional and you can quickly recover. So why use a separate circuit breakers per operations? The reason is because different dependencies have different characteristics. Payment services are critical. If they are failing, you need to know immediately and stop calling them. Notification services are nice to have. You can tolerate more errors before deciding they are unhealthy. Each dependency deserves configuration tuned for its behavior and importance. The key insight is that a single global circuit breaker would not capture these differences. When payment is failing but notifications are healthy, you want to open only the payment circuit while keeping the notifications flowing. When a circuit breaker is open, you cannot just fail the request. You need a fallback strategy. Let me walk you through 4 different fallback strategies. The first strategy is returning the cache data. In your get user profile function, You try to call the user service through the circuit breaker. If you catch a circuit open error, you return the user profile from cache instead. The data might be slightly stale, but it's better than failing completely. This is great for data that changes infrequently and where staleness is acceptable. The second strategy is returning a default value. In your get recommendations function, you try to call the recommendation service through the circuit breaker. If the circuit is open, you return default recommendations, which might be a static list of popular items, not personalized but functional. This works when you have sensible defaults that provide value even if it's not optimal. The third strategy is queuing up for later. In your send notification function, you try to call the notification service through the circuit breaker. If the circuit is open, you enqueue the notification to be processed later when the service recovers. This preserves the intent of operation without losing it entirely. This works for operations that are important but not time critical. The key insight is that fallback strategy should be designed based on the nature of each operation. Not every operation has the same acceptable fallback behavior. Let me show you a fourth fallback strategy that combines multiple approaches, which is graceful degradation. In the get product page function, you start by getting the core product data from the product service. This is required and must succeed, so there is no circuit breaker fallback here. Then you try to enrich the product with reviews by calling the review service through the circuit breaker. If the circuit is open, you set reviews to an empty list. The product page still renders just without reviews. Similarly, you try to get recommendations through the recommendation circuit. If that circuit is open, you set recommendations to an empty list. Finally, you return the product with whatever enrichments you were able to get. This is what is called a graceful degradation. The core functionality still works. Optionally, enrichment fails gracefully. The user gets a useful product page even some supplementary services are down. Now let me give you a decision matrix for choosing the fallback strategies. For critical services like payment, you should queue and retry and notify the user that the action is pending. For enrichment services like reviews, you should return empty and show a partial page. For caching services like user profile, you should return cached or stale data. For fire and forget services like analytics, you should drop silently because the user does not need to know. The key insight is that not all service failures are equally important to the user experience. Now let us talk about the bulkhead pattern, which is one of the most important isolation patterns in distributed systems. The name comes from ship design. Bulkheads are walls that divide the hull into separate compartments. If one compartment floods, the others stay dry and the ship stays afloat. So here's the problem we are trying to solve. Imagine you have a single shared thread pool with 100 threads, and this pool handles requests to 3 different services: the user service, the order service, and the payment service. Everything works fine until one day the payment service becomes slow. Maybe there is a database issue, maybe there is a network condition. Whatever the reason, calls that normally take, let's say, 50 milliseconds, now they are taking even 10 seconds. So what happens next is pretty bad. All 100 threads start making calls to the payment service, and because the payment service is slow, all 100 threads end up getting blocked, waiting for responses that are taking forever. Now here is the critical part. While those threads are waiting for on payment, no threads are available for user service requests or order service requests. A user tries to log in and their request times out because there are no threads to handle. Someone tries to view their orders and that fails too. The slow payment service has effectively taken down your entire system, even though the user service and order service are perfectly healthy. This is called failure propagation, and is one of the most common ways that partial outages become total outages. The solution is bulkhead pattern, so instead of one shared thread pool with 100 threads, you should create separate thread pools for each downstream service. So you might have a user pool with 30 threads, an order pool with 40 threads, and payment pool with 30 threads. Now when the payment service becomes slow, only the payment pool gets exhausted. Those 30 threads get stuck waiting, but the user pool still has 30 healthy threads available and the order pool still has 40 healthy threads available. Users can still log in, users can still view their orders. Yes, payment service is degraded, but the rest of the system continues working as normal. You have essentially isolated the failure to just the component that is actually having problems. So the key insight here is this: bulkhead turns a total system failure into a partial degradation, By isolating the resource pools, you ensure that the problems in one dependency cannot cascade and consume resources needed by healthy dependencies. Now let us look at how to actually implement the bulkhead pattern in code. The most straightforward approach is using thread pool isolation when you create a separate thread pool executor for each downstream service. If you look at the code on the screen, we have a bulkhead executor class that maintains a dictionary of executors. In the constructor, we create three separate thread pool executor instances, one for user operations with 30 workers, one for order operations with 40 workers, and one for payment operations with 30 workers. The submit method takes a bulkhead name and a function to execute. It looks up the appropriate executor from the dictionary and submits the work to the specific pool. This is the key part. When you call bulkhead.submit with user as a bulkhead name, your function runs in the user's thread pool, completely isolated from the payment and order pools. Then we have two example functions showing how to use this. The getUser function submits the work to the user bulkhead and waits up to 5 seconds for a result. The process_payment function submits work to the payment bulkhead and waits up to 10 seconds. Notice that we use different timeouts based on the expected behavior of each service. The beauty of this approach is that when the payment service becomes slow and all 30 payment threads are blocked, the get_user function still works perfectly because it uses a completely separate pool of threads. The failure is contained. So the key takeaway here is that thread pool isolation is the most common and most straightforward way to implement bulkheads, and it works well when you have distinct downstream services with different reliability characteristics. Now let us look at another way to implement bulkheads using semaphores. The semaphore-based approach is a lighter weight than thread pools and works well when you want to limit the concurrency without managing a dedicated pool of threads. Looking at the semaphore bulkhead class here on screen, the constructor takes a max_concurrent parameter and creates a threading.semaphore initialized with that value. The semaphore acts as a gate that only allows a certain number of operations to proceed at once. The call method is where the magic happens. First, we try to acquire the semaphore with an optional timeout. If we cannot acquire it within the timeout period, that means the bulkhead is full and we raise a bulkhead head full error. If we do acquire it, we execute the function inside the try finally block. The finally block ensures that we always release the semaphore slot when we are done, whether the operation succeeded or failed. In the usage example, we create a payment_bulkhead with max_concurrent set to 30. Then, in the process_payment function, we wrap our payment service call inside the bulkhead.call. If the bulkhead is full, meaning 30 payment operations already in flight, we cache the bulkhead full error and queue the order for later processing instead of blocking. The difference between this and the thread pool approach is subtle but very important. With thread pools, you dedicate threads to specific services. With semaphores, you share a common thread pool but limit how many concurrent calls can go to each service. The semaphore approach uses few resources but provides slightly weaker isolation. So when should you use each approach? Thread pool bulkheads are better when you need strong isolation and can afford the resource overhead. Semaphore bulkheads are better when you want lightweight concurrency limiting and your services share similar characteristics. Now let us talk about one of the trickiest aspects of bulkheads, which is figuring out how many threads or semaphore slots to allocate. You should be sizing your bulkheads too small and if you do that, you reject legitimate requests. And if you size them too large, and you defeat the purpose of isolation. The basic formula for calculating bulkhead size is required concurrent calls equals requests per second multiplied by average latency in seconds. Let me walk you through the example on the screen. Say your payment service handles 100 requests per second and the average payment latency is 200 milliseconds, which is 0.2 seconds. Using this formula, 100 times 0.2 equals 20 concurrent calls. This is the theoretical minimum, but you should add a buffer typically around 50% to handle the latency spikes. So 20 times 1.5 gives you 30 threads for a payment bulkhead. Now let us look at the sizing guidelines table. The first row is too small and the impact is that requests get rejected unnecessarily. If you have a bulkhead of only 10 slots but you need 20 concurrent calls, Half of your traffic gets rejected even when the downstream service is healthy. The second row is too large, and the impact is that it defeats the purpose because failure can still spread. If your payment bulkhead has 500 slots and your shared thread pool only has 100 threads, a slow payment service can still exhaust most of your threads. The third row is not isolated, meaning you have a separate limits but shared underlying resources. The fourth row is no monitoring, which means you cannot detect when a bulkhead is approaching exhaustion before it starts rejecting. The code at the bottom shows you how to monitor bulkhead health. The get bulkhead metrics function returns the number of active slots, available slots, maximum capacity, and utilization percentage. You should alert when utilization exceeds some things like 80% so you can investigate before you start shedding load. So the key insight here is that bulkhead sizing is not set and forget. You need to calculate initial sizes based on the expected load and latency, then monitor and adjust based on real world behavior. Now let us shift to graceful degradation, which is a philosophy that partial functionality is better than no functionality. This is one of those concepts that sounds obvious but surprisingly often violated in practice. Think about an e-commerce product page. When everything is working, the page shows product details, product images, customer reviews, personalized recommendations, inventory status, and shipping estimates. 6 different pieces of information, probably coming from 6 different services. Now imagine the review service goes down. What should happen? One approach is to fail the entire page load and show an error to the user. After all, the page is incomplete. But think about this from the user's perspective. They came to buy a product. They can see the product. They can see the price. They can even see if it's in stock. They just cannot see what other customers thought about it. The graceful degradation approach is to show the page anyway with a small notice saying reviews temporarily unavailable. The user can still complete their purchase, the business still makes money. Yes, the experience is slightly worse, but slightly worse is infinitely better than completely broken. Look at the degraded functionality example on the screen. Everything works except the reviews, which shows a friendly message instead of failing. The critical path, the ability to view and purchase the product remains intact. This is the core principle of graceful degradation. Identify which parts of your system are essential and which are enrichments, then design your system so that the enrichment failures never break essential functionality. So the key takeaway is this. When designing any feature, always ask yourself, if this fails, should the whole page fail? Usually the answer is no. Graceful degradation practice. The key is to explicitly classify your features by priority and handle each category differently under failure conditions. Looking at the feature priority class, we define 3 levels. Critical with value 1 means the important where the feature must work or the page fails. Important with the value 2 means the feature should work but we can degrade if needed. Optional with value 3 means it's nice to have but we can drop it entirely under load. The features dictionary maps each feature to its priority level. Product details and inventory status are critical because you cannot sell a product if users cannot see what it is and or whether it is available. Reviews and shipping estimate are important, useful for conversion, but not essential. Recommendations and social share count are optional, pure enrichment. Now let's look at the get product page function. It takes the product ID and the current system load as a percentage. First, we always fetch the critical features, product details, inventory. No try catch, no fallback. These must succeed or the request fails. Then we check if the system load is below 0.8, meaning below the 80% capacity. Only then we do attempt to fetch recommendations and we wrap it in a safe call helper that returns an empty list if anything goes wrong. This means under high load we do not even attempt optional features. Finally, we fetch reviews using safe call with a friendly fallback message. Reviews are important, so we always try to get them, but we degrade gracefully if the service is unavailable. The key insight here is that degradation should be intentional and planned. You decide in advance what features are critical, important, and optional. Then you write code that explicitly handles each category differently. Let us continue with 2 more implementation patterns for graceful degradation. First, the safe call helper function, then progressive degradation based on system load. The safe call function is a simple but powerful utility. It takes a function call, a default value to return on failure, and an optional timeout. Inside, we try to execute the function. If a circuit open error occurs, meaning the circuit breaker is already open, we return the default. Same for timeout error. For any other exception, we log a warning and return the default. This pattern lets you wrap any risky call and guarantees you get back either a real result or a safe fallback. Now let us look at the progressive degradation, which is a more sophisticated approach. The get page with degradation function checks the current system load and returns different versions of the page based on how stressed the system is. If the load is below 50%, we are in a good shape, so that we return the full product page with all the features enabled. If the load is between 50 and 70%, we start shedding, returning the page without optional features like recommendations and social sharing. If the load is between 70 and 90%, things are getting serious, so we return only the critical features, product details, and inventory. And if load exceeds 90%, we are in emergency mode and we return a cache version of the page that might be slightly stale but requires no backend calls at all. This is like having multiple versions of a product page ready to go and you automatically switch between them based on the system health. Users on a healthy system get the full experience. Users during a traffic spike still get a functional page, just with fewer bells and whistles. So the key takeaway is this: graceful degradation is not a single fallback, it's a spectrum. The more gracefully you can degrade across the spectrum, the more resilient your user experience becomes. Shedding, which is a more aggressive form of protection for extreme scenarios. Graceful degradation reduces what you do per request. Load shedding reduces how many requests you handle at all. Here's a scenario. Your system can handle 10,000 requests per second. Suddenly, maybe because of a viral post or even a DDoS attack, you receive 50,000 requests per second. What happens next? Without load shedding, you accept all 50,000 requests. Your system will become overwhelmed. Requests will queue up, memory will fill up, and connections exhaust, and everything will grind to a halt. Eventually, every single request either fails or times out. Your success rate is 0%. With load shedding, you accept only 10,000 requests, the amount you can actually handle. The other 40,000 requests are rejected immediately with a 503 service unavailable response. Yes, those rejected requests fail, but the 10,000 accepted requests succeed, so your success rate is 20%. Now, 20% might not sound great, but is infinitely better than 0%. More importantly, that 20% represents real users who can complete their transactions. Without the load shedding, nobody can do anything. There is a deeper principle here. When a system is overloaded, doing less work often results in more successful outcomes. By protecting your capacity for a subset of requests, you ensure that subset has a good experience rather than giving everyone a bad experience. So the key insight is this: load shedding is about accepting that you cannot serve everyone and making the deliberate choice to serve some people well rather than all people poorly. Now let's look at how to implement basic load shedding in code. The core idea is pretty simple. Track how many requests you are currently processing and reject the new request when you hit your limit. The load shedder class has three pieces of state: current, which tracks how many requests are in flight; max, which is our capacity limit; and a lock for thread safety. The try acquire method is called when a new request arrives. It requires a lock, checks if we are at capacity, and if we are not, increments the counter and returns true. If we are at capacity, it returns false without incrementing. The lock ensures that we never exceed our max even under concurrent access. The release method simply decrements the counter when the request completes. It should always be called in finally block to ensure we release the slot even if the request fails. Now let's look at the handle request function. First, we try to acquire a slot from the shedder. If try acquire method returns false, we immediately return a 503 response with a helpful message. Notice that we do not even attempt to process the request. We fail fast and free, giving the client a clear signal to retry later. If we do acquire a slot, we process the request inside a try finally block. The finally ensures that we call a release whether the request succeeds or fails. This example creates a load shedder with max concurrent set to 1000. This means we'll process at most 1000 requests simultaneously. Request 1001 gets a 503. So the key takeaway is that load shedding is simple to implement. The harder part is choosing the right max concurrent value, which depends on your system's actual capacity under load. Basic load shedding treats all requests equally, but not all requests are equally valuable. A checkout request that is about to generate revenue is more important than a request for personalized recommendations. Priority-based load shedding lets you shed lower value traffic first while protecting the high value traffic. Looking at the priority load shedder class, instead of a single counter, we maintain separate capacities and counters for each priority level. In this example, we reserve 500 slots for high priority, 300 for medium, and 200 for low. The try-equal method takes a priority parameter. First, we calculate the total current load and total capacity. For high priority requests, we use a special rule. If there is any capacity available anywhere in the system, we accept it. This means high priority requests can borrow capacity from lower priority buckets if needed. For medium and low priority requests, we check that if the specific priority level has capacity available. If the low priority bucket is full, we reject the low priority request even if the high priority bucket has room. This creates a natural shedding order. As load increases, low priority slots fill up first and start getting rejected, then medium priority. The high priority requests keep flowing until the entire system is at capacity. The key insight here is that priority-based shedding aligns your technical behavior with your business priorities. When you have to reject requests, you reject the ones that matter least to your business. So now let us look at how to classify requests into priority levels and wire it all together. The table on the screen shows a typical priority classification for an e-commerce system. Checkout and payment requests are high priority, so they should last because they represent users who are ready to give you the money to your business. Product page views and search are medium priority, so they shed second because they represent users who are actually shopping. Recommendations and analytics tracking are low priority, so we shed them first because they are enrichment and measurement that do not directly serve the user. The classify request function shows you how to implement this. We look at the request path and return the appropriate priority. Path starting with /checkout gets high priority. Paths starting with /API/analytics or API/recommendations get low priority. Everything else defaults to medium. In the handle request function, we first classify the request, then we try to acquire a slot at the priority level. If we cannot acquire a slot, we return a 503 response. Notice that we include a retry after a header set to 30 seconds. This tells well-behaved clients to wait before retrying, which helps prevent retry storms from making the overload situation worse. If we do get a slot, we process the request and try finally block, making sure to release the slot with the correct priority level when done. So the key takeaway is this: when implementing load shedding, always think about which requests matter most to your business and protect those requests while shedding lower value traffic first. Checks, which are how your platform actually knows whether your service is healthy enough to receive traffic. There are two fundamentally different types of health checks, and confusing them is actually one of the very important mistakes that you should avoid when you're doing operations for your system. A liveness check answers the question that is this process running and not deadlocked? If the liveness check fails, the platform should kill and restart the container. It's like asking, is the patient alive? The liveness endpoint should be as simple as possible. So looking at the code, our liveness endpoint just returns the status of being alive. No database checks, no dependency checks, nothing that could fail due to external factors. A readiness check answers a different question. Is this service ready to handle the traffic? If the readiness check fails, the platform should remove the instance from the load balancer but not restart it. It's like asking, is the patient ready to go back to work? The readiness endpoint should check everything the service needs to function. So for example, looking at the code, if you see, we check the database connection, the cache connection, critical dependencies. If all checks pass, we return a HTTP 200 with status ready. If any of the checks fail, we return HTTP 503 with status not ready. Here is why the distinction matters. If your database goes down, your service cannot handle requests, so it should fail readiness and be removed from the load balancer. But the process itself is fine. There is no reason to restart it. Restarting would just add more load to an already struggling database as the service retries to connect. So the key insight is this: liveness checks determines whether to restart readiness checks determine whether to route traffic. You should keep them separate and keep liveness checks simple. Now let us go deeper on when each type of health check should fail and what the platform does in response. Looking at the table, liveness should fail when there is a deadlock, an infinite loop, or memory corruption. Basically, when the process is fundamentally broken and needs to be restarted. The platform response is to kill and restart the pod. Readiness should fail when the database is down, when the service is still warming up, or when it is overloaded. The process is fine, it cannot serve the traffic right now. The platform response is to remove it from the load balancer but leave it running. Now let's look at a common mistake. The bad example shows a liveness check that queries the database. This seems reasonable. You want to make sure that the service is connected to the database. But here's the problem. If the database becomes slow, the liveness check times out and Kubernetes kills your pod. But the pod was perfectly healthy. It was just waiting for a slow database. So what happens next is even worse. Kubernetes starts a new pod. The new pod tries to connect to the same slow database. It times out. Kubernetes kills it as well. Now you end up in a restart loop where Kubernetes keeps killing your healthy pods because of a database issue. The good example shows the correct approach. The liveness check is trivial, so it just returns status alive. The database check belongs in the readiness endpoint. If the database is slow, the pod becomes not ready and stops receiving traffic. But it stays alive and it can recover when the database recovers. So the key takeaway is this. You should be never checking your external dependencies in your liveness probe. Liveness should only verify that your process is running. Put all dependency checks in readiness checks. Sometimes you need more than just liveness and readiness. You need a deep health check that examines all dependencies and reports detailed status. This is useful for debugging, for dashboards, and for understanding exactly what is broken when something goes wrong. Looking at the code, we have three helper functions. The check database connection function that tries to run a simple query and returns true or false. The check cache connection function that pings the cache and returns true or false. The check downstream service function that makes an HTTP request to another service health endpoint with a 2-second timeout. The deep health endpoint calls all these checks and assembles a dictionary with the results. It checks the database, the cache, the user service, and the payment service. Then it determines if all checks have passed using the Python's all function. If everything is healthy, we return a 200 status code with status healthy. If anything failed, we return a 503 with status degraded. Crucially, we include the individual check results in the response body, so whoever is calling this endpoint can see exactly which dependency is causing problems. A few important notes about deep health checks. First, you should not be using them for liveness or readiness probes because they are too slow and check too many things. Second, you should set aggressive timeouts on the dependency checks, like the 2-second timeout in the example, so a slow dependency does not make your health check hang. Third, these are great for operation dashboards and for the first step in the incident response. So the key takeaway is this. Deep health checks gives you visibility in your dependency tree. They answer just the okay, is the service healthy, but also okay, what exactly is broken right now? Let us talk about a specific problem that trips up many teams. Applications that take a long time to start. Maybe your service needs to load a large machine learning model into memory. Maybe it needs to warm up caches. Maybe it just has a lot of initialization to do. Now here's the problem. Your application takes 30 seconds, 60 seconds to restart. Let's say your liveness check has a 10-second timeout. After 10 seconds, the platform sees that the liveness check is failing and kills the container. The container never finishes starting, so it gets stuck in an endless restart loop. The solution for this problem is a startup probe, which is a special type of health check that only runs during startup. While the startup probe is running, liveness and readiness probes are disabled. Once the startup probe succeeds, normal liveness and readiness probes take over. Looking at the Kubernetes configuration, we configure the startup probe to check the /health/startup endpoint. We set the failure threshold to 30 and period seconds to 10. That means Kubernetes will try the startup probe every 10 seconds and allow up to 30 failures. The total startup window is 30 times 10, which is 300 seconds or 5 minutes. Notice that the liveness probe has initial delay seconds set to 0. This is fine because the liveness probe only starts after the startup probe succeeds. We do not need to manually delay it. The startup endpoint is simple. We have a global variable startup underscore complete and the start says false. Our initialization code sets to true when everything is ready. The endpoint returns HTTP 200 if startup is complete. Otherwise, it returns HTTP 503. So the key takeaway is this. If your application takes more than a few seconds to start, you should be using a startup probe to give it time to initialize without being killed by the liveness probe. Now let us move into chaos engineering, which is the practice of deliberately injecting failures into a system to verify that it handles them correctly. This might sound counterintuitive. Why would you intentionally break things? But the logic is pretty sound. You would want to find weaknesses on your terms during business hours with engineers watching rather than discovering them during a real incident at 3 a.m. The definition is simple. Deliberately inject failures to verify your system handles them correctly. Let us walk through the principles in the table. First, you build a hypothesis. Before you run any experiment, you should have a clear expectation of what will happen. For example, if the cache fails, the system will continue serving 95% of requests from the database with higher latency. If you do not have a hypothesis, you do not know what you are testing. Second, vary real world events. Your chaos experiments should simulate actual failure modes that could happen in production. Network partitions, disk filling up, a downstream service timing out. Do not invent unrealistic scenarios. Third, run in production. This is controversial, but again, it's pretty important. Staging environments cannot replicate the complexity, scale, and configuration of production. You can and should start with staging, but the real value comes from production environments. Fourth, minimize the blast radius. Start small and contain the impact. Maybe affect just 1% of the traffic. Maybe target a single availability zone. Have your kill switches ready. Fifth, automate the experiments. Chaos engineering should be repeatable and scheduled, not ad hoc. Automated experiments run regularly, catch regressions before they reach customers. So the key insight is this. Chaos engineering is about building confidence in a system's resilience through controlled scientific experimentation. Let us look at different categories of chaos experiments you might run. First, infrastructure chaos. Killing an instance tests your auto-scaling and load balancing. If you kill a server and traffic seamlessly shifts to other servers, your redundancy is working. Filling the disk tests how your application behaves under disk pressure. Does it gracefully reject writes? Does it crash? Network latency tests your timeout configuration. If you add 500 milliseconds of latency to a dependency, do your timeouts handle it correctly? Network partition tests split brain scenarios. So what happens when half of your cluster cannot talk to the other half? CPU stress tests how your application behaves when throttled and whether queue buildup is handled correctly. Second, application chaos. Dependency failure tests your circuit breakers and fallbacks. If the payment service return errors, does your circuit breakers open? Do your fallback strategies work? Slow responses test timeout handling. If a service takes 30 seconds to respond, does your application hang or fail fast? Error injection tests your error handling paths. These paths are often the least tested because they are hard to trigger in normal operation. Resource exhaustion tests your connection pool limits and bulkheads. So what happens when all database connections are in use? The key insight here is that the chaos experiments should map to real failure modes you have seen or expected to see. Every experiment should have a corresponding production scenario that could actually happen. Now let us look at how to implement basic chaos injection in your application. The simplest approach is a middleware that randomly fails or delays a percentage of requests. The chaos underscore config dictionary holds the configuration. We have enabled a boolean to turn the chaos on or off. We have a failure rate set to 0.01, meaning 1% of requests will fail. We have a latency rate set to 0.05, meaning 5% of requests will have latency added to them. And latency underscore ms set to 2000, meaning we add 2 seconds of delay. The chaos middleware function runs on every request. First, we check if the chaos is enabled. If not, we just pass the request through normally. Then we check if we should inject a failure. We generate a random number between 0 and 1. If it's less than our failure rate of 0.01, we log that and we are injecting a failure and return a 500 response immediately. The request never reaches the actual handler. If we did not inject a failure, we check if we should inject latency. Again, we generate a random number. If it is less than the latency rate of 0.05, we calculate the delay in seconds and sleep for that duration before passing the request through. If neither condition triggers, the request proceeds normally. This simple but effective approach for testing how your clients handle errors and slowness. The key is making it configurable so you can tune the rates and disable it quickly if something goes wrong. So the key takeaway is that chaos injection can be as simple as middleware with some random number generation. So you should be starting simple and add sophistication as you learn what you need. The basic middleware approach affects all traffic equally, but sometimes you want to inject the chaos into specific services or service paths. This targeted approach gives you more control and lets you test specific failure scenarios. The Chaos Monkey class maintains a dictionary of rules, where each rule specifies the failure rate and latency for a particular service. The add rule method lets you configure chaos for a specific service. The should fail method checks if you should inject a failure for a given service. The get latency method returns how much latency to add. Looking at the usage, we create a Chaos Monkey instance and add two rules. The payment service rule has a 10% failure rate, which is much higher than the global 1% because we specifically want to test payment failure handling. The user service rule adds 500 milliseconds of latency to test timeout handling for user operations. The call service function wraps any service call with chaos injection. First, we check the should fail for that service. If true, we raise a chaos injected error. Then we check for get underscore latency and sleep if needed. Finally, we execute the actual function. This targeted approach is powerful for testing specific hypotheses, wanting to verify that your checkout flow handles payment failures gracefully. So you should do this. Set the repayment service to 50% failure rate and then you run through the checkout. If you want to test if your user profile page degrades gracefully when the user profile is slow, then you should add 2 seconds of latency to the user service. So the key takeaway is that targeted chaos injection lets you test specific failure scenarios without affecting your entire system. You can test what happens when payment fails without also failing everything else. Chaos engineering in production can be dangerous if done without proper caution. Let us talk about how to run chaos experiments safely. The Safe Chaos class implements blast radius control. We have enabled as a click kill switch, so we have affected underscore person set to just 1%, meaning 99% of requests are unaffected. And we have excluded paths for routes that should have never have chaos injected. The should underscore inject method checks three conditions. First, is chaos enabled at all? Second, is this request on an excluded path? We never inject chaos on, let's say, path checkout or path payment because those directly affect revenue. Third, we only inject on 1% of the remaining traffic. Now let us look at the safety rules table. So the first rule is to start with 0.1% of traffic. This seems tiny, but it lets you validate that your monitoring can detect the injected failures before you scale up. If you cannot see the failures in your dashboards, you're not ready for larger experiments. Second, exclude the critical paths. Whatever makes you money, protect it. You can test those paths in staging. Third, have a kill switch. You need to be able to stop chaos injection immediately. The enable flag should be flippable via a feature flag system, not a code deploy. Fourth, you should be running during business hours. You would want the engineers to be available to respond if something unexpected happens. You should not be running chaos experiments at 2 a.m. Fifth, you should be monitoring closely. You should be watching your metrics and dashboard during the experiments, so you're looking for unexpected cascading failures that your hypothesis did not predict. So the key takeaway is this. Chaos engineering is about controlled experimentation, not reckless destruction. You should be starting small, exclude the critical paths, and always have a way to stop immediately. Before we wrap up the reliability section, let us look at some common mistakes that undermine resilience. These are the anti-patterns that I see teams fall into repeatedly, and you should definitely avoid them. Anti-pattern number 1 is making external calls without timeouts. Looking at the bad example, we just call request.get with a URL and no timeout. This request can hang forever if the remote server does not respond. Your thread or connection is stuck indefinitely. If you do this enough times, and you will exhaust your thread pool. The good example adds a timeout tuple. The first value is 3 is the connection timeout in seconds. The second value 10 is the read timeout. So you wait up to 3 seconds to establish a connection and up to 10 seconds to read the response. After that, we get a timeout exception and can handle it appropriately. Handy pattern number 2 is retrying without a backup. So the bad example shows a loop that retries immediately on failure. The problem is that if the service you're calling is overloaded, hitting it 3 times in rapid succession just adds to the overload. You're just making things worse for this service. The good example uses exponential backoff. So on the first retry, we sleep for 2 to the power 0, which is 1 second. On the second retry, we sleep for 2 to the power 1, which is 2 seconds. This gives the failing service time to recover between the attempts. So the key takeaway from these first 2 anti-patterns are always set timeouts on external calls and always use backoff between retries. These are non-negotiable in production systems. Let us continue with more anti-patterns to avoid. Anti-pattern number 3 is retrying non-idempotent operations. The bad example shows a loop that retries a charge underscore card call. What happens if the first call succeeds, but the response is lost due to a network glitch? We retry and charge the credit card of the customer again. The customer gets charged twice or 3 times, and this is a real problem that will cause problems for the business. The good example shows the fix. You should be using the idempotency key. The charge underscore card function takes an idempotency underscore key parameter, which is the order underscore ID. The payment processor tracks which idempotency keys have been processed. If we retry with the same key, the processor returns the previous result instead of charging again. Now the retries are safe. Anti-pattern number 4 is putting the circuit breaker at the wrong level. The bad example shows one circuit breaker for all database operations. The problem is that if one type of query starts failing, the circuit opens and blocks all database operations, including healthy ones. The good example shows separate circuits for user queries and order queries. If user queries start failing, only the user circuit opens. Order queries continue working. So the finer-grained circuits mean finer-grained degradation. Anti-pattern number 5 is having liveness checks depend on the external services. We covered this earlier. So the bad example shows a liveness check that pings an external service. If that service is slow, your pod gets killed. The good example keeps the liveness trivial and self-contained. So the key takeaway from this slide is you should be using idempotency keys for payment operations, use the fine-grained circuit breakers, and keep the liveness check simple. Each of these anti-patterns has caused real production incidents, so you should be following the best practices here. In the reliability section, we'll go through each pattern with its key takeaways. Timeouts. Every external call must have a timeout, no exceptions. You should be using cascading timeouts where inner calls have shorter timeouts than outer calls, so the outer call can handle the inner timeout gracefully. Separate connection timeouts from read timeouts because they represent different failure modes. Number 2 is retries. You should be using exponential backoff with jitter to avoid thundering herd problem. You should be implementing retry budgets to limit how much retries amplify load, something like 10% additional traffic from retries. Only retry idempotent operations or use idempotency keys to make key operations safe to retry. The third is circuit breakers. Their purpose is to prevent cascade failures by failing fast when a dependency is unhealthy. Remember the 3 states: closed, where the traffic flows normally; open, where the traffic fails immediately; and half open, where we test if the dependency has recovered. Configure the circuit breakers per operation rather than globally for more precise degradation, and always have a fallback strategy for when the circuit is open. Continuing the summary with the remaining patterns. So number 4 is bulkheads. So the purpose is to isolate failures by separating the resource pools. If one dependency fails, it cannot consume resources needed by the healthy dependencies. You should be sizing bulkheads based on expected load and latency using the formula we discussed. Monitor the utilization so you can detect exhaustion before you start ejecting traffic. Next is graceful degradation. You should be prioritizing features into critical, important, and optional categories. You should be dropping optional features first under the load. The core principle is that partial functionality beats total failure. Users can still accomplish their goals even if the experience is slightly reduced. Next is load shedding. When overwhelmed, reject the request to protect the system capacity. You should be shedding low priority requests first to protect high value traffic. Return 503 with a retry after header so clients know when to retry. Remember that 20% success is better than 0% success. Next is health checks. Liveness check answers, okay, is this process running? And trigger the restarts if they fail. Readiness checks answer that, okay, can it handle the traffic? And trigger the removal from load balancing if they fail. You should be using startup probes for applications that take a long time to initialize. So the key takeaway from this entire section is that reliability is not just one thing, it's a collection of patterns that work together. Timeouts enable retries, circuit breakers enable fallbacks, bulkheads enable graceful degradation, and each reliability pattern reinforces the other reliability patterns. So all of these patterns are super important collectively for having good reliability for your system design in production.